Preface to the 9th edition of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. Principles of Geology by Charles Lyell. The Principles of Geology in the first 5 editions embrace not only a view of the modern changes of the earth and its inhabitants, as set forth in the present work, but also some account of those monuments of analogous changes of ancient date, both in the organic and inorganic world, which it is the business of the geologist to interpret. The subject last mentioned, or Geology proper, constituted originally a 4th book, now omitted, the same having been enlarged into a separate treatise, first published in 1838 in 1 volume, 12/12, and called The Elements of Geology, afterwards recast in 2 volumes, 12/12, in 1842, and again re-edited under the title of Manual of Elementary Geology in 1 volume, 8/8, in 1851. The Principles and Manual, thus divided, occupy, with one exception to which I shall presently allude, very different ground. The Principles treat of such portions of the economy of existing nature, animate and inanimate, as are illustrative of geology, so as to comprise an investigation of the permanent effects of causes now in action, which may serve as records to after ages of the present condition of the globe and its inhabitants. Such effects are the enduring monuments of the ever-varying state of the physical geography of the globe, the lasting signs of its destruction and renovation, and the memorials of the equally fluctuating condition of the organic world. They may be regarded, in short, as a symbolical language in which the earth's autobiography is written. In the Manual of Elementary Geology, on the other hand, I have treated briefly of the component materials of the earth's crust, their arrangement and relative position, and their organic contents, which, when deciphered by aid of the keys supplied by the study of the modern changes above alluded to, reveal to us the annals of a grand succession of past events, a series of revolutions which the solid exterior of the globe and its living inhabitants have experienced in times antecedent to the creation of man. In thus separating the 2 works, however, I have retained the Principles, Book I, the discussion of some matters which might fairly be regarded as common to both treatises, as, for example, an historical sketch of the early progress of geology, followed by a series of preliminary essays to explain the facts and arguments which lead me to believe that the forces now operating upon and beneath the earth's surface may be the same, both in kind and degree, as those which at remote epochs have worked out geological changes. See Analysis of Contents of this work, page 9. If I am asked whether the Principles or the Manual should be studied first, I feel much the same difficulty in answering the question as if a student should inquire whether he ought to take up first a treatise on chemistry or one on natural philosophy, subjects sufficiently distinct, yet inseparably connected. On the whole, while I have endeavored to make each of the 2 treatises in their present form quite independent of the other, I would recommend the reader to study first the modern changes of the earth and its inhabitants as they are discussed in the present volume, proceeding afterwards to the classification and interpretation of the monuments of more remote ages. Charles Lyell, 11 Harley Street, London, May 24, 1853. End of Preface to the 9th edition of Principles of Geology.
Chapter 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Principles of Geology by Charles Lyell. Book 1, Chapter 1. Geology is the science which investigates the successive changes that have taken place in the organic and inorganic kingdoms of nature. It inquires into the causes of these changes and the influence which they have exerted in modifying the surface and external structure of our planet. By these researches into the state of the earth and its inhabitants at former periods, we acquire a more perfect knowledge of its present condition, and more comprehensive views concerning the laws now governing its animate and inanimate productions. When we study history, we obtain a more profound insight into human nature by instituting a comparison between the present and former states of society. We trace the long series of events which have gradually led to the actual posture of affairs, and by connecting effects with their causes, we are enabled to classify and retain in the memory a multitude of complicated relations, the various peculiarities of national character, the different degrees of moral and intellectual refinement, and numerous other circumstances which, without historical associations, would be uninteresting or imperfectly understood. As the present condition of nations is the result of many antecedent changes, some extremely remote, and others recent, some gradual, others sudden and violent, so the state of the natural world is the result of a long succession of events. And if we would enlarge our experience of the present economy of nature, we must investigate the effects of her operations in former epochs. We often discover with surprise, on looking back into the chronicles of nations, how the fortune of some battle has influenced the fate of millions of our contemporaries, when it has long been forgotten by the mass of the population. With this remote event, we may find inseparably connected the geographical boundaries of a great state, the language now spoken by the inhabitants, their peculiar manners, laws, and religious opinions. But far more astonishing and unexpected are the connections brought to light when we carry back our researches into the history of nature. The form of a coast, the configuration of the interior of a country, the existence and extent of lakes, valleys, and mountains can often be traced to the former prevalence of earthquakes and volcanoes in regions which have long been undisturbed. To these remote convulsions, the present fertility of some districts, the sterile character of others, the elevation of land above the sea, the climate, and various peculiarities may be distinctly referred. On the other hand, many distinguishing features of the surface may often be ascribed to the operation at a remote era of slow and tranquil causes, to the gradual deposition of sediment in a lake or in the ocean, or to the prolific increase of testacea and corals. To select another example, we find in certain localities subterranean deposits of coal, consisting of vegetable matter formerly drifted into seas and lakes. These seas and lakes have since been filled up. The lands whereon the forests grew have disappeared or changed their form. The rivers and currents which floated the vegetable masses can no longer be traced, and the plants belong to species which for ages have passed away from the surface of our planet. Yet the commercial prosperity and numerical strength of a nation may now be mainly dependent on the local distribution of fuel determined by that ancient state of things. Geology is intimately related to almost all the physical sciences, as history is to the moral. An historian should, if possible, be at once profoundly acquainted with ethics, politics, jurisprudence, the military art, theology, in a word, with all branches of knowledge by which any insight into human affairs or into the moral and intellectual nature of man can be obtained. It would be no less desirable that a geologist should be well versed in chemistry, natural philosophy, mineralogy, zoology, comparative anatomy, botany, in short, in every science relating to organic and inorganic nature. With these accomplishments, the historian and geologist would rarely fail to draw correct and philosophical conclusions from the various monuments transmitted to them of former occurrences. They would know to what combination of causes analogous effects were referable. They would often be enabled to supply, by inference, information concerning many events unrecorded in the defective archives of former ages. But as such extensive acquisitions are scarcely within the reach of any individual, it is necessary that men who have devoted their lives to different departments should unite their efforts. And as the historian receives assistance from the antiquary and from those who have cultivated different branches of moral and political science, so the geologist should avail himself of the aid of many naturalists, and particularly of those who have studied the fossil remains of lost species of animals and plants. The analogy, however, of the monuments consulted in geology and those available in history extends no farther than to one class of historical monuments, those which may be said to be undesignedly commemorative of former events. The canoes, for example, and stone hatchets found in our peat bogs afford an insight into the rude arts and manners of the earliest inhabitants of our island. The buried coin fixes the date of the reign of some Roman emperor. The ancient encampment indicates the districts once occupied by invading armies, and the former method of constructing military defenses. The Egyptian mummies throw light on the art of embalming, the rites of sepulture, or the average stature of the human race in ancient Egypt. This class of memorials yields to no other in authenticity, but it constitutes a small part only of the resources on which the historian relies. Whereas in geology, it forms the only kind of evidence which is at our command. For this reason, we must not expect to obtain a full and connected account of any series of events beyond the reach of history. But the testimony of geological monuments, if frequently imperfect, possesses at least the advantage of being free from all intentional misrepresentation. We may be deceived in the inferences which we draw, in the same manner as we often mistake the nature and import of phenomena observed in the daily course of nature. But our liability to err is confined to the interpretation, and if this be correct, our information is certain. It was long before the distinct nature and legitimate objects of geology were fully recognized, and it was at first confounded with many other branches of inquiry, such as the limits of history, poetry, and mythology were ill-defined in the infancy of civilization. Even in Werner's time, or at the close of the 18th century, geology appears to have been regarded as little other than a subordinate department of mineralogy, and Desmarest included it under the head of physical geography. But the most common and serious source of confusion arose from the notion that it was the business of geology to discover the mode in which the earth originated, or, as some imagined, to study the effects of those cosmological causes which were employed by the author of nature to bring this planet out of a nascent and chaotic state into a more perfect and habitable condition. Hutton was the first to endeavor to draw a strong line of demarcation between his favorite science and cosmogony, for he declared that geology was in no wise concerned, quote, with questions as to the origin of things, unquote. An attempt will be made in the sequel of this work to demonstrate that geology differs as widely from cosmogony as speculations concerning the mode of the first creation of man differ from history. But before entering more at large on this controverted question, it will be desirable to trace the progress of opinion on this topic from the earliest ages to the commencement of the present century. End of Chapter 1.
Chapter 2, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick McHaffie, Chicago. Principles of Geology by Charles LYELL. Chapter 2, Part 1. Chapter 2. Historical Sketch of the Progress of Geology. Oriental Cosmogony, Hymns of the Vedas, Institutes of Menu, Doctrine of the Successive Destruction and Renovation of the World, Origin of this Doctrine, Common to the Egyptians, Adopted by the Greeks, System of Pythagoras, of Aristotle, Dogmas concerning the extinction and reproduction of genera and species, Strabo's theory of elevation by earthquakes, Pliny, Concluding Remarks on the Knowledge of the Ancients. Oriental Cosmogony. The earliest doctrines of the Indian and Egyptian schools of philosophy agreed in ascribing the first creation of the world to an omnipotent and infinite being. They concurred also in representing this being, who had existed from all eternity, as having repeatedly destroyed and reproduced the world and all its inhabitants. In the sacred volume of the Hindus, called the Ordinances of Menu, comprising the Indian system of duties, religious and civil, we find a preliminary chapter treating of the creation, in which the cosmogony is known to have been derived from earlier writings and traditions, and principally from certain hymns of high antiquity, called the Vedas. These hymns were first put together, according to Mr. Colebrook, in a connected series about 13 centuries before the Christian era, but they appear from internal evidence to have been written at various antecedent periods. In them, as we learn from the researches of Professor Wilson, the eminent Sanskrit scholar, two distinct philosophical systems are discoverable. According to one of them, all things were originally brought into existence by the sole will of a single first cause, which existed from eternity. According to the other, there have always existed two principles, the one material, but without form, the other spiritual, and capable of compelling, quote, inert matter to develop its sensible properties, end quote. This development of matter into, quote, individual and visible existences, end quote, is called creation, and is assigned to a subordinate agent, or the creative faculty of the Supreme Being embodied in the person of Brahma. In the first chapter of the Ordinances of Menu, above alluded to, we meet with the following passages relating to former destructions and renovations of the world. Quote, the being, whose powers are incomprehensible, having created me, Menu, and this universe, again became absorbed in the Supreme Spirit, changing the time of energy for the hour of repose. When the power awakes, then has this world its full expansion, but when he slumbers with a tranquil spirit, then the whole system fades away. For while he reposes, as it were, embodied spirits endowed with principles of action depart from their several acts, and the mind itself becomes inert. End quote. The absorption of all beings into the supreme essence is then described, and the divine soul itself is said to slumber, and to remain for a time immersed in, quote, the first idea, or in darkness, end quote. After which the text thus proceeds, verse 57, quote, thus that immutable power, by waking and reposing alternatively, revivifies and destroys, in eternal succession, this whole assemblage of locomotive and immovable creatures, end quote. It is then declared that there has been a long succession of manvantaras, or periods, each of the duration of many thousand ages, and, quote, there are creations also and destructions of worlds innumerable. The being, supremely exalted, performs all this with as much ease as if in sport, again and again, for the sake of conferring happiness. End quote. No part of the Eastern cosmogony from which these extracts are made is more interesting to the geologist than the doctrine, so frequently alluded to, of the reiterated submersion of the land beneath the waters of a universal ocean. In the beginning of things, we are told, the first sole cause, quote, with a thought created the waters, end quote, and then moved upon their surface in the form of Brahma the Creator, by whose agency the emergence of the dry land was effected, and the peopling of the earth with plants, animals, celestial creatures, and man. Afterwards, as often as a general conflagration at the close of each manvantara had annihilated every visible and existing thing, Brahma, on awakening from his sleep, finds the whole world a shapeless ocean. Accordingly, in the legendary poems called the Puranas, composed at a later date than the Vedas, the three first avatars, or descents, of the deity upon earth have for their object to recover the land from the waters. For this purpose, Vishnu is made successively to assume the form of a fish, a tortoise, and a boar. Extravagant as may be some of the conceits and fictions which disfigure these pretended revelations, we can by no means look upon them as a pure effort of the unassisted imagination, or believe them to have been composed without regard to opinions and theories founded on the observation of nature. In astronomy, for instance, it is declared that at the North Pole the year was divided into a long day and night, and that their long day was the northern, and their night the southern course of the sun. And to the inhabitants of the moon it is said one day is equal in length to 1 month of mortals. If such statements cannot be resolved into mere conjectures, we have no right to refer to mere chance the prevailing notion that the earth and its inhabitants had formerly undergone a succession of revolutions and aqueous catastrophes interrupted by long intervals of tranquillity. Now, there are two sources in which such a theory may have originated. The marks of former convulsions on every part of the surface of our planet are obvious and striking. The remains of marine animals embedded in the solid strata are so abundant that they may be expected to force themselves on the attention of every people who have made some progress in refinement, and especially where one class of men are expressly set apart from the rest, like the ancient priesthoods of India and Egypt, for study and contemplation. If these appearances are once recognized, it seems natural that the mind should conclude in favor not only of mighty changes in past ages, but of alternate periods of repose and disorder. Of repose when the animals, now fossil, lived, grew, and multiplied; of disorder when the strata in which they were buried becomes transferred from the sea to the interior of continents, and were uplifted so as to form part of high mountain chains. Those modern writers who are disposed to disparage the former intellectual advancement and civilization of Eastern nations may concede some foundation of observed facts for the curious theories now under consideration, without indulging in exaggerated opinions of the progress of science, especially as universal catastrophes of the world and exterminations of organic beings in the sense in which they were understood by the Brahmins are untenable doctrines. We know that the Egyptian priests were aware not only that the soil beneath the plains of the Nile, but that also the hills bounding the great valley contained marine shells, and Herodotus inferred from these facts that all Lower Egypt, and even the high lands above Memphis, had once been covered by the sea. As similar fossil remains occur in all parts of Asia hitherto explored, far in the interior of the continent, as well as near the sea, they could hardly have escaped detection by some Eastern sages not less capable than the Greek historian of reasoning philosophically on natural phenomena. We also know that the rulers of Asia were engaged in very remote areas in executing great national works, such as tanks and canals, requiring extensive excavations. In the 14th century of our era, in the year 1360, the removal of soil necessary for such undertakings brought to light geological facts which attracted the attention of a people less civilized than were many of the older nations of the East. The historian Ferishtah relates that 50,000 laborers were employed in cutting through a mound so as to form a junction between the rivers Selima and Sutlej, and in this mound were found the bones of elephants and men, some of them petrified, and some of them resembling bone. The gigantic dimensions attributed to the human bones show them to have belonged to some of the larger pachydermata. But although the Brahmins, like the priests of Egypt, may have been acquainted with the existence of fossil remains in the strata, it is possible that the doctrine of successive destructions and renovations of the world merely received corroboration from such proofs, and that it may have been originally handed down, like the religious traditions of most nations, from a ruder state of society. The system may have had its source, in part at least, in exaggerated accounts of those dreadful catastrophes, which are occasioned by particular combinations of natural causes. Floods and volcanic eruptions, the agency of water and fire, are the chief instruments of devastation on our globe. We shall point out in the sequel the extent of many of these calamities recurring at distant intervals of time in the present course of nature, and shall only observe here that they are so peculiarly calculated to inspire a lasting terror, and are so often fatal in their consequences to great multitudes of people, that it scarcely requires the passion for the marvelous so characteristic of rude and half-civilized nations, still less the exuberant imagination of Eastern writers, to augment them into general cataclysms and conflagrations. The great flood of the Chinese, which their traditions carry back to the period of Yahoo, something more than 2,000 years before our era, has been identified by some persons with the universal deluge described in the Old Testament. But according to Mr. Davis, who accompanied 2 of our embassies to China, and who has carefully examined their written accounts, the Chinese cataclysm is therein described as interrupting the business of agriculture, rather than as involving a general destruction of the human race. The great Yu was celebrated for having, quote, opened 9 channels to draw off the waters, end quote, which, quote, covered the low hills and bathed the foot of the highest mountains, end quote. Mr. Davis suggests that a great derangement of waters of the Yellow River, one of the largest in the world, might even now cause the flood of Yahoo to be repeated, and lay the most fertile and populous plains of China under water. In modern times, the bursting of the banks of an artificial canal, into which a portion of the Yellow River has been turned, has repeatedly given rise to the most dreadful accidents, and is a source of perpetual anxiety to the government. It is easy, therefore, to imagine how much greater may have been the inundation if this valley was ever convulsed by a violent earthquake. Humboldt relates the interesting fact that, after the annihilation of a large part of the inhabitants of Cumana by an earthquake in 1766, a season of extraordinary fertility ensued, in consequence of the great rains which accompanied the subterranean convulsions. The Indians, he says, celebrated after the ideas of an antique superstition, by festivals and dancing, the destruction of the world and the approaching epoch of its regeneration. The existence of such rites among the rude nations of South America is most important, as showing what effects may be produced by local catastrophes, recurring at distant intervals of time on the minds of a barbarous and uncultivated race. I shall point out in the sequel how the tradition of a deluge among the Araucanian Indians may be explained, by reference to great earthquake waves, which have repeatedly rolled over part of Chile since the first recorded flood of 1590. The legend also of the ancient Peruvians of an inundation many years before the reign of the Incas, in which only 6 persons were saved on a float, relates to a region which has more than once been overwhelmed by inroads of the ocean since the days of Pizarro. I might refer the reader to my account of the submergence of a wide area in Kutch, so lately as the year 1819, when a single tower only of the fort of Sindri appeared above the waste of waters. If it were necessary to prove how easily the catastrophes of modern times might give rise to traditionary narratives among a rude people of floods of boundless extent. Nations without written records, and who are indebted for all their knowledge of past events exclusively to oral tradition, are in the habit of confounding in one legend a series of incidents which have happened at various epochs, nor must we forget that the superstitions of a savage tribe are transmitted through all the progressive stages of society, till they exert a powerful influence on the mind of the philosopher. He may find in the monuments of former changes on the earth's surface an apparent confirmation of tenets handed down through successive generations from the rude hunter whose terrified imagination drew a false picture of those awful visitations of floods and earthquakes, whereby the whole earth, as known to him, was simultaneously devastated. Egyptian Cosmogony. Respecting the cosmogony of the Egyptian priests, we gather much information from writers of the Grecian sects, who borrowed almost all their tenets from Egypt, and amongst others that of the former successive destruction and renovation of the world. We learn from Plutarch that this was the theme of the hymns of Orpheus, so celebrated in the fabulous ages of Greece. It was brought to him from the banks of the Nile, and we even find in his verses, as in the Indian systems, a definite period assigned for the duration of each successive world. The returns of great catastrophes were determined by the period of the Annus Magnus, or Great Year, a cycle composed of the revolutions of the sun, moon, and planets, and terminating when these returned together to the same sign whence they were supposed at some remote epoch to have set out. The duration of this great cycle was variously estimated. According to Orpheus, it was 120,000 years, according to others, 300,000, and by Cassander, it was taken to be 360,000 years. We learn particularly from the Timaeus of Plato that the Egyptians believed the world to be subject to occasional conflagrations and deluges, whereby the gods arrested the career of human wickedness and purified the earth from guilt. After each regeneration, mankind were in a state of virtue and happiness, from which they gradually degenerated again into vice and immorality. From this Egyptian doctrine, the poets derived the fable of the decline from the Golden to the Iron Age. The sect of Stoics adopted most fully the system of catastrophes destined at certain intervals to destroy the world. Those they taught were of two kinds: the cataclysm, or destruction by water, which sweeps away the whole human race and annihilates all the animal and vegetable productions of nature, and the ekpyrosis, or destruction by fire, which dissolves the globe itself. From the Egyptians also they derived the doctrine of the gradual debasement of man from a state of innocence. Towards the termination of each era, the gods could no longer bear with the wickedness of men, and a shock of the elements or a deluge overwhelmed them, after which calamity Astrea again descended on the earth to renew the Golden Age. The connection between the doctrine of successive catastrophes and repeated deteriorations in the moral character of the human race is more intimate and natural than might at first be imagined. For, in a rude state of society, all great calamities are regarded by the people as judgments of God on the wickedness of man. Thus, in our own time, the priests persuaded a large part of the population of Chile, and perhaps believed themselves, that the fatal earthquake of 1822 was a sign of the wrath of heaven for the great political revolution just then consummated in South America. In like manner, in the account given to Solon by the Egyptian priests of the submersion of the island of Atlantis under the waters of the ocean, after repeated shocks of an earthquake, we find that the event happened when Jupiter had seen the moral depravity of the inhabitants. Now, when the notion had once gained ground, whether from causes before suggested or not, that the earth had been destroyed by several general catastrophes, it would next be inferred that the human race had been as often destroyed and renovated. And since every extermination was assumed to be penal, it could only be reconciled with divine justice by the supposition that man, at each successive creation, was regenerated in a state of purity and innocence. A very large portion of Asia, inhabited by the earliest nations, whose traditions have come down to us, has been always subject to tremendous earthquakes. Of the geographical boundaries of these and their effects, I shall speak in the proper place. Egypt has, for the most part, been exempt from this scourge, and the Egyptian doctrine of great catastrophes was probably derived in part, as before hinted, from early geological observations, and in part from Eastern nations. End of Chapter 2, Part 1. Recording by Patrick McHaffie, Chicago. Chapter 2, Part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick McHaffie, Chicago. Principles of Geology by Charles LYELL. Chapter 2, Part 2. Pythagorean Doctrines. Pythagoras, who resided for more than 20 years in Egypt and, according to Cicero, had visited the East and conversed with the Persian philosophers, introduced into his own country on his return the doctrine of the gradual deterioration of the human race from an original state of virtue and happiness. But if we are to judge of his theory concerning the destruction and renovation of the earth from the sketch given by Ovid, we must concede it to have been far more philosophical than any known version of the cosmogonies of Oriental or Egyptian sects. Although Pythagoras is introduced by the poet as delivering his doctrine in person, some of the illustrations are derived from natural events which happened after the death of the philosopher. But notwithstanding these anachronisms, we may regard the account as a true picture of the tenets of the Pythagorean school in the Augustan age, and although perhaps partially modified, it must have contained the substance of the original scheme. Thus considered, it is extremely curious and instructive, for we here find a comprehensive summary of almost all the great causes of change now in activity on the globe, and these adduced in confirmation of a principle of a perpetual and gradual revolution inherent in the nature of our terrestrial system. These doctrines, it is true, are not directly applied to the explanation of geological phenomena, or, in other words, no attempt is made to estimate what may have been in past ages, or what may hereafter be, the aggregate amount of change brought about by such never-ending fluctuations. Had this been the case, we might have been called upon to admire so extraordinary an anticipation with no less interest than astronomers, when they endeavored to define by what means the Samian philosopher came to the knowledge of the Copernican system. Let us now examine the celebrated passages to which we have been adverting. Quote, "Nothing perishes in this world, but things merely vary and change their form. To be born means simply that a thing begins to be something different from what it was before, and dying is ceasing to be the same thing. Yet, although nothing retains long the same image, the sum of the whole remains constant. These general propositions are then confirmed by a series of examples, all derived from natural appearances, except the first, which refers to the Golden Age giving place to the Age of Iron. The illustrations are thus consecutively adduced. 1. Solid land has been converted into sea. 2. Sea has been changed into land. Marine shells lie far distant from the deep, and the anchor has been found on the summit of hills. 3. Valleys have been excavated by running water, and floods have washed down hills into the sea. 4. Marshes have become dry ground. 5. Dry lands have been changed into stagnant pools. 6. During earthquakes, some springs have been closed up, and new ones have broken out. Rivers have deserted their channels and have been reborn elsewhere, as the Erasinus in Greece and Mysis in Asia. 7. The waters of some rivers, formerly sweet, have become bitter, as those of the Anegri in Greece, etc. 8. Islands have become connected with the mainland by the growth of deltas and new deposits, as in the case of Antissa joined to Lesbos, Pharos to Egypt, etc. 9. Peninsulas have been divided from the main land and have become islands, as Leucadia, and, according to tradition, Sicily, the sea having carried away the isthmus. 10. Land has been submerged by earthquakes. The Grecian cities of Helis and Buris, for example, are to be seen under the sea, with their walls inclined. 11. Plains have been upheaved into hills by the confined air seeking vent, as at Trezene in the Peloponnesus. 12. The temperature of some springs varies at different periods. The waters of others are inflammable. 13. There are streams which have a petrifying power and convert the substances which they touch into marble. 14. Extraordinary medicinal and deleterious effects are produced by the water of different lakes and springs. 15. Some rocks and islands, after floating and having been subject to violent movements, have at length become stationary and immovable, as Delos and the Cyanean Isles. 16. Volcanic vents shift their position. There was a time when Etna was not a burning mountain, and the time will come when it will cease to burn. Whether it be that some caverns become closed up by the movements of the earth, and others opened, or whether the fuel is finally exhausted, etc., etc. The various causes of change in the inanimate world having been thus enumerated, the doctrine of equivocal generation is next propounded, as illustrating a corresponding perpetual flux in the animate creation. In the Egyptian and Eastern cosmogonies, and in the Greek version of them, no very definite meaning can, in general, be attached to the term destruction of the world, for sometimes it would seem almost to imply the annihilation of our planetary system, and at others a mere revolution of the surface of the earth. Opinions of Aristotle. From the works now extant of Aristotle, and from the system of Pythagoras, as above exposed, we might certainly infer that these philosophers considered the agents of change now operating in nature as capable of bringing about, in the lapse of ages, a complete revolution, and the Stagirite even considers occasional catastrophes, happening at distant intervals of time, as part of the regular and ordinary course of nature. The deluge of Deucalion, he says, affected Greece only, and principally the part called Hellas, and it arose from great inundations of rivers during a rainy winter. But such extraordinary winters, he says, though after a certain period they return, do not always revisit the same places. Censorinus quotes it as Aristotle's opinion that there were general inundations of the globe, and that they alternated with conflagrations, and that the flood constituted the winter of the great year, or astronomical cycle, while the conflagration, or destruction by fire, is the summer, or period of greatest heat. If this passage, as Lipsius supposes, be an amplification by Censorinus of what is written in the Meteorics, it is a gross misrepresentation of the doctrine of the Stagirite, for the general bearing of his reasoning in that treatise tends clearly in an opposite direction. He refers to many examples of changes now constantly going on, and insists emphatically on the great results which they must produce in the lapse of ages. He instances particular cases of lakes that had dried up, and deserts that had at length become watered by rivers and fertilized. He points to the growth of the Nilotic delta since the time of Homer, to the shallowing of the Palus Metos within 60 years from his own time, and although in the same chapter he says nothing of earthquakes, yet in others of the same treatise he shows himself not unacquainted with their effects. He alludes, for example, to the upheaving of one of the Aeolian islands previous to a volcanic eruption. Quote, "The changes of the earth," he says, "are so slow in comparison to the duration of our lives that they are overlooked, and the migrations of people after great catastrophes and their removal to other regions cause the event to be forgotten." End quote. When we consider the acquaintance displayed by Aristotle in his various works with the destroying and renovating powers of nature, the introductory and concluding passages of the 12th chapter of his Meteorics are certainly very remarkable. In the first sentence he says, quote, "The distribution of land and sea in particular regions does not endure throughout all time, but it becomes sea in those parts where it was land, and again it becomes land where it was sea. And there is reason for thinking that these changes take place according to a certain system and within a certain period." End quote. The concluding observation is as follows, quote, "As time never fails and the universe is eternal, neither the Tanais nor the Nile can have flowed forever. The places where they rise were once dry, and there is a limit to their operations, but there is none to time. So also of all other rivers, they spring up, and they perish, and the sea also continually deserts some lands and invades others. The same tracts, therefore, of the earth are not some always sea and others always continents, but everything changes in the course of time." End quote. It seems, then, that the Greeks had not only derived from preceding nations, but had also, in some slight degree, deduced from their own observations the theory of periodical revolutions in the inorganic world. There is, however, no ground for imagining that they contemplated former changes in the races of animals and plants. Even the fact that marine remains were enclosed in solid rocks, although observed by some, and even made the groundwork of geological speculation, never stimulated the industry or guided the inquiries of naturalists. It is not impossible that the theory of equivocal generation might have engendered some indifference on this subject, and that a belief in the spontaneous production of living beings from the earth or corrupt matter might have caused the organic world to appear so unstable and fluctuating that phenomena indicative of former changes would not awaken intense curiosity. The Egyptians, it is true, had taught, and the Stoics had repeated, that the earth had once given birth to some monstrous animals, which existed no longer. But the prevailing opinion seems to have been that after each great catastrophe the same species of animals were created over again, This tenet is implied in a passage of Seneca, where, speaking of a future deluge, he says, quote, "Every animal shall be generated anew, and man free from guilt shall be given to the earth." End quote. An old Arabian version of the doctrine of the successive revolutions of the globe, translated by Abraham Echelensis, seems to form a singular exception to the general rule, for here we find the idea of different genera and species having been created. The Gerbonites, a sect of astronomers who flourished some centuries before the Christian era, taught as follows, quote, that every period of 36,425 years there were produced a pair of every species of animal, both male and female, from whom animals might be propagated and inhabit this lower world. But when a circulation of the heavenly orbs was completed, which is finished in that space of years, other genera and species of animals are propagated, as also of plants and other things, and the first order is destroyed, and so it goes on forever and ever. End quote. Theory of Strabo. As we learn much of the tenets of the Egyptian and Oriental schools in the writings of the Greeks, so many speculations of the early Greek authors are made known to us in the works of the Augustan and later ages. Strabo, in particular, enters largely in the second book of his Geography into the opinions of Eratosthenes and other Greeks on one of the most difficult problems in geology, viz., by what causes marine shells came to be plentifully buried in the earth at such great elevations and distances from the sea. He notices, amongst others, the explanation of Xanthus the Lydian, who said that the seas had once been more extensive, and that they had afterwards been partially dried up, as in his own time many lakes, rivers, and wells in Asia had failed during a season of drought. Treating this conjecture with merited disregard, Strabo passes on to the hypothesis of Strato, the natural philosopher, who had observed that the quantity of mud brought down by rivers into the Euxine was so great that its bed must be gradually raised, while the rivers still continue to pour in an undiminished quantity of water. He therefore conceived that, originally when the Euxine was an inland sea, its level had by this means become so much elevated that it burst its barrier near Byzantium and formed a communication with the Propontis, and this partial drainage, he supposed, had already converted the left side into marshy ground, and thus, at last, the whole would be choked up with soil. So, it was argued, the Mediterranean had once opened a passage for itself by the columns of Hercules into the Atlantic, and perhaps the abundance of seashells in Africa, near the temple of Jupiter Ammon, might also be the deposit of some former inland sea which had at length forced a passage and escaped. But Strabo rejects this theory as insufficient to account for all the phenomena, and he proposes one of his own, the profoundness of which modern geologists are only beginning to appreciate. Quote, "It is not," he says, "because the lands were covered by seas, were originally at different altitudes, that the waters have risen or subsided or receded from some parts and inundated others. But the reason is that the same land is sometimes raised up and sometimes depressed, and the sea also is simultaneously raised and depressed, so that it either overflows or returns into its own place again. We must therefore ascribe the cause to the ground, either to that ground which is under the sea, or to that which becomes flooded by it, but rather to that which lies beneath the sea, for this is more movable, and, on account of its humidity, can be altered with great celerity. It is proper," he observes in continuation, "to derive our explanations from things which are obvious, and in some measure of daily occurrence, such as deluges, earthquakes, and volcanic eruptions, and sudden swellings of the land beneath the sea. For the last raise up the sea also, and when the same lands subside again, they occasion the sea to be let down. And it is not merely the small, but the large islands also, and not merely the islands, but the continents, which can be lifted up together with the sea, and both large and small tracts may subside, for habitations and cities, like Bure, Bizona, and many others, have been engulfed by earthquakes." End quote. In another place, this learned geographer, in alluding to the tradition that Sicily had been separated by a convulsion from Italy, remarks that at present the land near the sea in those parts was rarely shaken by earthquakes, since there were now open orifices whereby fire and ignited matters and waters escape. But formerly, when the volcanoes of Etna, the Lipari Islands, Ischia, and others were closed up, the imprisoned fire and wind might have produced far more vehement movements. The doctrine, therefore, that volcanoes are safety valves, and that the subterranean convulsions are probably most violent when first the volcanic energy shifts itself to a new quarter, is not modern. We learn from a passage in Strabo that it was a dogma of the Gaulish Druids that the universe was immortal, but destined to survive catastrophes both of fire and water. That this doctrine was communicated to them from the East, with much of their learning, cannot be doubted. Caesar, it will be remembered, says that they made use of Greek letters in arithmetical computations. Pliny. This philosopher had no theoretical opinions of his own concerning changes of the earth's surface, and in this department, as in others, he restricted himself to the task of a compiler, without reasoning on the facts stated by him, or attempting to digest them into regular order. But his enumeration of the new islands which had been formed in the Mediterranean, and of other convulsions, shows that the ancients had not been inattentive observers of the changes which had taken place within the memory of man. Such, then, appears to have been the opinions entertained before the Christian era concerning the past revolutions of our globe. Although no particular investigations had been made for the express purpose of interpreting the monuments of ancient changes, they were too obvious to be entirely disregarded, and the observation of the present course of nature presented too many proofs of alterations continually in progress on the earth to allow philosophers to believe that nature was in a state of rest, or that the surface had remained and would continue to remain unaltered. But they had never compared attentively the results of the destroying and reproductive operations of modern times with those of remote eras, nor had they ever entertained so much as a conjecture concerning the comparative antiquity of the human race, or of living species of animals and plants, with those belonging to former conditions of the organic world. They had studied the movements and positions of the heavenly bodies with laborious industry, and made some progress in investigating the animal, vegetable, and mineral kingdoms. But the ancient history of the globe was to them a sealed book, and, although written in characters of the most striking and imposing kind, they were unconscious even of its existence. End of Chapter 2, Part 2. Recording by Patrick McHaffie, Chicago.
Chapter 3, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 3. Arabian Writers of the 10th Century. Avicenna, Omar, Cosmogony of the Quran, Qazwini, Early Italian writers: Leonardo da Vinci. Fracastoro. Controversy as to the real nature of fossils, attributed to the Mosaic deluge. Policy: Steno, Sylla, Carini, Boyle, Lister, Leibniz. Hooke's theory of elevation by earthquakes, of lost species of animals. Ray. Physico-theological writers: Woodward's diluvial theory, Burnet, Whiston, Vallisneri, Lazzaro Moro, Generelli, Buffon, his theory condemned by the Sorbonne as unorthodox, his declaration. Targioni, Arduino, Michel, Catcott, Raspe, Fouchel, Fortis, Testa, Whitehurst, Paulus, Saussure. Arabian writers. After the decline of the Roman Empire, the cultivation of physical science was first revived with some success by the Saracens, about the middle of the 8th century of our era. The works of the most eminent classic writers were purchased at great expense from the Christians and translated into Arabic, and Al-Mamun, son of the famous Harun al-Rashid, the contemporary of Charlemagne, received with marks of distinction at his court at Baghdad astronomers and men of learning from different countries. This caliph and some of his successors encountered much opposition and jealousy from the doctors of the Mohammedan law, who wished the Moslems to confine their studies to the Koran, dreading the effects of the diffusion of a taste for the physical sciences. Avicenna. Almost all the works of the early Arabian writers are lost. Amongst those of the 10th century, of which fragments are now extant, is a short treatise on the formation and classification of minerals, by Avicenna, a physician, in whose arrangement there is considerable merit. The second chapter, on the cause of mountains, is remarkable. For mountains, he says, are formed some by essential, others by accidental causes. In illustration of the essential, he instances a violent earthquake by which land is elevated and becomes a mountain. Of the accidental, the principle, he says, is excavation by water, whereby cavities are produced and adjoining lands made to stand out and form eminences. Omar, Cosmogony of the Koran. In the same century also Omar, surnamed El-Alem, or the Learned, wrote a work on the retreat of the sea. It appears that on comparing the charts of his own time with those made by the Indian and Persian astronomers 2,000 years before, he had satisfied himself that important changes had taken place since the times of history in the form of the coasts of Asia, and that the extension of the sea had been greater at some former periods. He was confirmed in this opinion by the numerous salt springs and marshes in the interior of Asia, a phenomenon from which Pallas, in more recent times, has drawn the same inference. Von Hoff has suggested, with great probability, that the changes in the level of the Caspian, some of which there is reason to believe have happened within the historical era, and the geological appearances in that district, indicating the desertion by that sea of its ancient bed, had probably led Omar to his theory of a general subsidence. But whatever may have been the proofs relied on, his system was declared contradictory to certain passages in the Koran, and he was called upon publicly to recant his errors, to avoid which persecution he went into voluntary banishment from Samarcand. The cosmological opinions expressed in the Koran are few, and merely introduced incidentally, so that it is not easy to understand how they could have interfered so seriously with free discussion on the former changes of the globe. The prophet declares that the earth was created in 2 days, and the mountains were then placed on it, and during these and 2 additional days the inhabitants of the earth were formed, and in 2 more the 7 heavens. There is no more detail of circumstances, and the deluge, which is also mentioned, is discussed with equal brevity. The waters are represented to have poured out of an oven, a strange fable said to be borrowed from the Persian magi, who represented them as issuing from the oven of an old woman. All men were drowned, save Noah and his family, and then God said, O earth, swallow up thy waters, and thou, O heaven, withhold thy rain. And immediately the waters abated. We may suppose Omar to have represented the desertion of the land by the sea to have been gradual, and that his hypothesis required a greater lapse of ages than was consistent with Moslem orthodoxy, for it is to be inferred from the Koran that man and this planet were created at the same time, and although Muhammad did not limit expressly the antiquity of the human race, yet he gave an implied sanction to the Mosaic chronology by the veneration expressed by him for the Hebrew patriarchs. A manuscript work entitled The Wonders of Nature is preserved in the Royal Library at Paris by an Arabian writer, Mohammed Kazwini, who flourished in the 7th century of the Hegira, or at the close of the 13th century of our era. Besides several curious remarks on aerolites, earthquakes, and the successive changes of position which the land and sea have undergone, we meet with the following beautiful passage, which is given as the narrative of Keats, an allegorical personage. I passed one day by a very ancient and wonderfully populous city, and asked one of its inhabitants how long it had been founded. It is indeed a mighty city, replied he. We know not how long it has existed, and our ancestors were on this subject as ignorant as ourselves. 5 centuries afterwards, as I passed by the same place, I could not perceive the slightest vestige of the city. I demanded of a peasant who was gathering herbs upon its former site how long it had been destroyed. In sooth, a strange question, replied he. The ground here has never been different from what you now behold it. Was there not of old, said I, a splendid city here? Never, answered he, so far as we have seen, and never did our fathers speak to us of any such. On my return there 500 years afterwards, I found the sea in the same place, and on its shores were a party of fishermen, of whom I inquired how long the land had been covered by the waters. Is this a question, said they, for a man like you? This spot has always been what it is now. I again returned 500 years afterwards, and the sea had disappeared. I inquired of a man who stood alone upon the spot how long ago this change had taken place, and he gave me the same answer as I had received before. Lastly, on coming back again after an equal lapse of time, I found there a flourishing city, more populous and more rich in beautiful buildings than the city I had seen the first time. And when I would fain have informed myself concerning its origin, the inhabitants answered me, its rise is lost in remote antiquity. We are ignorant how long it has existed, and our fathers were on this subject as ignorant as ourselves. Early Italian writers. It was not till the earlier part of the 16th century that geological phenomenon began to attract the attention of the Christian nations. At that period, a very animated controversy sprang up in Italy concerning the true nature and origin of marine shells and other organized fossils found abundantly in the strata of the peninsula. The celebrated painter Leonardo da Vinci, who in his youth had planned and executed some navigable canals in the north of Italy, was one of the first who applied sound reasoning to these subjects. The mud of rivers, he said, had covered and penetrated into the interior of fossil shells at a time when these were still at the bottom of the sea near the coast. They tell us that these shells were formed in the hills by the influence of the stars. But I ask, where in the hills are the stars now forming shells of distinct ages and species? And how can the stars explain the origin of gravel, occurring at different heights, and composed of pebbles rounded as if by the motion of running water? Or in what manner can such a cause account for the petrifaction in the same places of various leaves, seaweeds, and marine crabs? The excavations made in 1517 for repairing the city of Verona brought to light a multitude of curious petrifactions, and furnished matter for speculation to different authors, and among the rest to Fracastoro, who declared his opinion that fossil shells had all belonged to living animals, which had formerly lived and multiplied where their exuvia are now found. He exposed the absurdity of having recourse to a certain plastic force, which it was said had power to fashion stones into organic forms, and with no less cogent arguments demonstrated the futility of attributing the situation of the shells in question to the Mosaic deluge, a theory obstinately defended by some. That inundation, he observed, was too transient. It consisted principally of fluviatile waters, and if it had transported shells to great distances, must have strewed them over the surface, not buried them at vast depths in the interior of mountains. His clear exposition of the evidence would have terminated the discussion forever, if the passions of mankind had not been enlisted in the dispute. And even though doubts should for a time have remained in some minds, they would speedily have been removed by the fresh information obtained almost immediately afterwards respecting the structure of fossil remains and of their living analogues. But the clear and philosophical views of Fracastoro were disregarded, and the talent and argumentative powers of the learned were doomed for 3 centuries to be wasted in the discussion of these 2 simple and preliminary questions. First, whether fossil remains had ever belonged to living creatures, and secondly, whether, if this be admitted, all the phenomena could not be explained by the deluge of Noah. It had been the general belief of the Christian world, down to the period now under consideration, that the origin of this planet was not more remote than a few thousand years, and that, since the creation, the deluge was the only great catastrophe by which considerable change had been wrought on the earth's surface. On the other hand, the opinion was scarcely less general that the final dissolution of our system was an event to be looked for at no distant period. The era, it is true, of the expected millennium had passed away, and for 500 years after the fatal hour when the annihilation of the planet had been looked for, the monks remained in undisturbed enjoyment of rich grants of land bequeathed to them by pious donors, who in the preamble of deeds beginning appropinquante mundi termino, appropinquante magno judici dia, left lasting monuments of the popular delusion. But although in the 16th century it had become necessary to interpret certain prophecies respecting the millennium more liberally, and to assign a more distant date to the future conflagration of the world, we find in the speculation of the early geologists perpetual allusion to such an approaching catastrophe, while in all that regarded the antiquity of the earth, no modification whatever of the opinions of the Dark Ages had been effected. Considerable alarm was at first excited when the attempt was made to invalidate, by physical proofs, an article of faith so generally received. But there was sufficient spirit of toleration and candor amongst the Italian ecclesiastics to allow the subject to be canvassed with much freedom. They even entered warmly into the controversy themselves, often favoring different sides of the question. And however much we may deplore the loss of time and labor devoted to the defense of untenable positions, it must be conceded that they displayed far less polemic bitterness than certain writers who followed them beyond the Alps 2 centuries and a half later. End of chapter 3, part 1. Chapter 3, part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles LYELL. Chapter 3, Part 2. Controversy as to the real nature of fossil organic remains. Mattioli, Volapio. The system of scholastic disputations encouraged in the universities of the Middle Ages had unfortunately trained men to habits of indefinite argumentation, and they often preferred absurd and extravagant propositions because greater skill was required to maintain them, the end and object of these intellectual combats being victory and not truth. No theory could be so far-fetched or fantastical as not to attract some followers, provided it fell in with popular notions, and as cosmogonists were not at all restricted in building their systems to the agency of known causes, the opponents of Frascatoro met his arguments by feigning imaginary causes which differed from each other rather in name than in substance. Andrea Mattioli, for instance, an eminent botanist, the illustrator of Dioscorides, embraced the notion of Agricola, a skilful German miner, that a certain materials pinguis, or fatty matter, set into fermentation by heat, gave birth to fossil organic shapes. Yet Mattioli had come to the conclusion, from his own observations, that porous bodies, such as bones and shells, might be converted into stone, as being permeable to what he termed the lapidifying juice. In like manner, Volapio of Padua conceived that petrified shells were generated by fermentation in the spots where they are found, or that they had in some cases acquired their form from the tumultuous movements of terrestrial exhalations. Although celebrated as a professor of anatomy, he taught that certain tusks of elephants dug up in his time in Apulia were mere earthly concretions, and consistently with these principles, he even went so far as to consider it probable that the vases of Monte Testaceo at Rome were natural impressions stamped in the soil. In the same spirit, Mercati, who published in 1574 faithful figures of the fossil shells preserved by Pope Sixtus V in the Museum of the Vatican, expressed an opinion that they were mere stones which had assumed their peculiar configuration from the influence of the heavenly bodies. And Olivi of Cremona, who described the fossil remains of a rich museum at Verona, was satisfied with considering them as mere sports of nature. Some of the fanciful notions of those times were deemed less unreasonable, as being somewhat in harmony with the Aristotelian theory of spontaneous generation, then taught in all the schools. For men who had been taught in early youth that a large proportion of living animals and plants were formed from the fortuitous concourse of atoms, or had sprung from the corruption of organic matter, might easily persuade themselves that organic shapes, often imperfectly preserved in the interior of solid rock, owed their existence to causes equally obscure and mysterious. Cardano, 1552. But there were not wanting some who, during the progress of this century, expressed more sound and sober opinions. The title of a work of Cardano's, published in 1552, De Subtilitate, corresponding to what would now be called transcendental philosophy, would lead us to expect, in the chapter on minerals, many far-fetched theories characteristic of that age, but when treating of petrified shells, he decided that they clearly indicated the former sojourn of the sea upon the mountains. Cesalpino Majoli, 1597. Cesalpino, a celebrated botanist, conceived that fossil shells had been left on the land by the retiring sea, and had concreted into stone during the consolidation of the soil, and in the following year, 1597, Simeon Majoli went still farther, and, coinciding for the most part with the views of Cesalpino, suggested that the shells and submarine matter of the Varanese and other districts might have been cast up upon the land by volcanic explosions, like those which gave rise in 1538 to Monte Nuovo, near Puzzoli. This hint seems to have been the first imperfect attempt to connect the position of fossil shells with the agency of volcanoes, a system afterwards more fully developed by Hooke, Lazaro Moro, Hutton, and other writers. 2 years afterwards, Imperati advocated the animal origin of fossilized shells, yet admitted that stones could vegetate by force of an internal principle, and as evidence of this he referred to the teeth of fish and spines of Achini found petrified. Palissy, 1580. Palissy, a French writer on the origin of springs from rainwater and of other scientific works, undertook in 1580 to combat the notions of many of his contemporaries in Italy, that petrified shells had all been deposited by the universal deluge. He was the first, said Fontenelle, when in the French Academy he pronounced his eulogy nearly a century and a half later, who dared assert, in Paris, that fossil remains of testacea and fish had once belonged to marine animals. Fabio Colonna. To enumerate the multitude of Italian writers who advanced various hypotheses, all equally fantastical, in the early part of the 17th century, would be unprofitably tedious. But Fabio Colonna deserves to be distinguished, for although he gave way to the dogma that all fossil remains were to be referred to the deluge of Noah, he resisted the absurd theory of Stelluti, who taught that fossil wood and ammonites were mere clay, altered into such forms by sulphureous waters and subterranean heat, and he pointed out the different states of shells buried in the strata, distinguishing between first the mere mold or impression, second the cast or nucleus, and thirdly the remains of the shell itself. He had also the merit of being the first to point out that some of the fossils had belonged to marine and some to terrestrial testacea. Steno, 1669. But the most remarkable work of that period was published by Steno, a Dane, once professor of anatomy at Padua, and who afterwards resided many years at the court of the Grand Duke of Tuscany. His treatise bears the quaint title of De Solido intra solidum naturaliter contento, 1669, by which the author intended to express on gems, crystals, and organic petrifactions enclosed within solid rocks. This work attests the priority of the Italian school in geological research, exemplifying at the same time the powerful obstacles opposed in that age to the general reception of enlarged views in the science. It was still a favorite dogma that the fossil remains of shells and marine creatures were not of animal origin, an opinion adhered to by many from their extreme reluctance to believe that the earth could have been inhabited by living beings before a great part of the existing mountains were formed. In reference to this controversy, Steno had dissected a shark recently taken from the Mediterranean, and had demonstrated that its teeth and bones were identical with many fossils found in Tuscany. He had also compared the shells discovered in the Italian strata with living species, pointed out their resemblance, and traced the various gradations from shells merely calcined, or which had only lost their animal gluten, to those petrifactions in which there was a perfect substitution of stony matter. In his division of mineral masses, he insisted on the secondary origin of those deposits in which the spoils of animals or fragments of older rocks were enclosed. He distinguished between marine formations and those of a fluviatile character, the last containing reeds, grasses, or the trunks and branches of trees. He argued in favor of the original horizontality of sedimentary deposits, attributing their present inclined and vertical position sometimes to the escape of subterranean vapors heaving the crust of the earth from below upwards, and sometimes to the falling in of masses overlying subterranean cavities. He declared that he had obtained proof that Tuscany must successively have acquired 6 distinct configurations, having been twice covered by water, twice laid dry with a level, and twice with an irregular and uneven surface. He displayed great anxiety to reconcile his new views with Scripture, for which purpose he pointed to certain rocks as having been formed before the existence of animals and plants, selecting, unfortunately, as examples, certain formations of limestone and sandstone in his own country, now known to contain, though sparingly, the remains of animals and plants, strata which do not even rank as the oldest part of our secondary series. Steno suggested that Moses, when speaking of the loftiest mountains as having been covered by the deluge, meant merely the loftiest of the hills then existing, which may not have been very high. The diluvian waters, he supposed, may have issued from the interior of the earth, into which they had retired, when in the beginning the land was separated from the sea. These and other hypotheses on the same subject are not calculated to enhance the value of the treatise, and could scarcely fail to detract from the authority of those opinions which were sound and legitimate deductions from fact and observation. They have served, nevertheless, as the germs of many popular theories of later times, and in an expanded form have been put forth as original inventions by some of our contemporaries. Sylla, 1670. Sylla, a Sicilian painter, published in 1670 a treatise in Latin on the fossils of Calabria, illustrated by good engravings. This work proves the continued ascendancy of dogmas often refuted, for we find the wit and eloquence of the author chiefly directed against the obstinate incredulity of naturalists as to the organic nature of fossil shells. Like many eminent naturalists of his day, Sylla gave way to the popular persuasion that all fossil shells were the effects and proofs of the Mosaic deluge. It may be doubted whether he was perfectly sincere, and some of his contemporaries who took the same course were certainly not so. But so eager were they to root out what they justly considered an absurd prejudice respecting the nature of organized fossils, that they seem to have been ready to make any concessions in order to establish this preliminary point. Such a compromising policy was short-sighted, since it was to little purpose that the nature of the documents should at length be correctly understood, if men were to be prevented from deducing fair conclusions from them. Diluvial theory. The theologians who now entered the field in Italy, Germany, France, and England were innumerable, and henceforward they who refused to subscribe to the position that all marine organic remains were proofs of the Mosaic deluge were exposed to the imputation of disbelieving the whole of the sacred writings. Scarcely any step had been made in approximating to sound theories since the time of Froscatoro, more than 100 years having been lost, in writing down the dogma that organized fossils were mere sports of nature. An additional period of a century and a half was now destined to be consumed in exploding the hypothesis that organized fossils had all been buried in the solid strata by Noah's flood. Never did a theoretical fallacy in any branch of science interfere more seriously with accurate observation and the systematic classification of facts. In recent times, we may attribute our rapid progress chiefly to the careful determination of the order of succession in mineral masses by means of their different organic contents and their regular superposition. But the old diluvialists were induced by their system to confound all the groups of strata together instead of discriminating, to refer all appearances to one cause and to one brief period, not to a variety of causes acting throughout a long succession of epochs. They saw the phenomena only as they desired to see them, sometimes misrepresenting facts, and at other times deducing false conclusions from correct data. Under the influences of such prejudices, 3 centuries were of as little avail as a few years in our own times, when we are no longer required to propel the vessel against the force of an adverse current. It may be well, therefore, to forewarn the reader that in tracing the history of geology from the close of the 17th to the end of the 18th century, he must expect to be occupied with accounts of the retardation as well as of the advance of the science. It will be necessary to point out the frequent revival of exploded errors and the relapse from sound to the most absurd opinions, and to dwell on futile reasoning and visionary hypothesis, because some of the most extravagant systems were invented or controverted by men of acknowledged talent. In short, a sketch of the progress of geology is the history of a constant and violent struggle of new opinions against doctrines sanctioned by the implicit faith of many generations, and supposed to rest on scriptural authority. The inquiry, therefore, although highly interesting to one who studies the philosophy of the human mind, is too often barren of instruction to him who searches for truths in physical science. Querini, 1676. Querini, in 1676, contended, in opposition to Sylla, that the diluvian waters could not have conveyed heavy bodies to the summit of mountains, since the agitation of the sea never, as Boyle had demonstrated, extended to great depths, and still less could the testacea, as some pretended, have lived in these diluvian waters, for the duration of the flood was brief, and the heavy rains must have destroyed the saltness of the sea. He was the first writer who ventured to maintain that the universality of the Mosaic cataclysm ought not to be insisted upon. As to the nature of petrified shells, he conceived that as earthly particles united in the sea to form the shells of mollusca, the same crystallizing process might be effected on the land, and that in the latter case the germs of the animals might have been disseminated through the substance of the rocks, and afterwards developed by virtue of humidity. Visionary as was this doctrine, it gained many proselytes, even amongst the more sober reasoners of Italy and Germany, for it conceded that the position of fossil bodies could not be accounted for by the diluvial theory. Plot, Lister, 1678. In the meantime, the doctrine that fossil shells had never belonged to real animals maintained its ground in England, where the agitation of the question began at a much later period. Dr. Plot, in his Natural History of Oxfordshire, 1677, attributed to a plastic virtue latent in the earth the origin of fossil shells and fishes, and Lister, to his accurate account of British shells in 1678, added the fossil species under the appellation of turbinated and bivalve stones. Either, said he, these were terrigenous, or if otherwise, the animals they so exactly represent have become extinct. This writer appears to have been the first who was aware of the continuity over large districts of the principal groups of strata in the British series, and who proposed the construction of regular geological maps. Leibniz, 1680. The great mathematician Leibniz published his Protégea in 1680. He imagined this planet to have been originally a burning luminous mass, which ever since its creation has been undergoing refrigeration. When the outer crust had cooled down sufficiently to allow the vapors to be condensed, they fell and formed a universal ocean covering the loftiest mountains and investing the whole globe. The crust, as it consolidated from a state of fusion, assumed a vesicular and cavernous structure, and being rent in some places, allowed the water to rush into the subterranean hollows, whereby the level of the primeval ocean was lowered. The breaking in of these vast caverns is supposed to have given rise to the dislocated and deranged position of the strata which Steno had described, and the same disruptions communicated violent movements to the incumbent waters, whence great inundations ensued. The waters, after they had been thus agitated, deposited their sedimentary matter during intervals of quiescence, and hence the various stony and earthy strata. We may recognize, therefore, says Leibnitz, a double origin of primitive masses, the one by refrigeration from igneous fusion, the other by concretion from aqueous solution. By the repetition of similar causes, the disruption of the crust and consequent floods, alternations of new strata were produced, until at length these causes were reduced to a condition of quiescent equilibrium, and a more permanent state of things was established. End of chapter 3, part 2. Chapter 3, part 3 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 3, Part 3. Hooke, 1688. The posthumous works of Robert Hooke, M.D., well known as a great mathematician and natural philosopher, appeared in 1705, containing a discourse of earthquakes, which, we are informed by his editor, was written in 1668, but revised at subsequent periods. Hooke frequently refers to the best Italian and English authors who wrote before his time on geological subjects, but there are no passages in his works implying that he participated in enlarged views of Steno and Lister, or of his contemporary Woodward, in regard to the geological extent of certain groups of strata. His treatise, however, is the most philosophical production of that age, in regard to the causes of former changes in the organic and inorganic kingdoms of nature. However trivial a thing, he says, a rotten shell may appear to some, yet these monuments of nature are more certain tokens of antiquity than coins or medals, since the best of those may be counterfeited or made by art and design, as may also books, manuscripts, and inscriptions, as all the learned are now sufficiently satisfied has often been actually practised, etc. And though it must be granted that it is very difficult to read them, the records of nature, and to raise a chronology out of them, and to state the intervals of the time wherein such or such catastrophes and mutations have happened, yet it is not impossible. Respecting the extinction of species, Hooke was aware that the fossil ammonites, nautili, and many other shells and fossil skeletons found in England were of different species from any then known, but he doubted whether the species had become extinct, observing that the knowledge of naturalists of all the marine species, especially those inhabiting the deep sea, was very deficient. In some parts of his writing, however, he leans to the opinion that species had been lost, and in speculating on this subject, he even suggests that there might be some connection between the disappearance of certain kinds of animals and plants and the changes wrought by earthquakes in former ages. Some species, he observes with great sagacity, are peculiar to certain places and not to be found elsewhere. If, then, such a place had been swallowed up, it is not improbable but that those animate beings may have been destroyed with it, and this may be true both of aerial and aquatic animals. For those animated bodies, whether vegetables or animals, which were naturally nourished or refreshed by the air, would be destroyed by the water, etc. Turtles, he adds, and such large ammonites as are found in Portland, seem to have been the productions of hotter countries, and it is necessary to suppose that England once lay under the sea within the torrid zone. To explain this and similar phenomena, he indulges in a variety of speculations concerning changes in the position of the axis of the earth's rotation, a shifting of the earth's center of gravity, analogous to the revolutions of the magnetic pole, etc. None of these conjectures, however, are proposed dogmatically, but rather in the hope of promoting fresh inquiries and experiments. In opposition to the prejudices of his age, we find him arguing against the idea that nature had formed fossil bodies for no other end than to play the mimic in the mineral kingdom, maintaining that figured stones were really the several bodies they represent, or the mouldings of them petrified, and not, as some have imagined, a lusus natura, sporting herself in the needless formation of useless beings. It was objected to Hooke that his doctrine of the extinction of species derogated from the wisdom and power of the omnipotent Creator, but he answered that, as individuals die, there may be some termination to the duration of a species, and his opinions, he declared, were not repugnant to Holy Writ, for the Scriptures taught that our system was degenerating and tending to its final dissolution, and as, when that shall happen, all the species will be lost, why not some at one time and some at another? But his principal object was to account for the manner in which shells had been conveyed into the higher parts of the Alps, Apennines, and Pyrenean hills, and the interior of continents in general. These and other appearances, he said, might have been brought about by earthquakes, which have turned plains into mountains, and mountains into plains, seas into land, and land into seas, made rivers where there were none before, and swallowed up others that formerly were, etc., etc., and which, since the creation of the world, have wrought many great changes on the superficial parts of the earth, and have been the instruments of placing shells, bones, plants, fishes, and the like, in those places where, with much astonishment, we find them. This doctrine, it is true, had been laid down in terms almost equally explicit by Strabo, to explain the occurrence of fossil shells in the interior of continents, and to that geographer and other writers of antiquity Hooke frequently refers. But the revival and development of the system was an important step in the progress of modern science. Hooke enumerated all the examples known to him of subterranean disturbance, from the sad catastrophe of Sodom and Gomorrah down to the Chilean earthquake of 1646, the elevating of the bottom of the sea, the sinking and submersion of the land, and most of the inequalities of the earth's surface might, he said, be accounted for by the agency of these subterranean causes. He mentions that the coast near Naples was raised during the eruption of Monte Nuovo, and that in 1591 land rose in the island of St. Michael during an eruption, and although it would be more difficult, he says, to prove, he does not doubt but that there had been as many earthquakes in the parts of the earth under the ocean as in the parts of the dry land. in confirmation of which he mentions the immeasurable depth of the sea near some volcanoes. To attest the extent of simultaneous subterranean movements, he refers to an earthquake in the West Indies in the year 1690, where the space of earth raised or struck upwards by the shock exceeded, he affirms, the length of the Alps and Pyrenees. Hooke's diluvial theory. As Hooke declared the favorite hypothesis of the day, that marine fossil bodies were to be referred to Noah's flood, to be wholly untenable, he appears to have felt himself called upon to substitute a diluvial theory of his own, and thus he became involved in countless difficulties and contradictions. During the great catastrophe, he said, there might have been a changing of that part which was before dry land into sea by sinking, and of that which was sea into dry land by raising, and marine bodies might have been buried in sediment beneath the ocean in the interval between the creation and the deluge. Then follows a disquisition on the separation of the land from the waters mentioned in Genesis, during which operation some places of the shell of the earth were forced outwards, and others pressed downwards or inwards, etc. His diluvial hypothesis very much resembled that of Steno, and was entirely opposed to the fundamental principles professed by him, that he would explain the former changes of the earth in a more natural manner than others had done. When, in despite of this declaration, he required a former crisis of nature, and taught that earthquakes had become debilitated, and that the Alps, Andes, and other chains had been lifted up in a few months, he was compelled to assume so rapid a rate of change that his machinery appeared scarcely less extravagant than that of his most fanciful predecessors. For this reason, perhaps, his whole theory of earthquakes was met with undeserved neglect. Ray, 1692. One of his contemporaries, the celebrated naturalist Ray, participated in the same desire to explain geological phenomena, by reference to causes less hypothetical than those usually resorted to. In his essay on Chaos and Creation, he proposed a system agreeing in its outline and in many of its details with that of Hooke, but his knowledge of natural history enabled him to elucidate the subject with various original observations. Earthquakes, he suggested, might have been the second causes employed at the creation, in separating the land from the waters, and in gathering the waters together into one place. He mentions, like Hooke, the earthquake of 1646, which had violently shaken the Andes for some hundreds of leagues, and made many alterations therein. In assigning a cause for the general deluge, he preferred a change in the earth's center of gravity to the introduction of earthquakes. Some unknown cause, he said, might have forced the subterranean waters outwards, as was perhaps indicated by breaking up of the fountains of the great deep. Ray was one of the first of our writers who enlarged upon the effects of running water upon the land, and of the encroachment of the sea upon the shores. So important did he consider the agency of these causes, that he saw in them an indication of the tendency of our system to its final dissolution. And he wondered why the earth did not proceed more rapidly towards a general submersion beneath the sea, when so much matter was carried down by rivers, or undermined in the sea cliffs. We perceive clearly from his writings that the gradual decline of our system and its future consummation by fire was held to be as necessary an article of faith by the orthodox as was the recent origin of our planet. His discourses, like those of Hooke, are highly interesting, as attesting the familiar association in the minds of philosophers in the age of Newton of questions in physics and divinity. Ray gave an unequivocal proof of the sincerity of his mind by sacrificing his preferment in the church rather than take an oath against the Covenanters, which he could not reconcile with his conscience. His reputation, however, in the scientific world placed him high above the temptation of courting popularity by pandering to the physico-theological taste of his age. It is, therefore, curious to meet with so many citations from the Christian fathers and prophets in his essays on physical science, to find him in one page proceeding by the strict rules of induction to explain the former changes of the globe, and in the next gravely entertaining the question whether the sun and stars and the whole heavens shall be annihilated together with the earth at the era of the grand conflagration. Woodward, 1695. Among the contemporaries of Hooke and Ray, Woodward, a professor of medicine, had acquired the most extensive information respecting the geological structure of the crust of the earth. He had examined many parts of the British strata with minute attention, and his systematic collection of specimens, bequeathed to the University of Cambridge and still preserved there as arranged by him, shows how far he had advanced in ascertaining the order of superposition. From the great number of facts collected by him, we might have expected his theoretical views to be more sound and enlarged than those of his contemporaries, but in his anxiety to accommodate all observed phenomena to the scriptural account of the creation and deluge, he arrived at most erroneous results. He conceived the whole terrestrial globe to have been taken to pieces and dissolved at the flood, and the strata to have settled down from this promiscuous mass as any earthly sediment from a fluid. In corroboration of these views, he insisted upon the fact that marine bodies are lodged in the strata according to the order of their gravity, the heavier shells in stone, the lighter in chalk, and so of the rest. Ray immediately exposed the unfounded nature of this assertion, remarking truly that fossil bodies are often mingled, heavy with light, in the same stratum. And he even went so far as to say that Woodward must have invented the phenomena for the sake of confirming his bold and strange hypothesis, a strong expression from the pen of a contemporary. Burnet, 1690. At the same time, Burnet published his Theory of the Earth. The title is most characteristic of the age, The Sacred Theory of the Earth, containing an account of the original of the earth, and of all the general changes which it hath already undergone, or is to undergo, till the consummation of all things. Even Milton had scarcely ventured in his poem to indulge his imagination so freely in painting scenes of the creation and deluge, paradise and chaos. He explained why the primeval earth enjoyed a perpetual spring before the flood, showed how the crust of the globe was fissured by the sun's rays so that it burst, and thus the diluvial waters were let loose from a supposed central abyss. Not satisfied with these themes, he derived from the books of the inspired writers, and even from heathen authorities, prophetic views of the future revolutions of the globe, gave a most terrific description of the general conflagration, and proved that a new heaven and a new earth will rise out of a second chaos, after which will follow the blessed millennium. The reader should be informed that, according to the opinion of many respectable writers of that age, there was good scriptural ground for presuming that the garden bestowed upon our first parents was not on the earth itself, but above the clouds, in the middle region between our planet and the moon. Burnet approaches with becoming gravity the discussion of so important a topic. He was willing to concede that the geographical position of paradise was not in Mesopotamia, yet he maintained that it was upon the earth, and in the southern hemisphere, near the equinoctial line. Butler selected this conceit as a fair mark for his satire, when amongst the numerous accomplishments of Hudibras he says, "He knew the seat of paradise, could tell in what degree it lies, and as he was disposed, could prove it below the moon, or else above it. Yet the same monarch, who is said never to have slept without Butler's poem under his pillow, was so great an admirer and patron of Burnet's book that he ordered it to be translated from the Latin into English. The style of the Sacred Theory was eloquent, and the book displayed powers of invention of no ordinary stamp. It was, in fact, a fine historical romance, as Buffon afterwards declared, but it was treated as a work of profound science in the time of its author, and was panegyrized by Addison in a Latin ode, while Steele praised it in The Spectator. Whiston, 1696. Another production of the same school, and equally characteristic of the time, was that of Whiston, entitled A New Theory of the Earth, wherein the creation of the world in 6 days, the universal deluge, and the general conflagration, as laid down in the Holy Scriptures, are shown to be perfectly agreeable to reason and philosophy. He was at first a follower of Burnet, but his faith in the infallibility of that writer was shaken by the declared opinion of Newton, that there was every presumption in astronomy against any former change in the inclination of the earth's axis. This was a leading dogma in Burnet's system, though not original, for it was borrowed from an Italian, Alessandro degli Alessandri, who had suggested it in the beginning of the 15th century to account for the former occupation of the present continents by the sea. Laplace has since strengthened the arguments of Newton against the probability of any former revolution of this kind. The remarkable comet of 1680 was fresh in the memory of every one when Whiston first began his cosmological studies, and the principal novelty of his speculations consisted in attributing the deluge to the near approach to the earth of one of these erratic bodies. Having ascribed an increase of the waters to this source, he adopted Woodward's theory, supposing all stratified deposits to have resulted from the chaotic sediment of the flood. Whiston was one of the first who ventured to propose that the text of Genesis should be interpreted differently from its ordinary acceptation, so that the doctrine of the earth having existed long previous to the creation of man might no longer be regarded as unorthodox. He had the art to throw an air of plausibility over the most improbable parts of his theory, and seemed to be proceeding in the most sober manner, and by the aid of mathematical demonstration, to the establishment of his various propositions. Locke pronounced a panegyric on his theory, commending him for having explained so many wonderful and before inexplicable things. His book, as well as Burnet's, was attacked and refuted by Keele. Like all who introduced purely hypothetical causes to account for natural phenomena, Whiston retarded the progress of truth, diverting men from the investigation of the laws of sublunary nature, and inducing them to waste time in speculations on the power of comets to drag the waters of the ocean over the land, on the condensation of the vapors of their tails into water, and other matters equally edifying. Hutchinson, 1724. John Hutchinson, who had been employed by Woodward in making his collection of fossils, published afterwards, in 1724, the first part of his Moses's Principia, wherein he ridiculed Woodward's hypothesis. He and his numerous followers were accustomed to declaim loudly against human learning, and they maintained that the Hebrew Scriptures, when rightly translated, comprised a perfect system of natural philosophy, for which reason they objected to the Newtonian theory of gravitation. Celsius. Andrea Celsius, the Swedish astronomer, published about this time his remarks on the gradual diminution and sinking of the waters in the Baltic, to which I have occasion to advert more particularly in the sequel. Chapter 29. Schuster, 1708. In Germany, in the meantime, Schutzer published his Complaint and Vindication of the Fishes, 1708, Piscium Querele et Vindice, a work of zoological merit, in which he gave some good plates and descriptions of fossil fish. Among other conclusions, he labored to prove that the earth had been remodeled at the deluge. Pluche, also in 1732, wrote to the same effect, while Holbach, in 1753, after considering the various attempts to refer all the ancient formations to the flood of Noah, exposed the inadequacy of this cause. Italian geologists, Vallisneri. I return with pleasure to the geologists of Italy, who preceded, as has already been shown, the naturalists of other countries in their investigations into the ancient history of the earth, and who still maintained a decided preeminence. They refuted and ridiculed the physico-theological systems of Burnet, Whiston, and Woodward, while Vallisneri, in his comments on the Woodwardian theory, remarked how much the interests of religion, as well as those of sound philosophy, had suffered by perpetually mixing up the sacred writings with questions in physical science. The works of this author were rich in original observations. He attempted the first general sketch of the marine deposits of Italy, their geographical extent, and most characteristic organic remains. In his treatise on the origin of springs, he explained their dependence on the order and often on the dislocations of the strata, and reasoned philosophically against the opinions of those who regarded the disordered state of the earth's crust as exhibiting signs of the wrath of God for the sins of man. He found himself under the necessity of contending in his preliminary chapter against St. Jerome and 4 other principal interpreters of Scripture, besides several professors of divinity, that springs did not flow by subterranean siphons and cavities from the sea upwards, losing their saltiness in the passage, for this theory had been made to rest on the infallible testimony of Holy Writ. Although reluctant to generalize on the rich materials accumulated in his travels, Vallisneri had been so much struck with the remarkable continuity of the more recent marine strata from one end of Italy to the other, that he came to the conclusion that the ocean formerly extended over the whole earth, and after abiding there for a long time had gradually subsided. This opinion, however untenable, was a great step beyond Woodward's diluvial hypothesis, against which Vallisneri, and after him all the Tuscan geologists, uniformly contended, while it was warmly supported by the members of the Institute of Bologna. Among others of that day, Spada, a priest of Grazzana in 1737, wrote to prove that the petrified marine bodies near Verona were not diluvian. Matani drew a similar inference from the shells of Volterra and other places, while Constantini, on the other hand, whose observations on the valley of the Brenta and other districts were not without value, undertook to vindicate the truth of the deluge, as also to prove that Italy had been peopled by the descendants of Japhet. End of chapter 3, section 3. Chapter 3, Part 4 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 3, Part 4. Moro, 1740. Lazaro Moro, in his work, published in 1740, on the marine bodies which are found in the mountains, attempted to apply the theory of earthquakes, as expounded by Strabo, Pliny, and other ancient authors with whom he was familiar, to the geological phenomena described by Vallisneri. his attention was awakened to the elevating power of subterranean forces by a remarkable phenomenon which happened in his own time, and which had also been noticed by Vallisneri in his letters. A new island rose in 1707 from deep waters in the Gulf of Santorin, in the Mediterranean, during continued shocks of an earthquake, and increasing rapidly in size, grew in less than a month to be half a mile in circumference, and about 25 feet above high water mark. It was soon afterwards covered by volcanic ejections, but when first examined, it was found to be a white rock, bearing on its surface living oysters and crustacea. In order to ridicule the various theories then in vogue, Morrow ingeniously supposes the arrival on this new island of a party of naturalists ignorant of its recent origin. One immediately points to the marine shells as proofs of the universal deluge. Another argues that they demonstrate the former residence of the sea upon the mountains. The third dismisses them as mere sports of nature, while a fourth affirms that they were born and nourished within the rock in ancient caverns, into which salt water had been raised in the shape of vapor by the action of subterranean heat. Morrow pointed with great judgment to the faults and dislocations of the strata described by Vallisneri in the Alps and other chains, in confirmation of his doctrine that the continents had been heaved up by subterranean movements. He objected on solid grounds to the hypothesis of Burnet and of Woodward, yet he ventured so far to disregard the protest of Vallisneri as to undertake the adaptation of every part of his own system to the Mosaic account of the creation. On the third day, he said, the globe was everywhere covered to the same depth by fresh water, and when it pleased the Supreme Being that the dry land should appear, volcanic explosions broke up the smooth and regular surface of the earth composed of primary rocks. These rose in mountain masses above the waves and allowed melted metals and salts to ascend through fissures. The sea gradually acquired its saltness from volcanic exhalations, and while it became more circumscribed in area, increased in depth. Sand and ashes ejected by volcanoes were regularly disposed along the bottom of the ocean, and formed the secondary strata, which in their turn were lifted up by earthquakes. We need not follow this author in tracing the progress of the creation of vegetables and animals on the other days of creation, but upon the whole it may be remarked that few of the old cosmological theories had been conceived with so little violation of known analogies. Generelli's Illustrations of Morrow, 1749. The style of Morrow was extremely prolix, and like Hutton, who at a later period advanced many of the same views, he stood in need of an illustrator. The Scotch geologist was hardly more fortunate in the advocacy of Playfair than was Morrow in numbering amongst his admirers Cirillo Generelli, who, 9 years afterwards, delivered at a sitting of academicians at Cremona a spirited exposition of his theory. This learned Carmelitan friar does not pretend to have been an original observer, but he had studied sufficiently to enable him to confirm the opinions of Morrow by arguments from other writers, and his selection of the doctrines then best established is so judicious that a brief abstract of them cannot fail to be acceptable as illustrating the state of geology in Europe and in Italy in particular before the middle of the last century. The bowels of the earth, says he, have carefully preserved the memorials of past events, and this truth the marine productions so frequent in the hills attest. From the reflections of Lazaro Morrow, we may assure ourselves that these are the effects of earthquakes in past times, which have changed vast spaces of sea into terra firma, and inhabited lands into seas. In this, more than in any other department of physics, are observations and experiments indispensable, and we must diligently consider facts. The land is known, wherever we make excavations, to be composed of different strata or soils placed one above the other, some of sand, some of rock, some of chalk, others of marl, coal, pumice, gypsum, lime, and the rest. These ingredients are sometimes pure and sometimes confusedly intermixed. Within are often imprisoned different marine fishes, like dried mummies, and more frequently shells, crustacea, corals, plants, etc., not only in Italy, but in France, Germany, England, Africa, Asia, and America. Sometimes in the lowest, sometimes in the loftiest beds of the earth, some upon the mountains, some in deep mines, others near the sea, and others hundreds of miles distant from it. Woodward conjectured that these marine bodies might be found everywhere, but there are rocks in which none of them occur, as is sufficiently attested by Vallisneri and Marsilli. The remains of fossil animals consist chiefly of their more solid parts, and the most rocky strata must have been soft when such exuvia were enclosed in them. Vegetable productions are found in different states of maturity, indicating that they were embedded in different seasons. Elephants, elks, and other terrestrial quadrupeds have been found in England and elsewhere in superficial strata, never covered by the sea. Alternations are rare, yet not without example, of marine strata, with those which contain marshy and terrestrial productions. Marine animals are arranged in the subterraneous beds with admirable order, in distinct groups, oysters here, dentalia or corals there, etc., as now, according to Marsilli, on the shores of the Adriatic. We must abandon the doctrine, once so popular, which denies that organized fossils were derived from living beings, and we cannot account for their present position by the ancient theory of Strabo, nor by that of Leibnitz, nor by the universal deluge, as explained by Woodward and others. Nor is it reasonable to call the deity capriciously upon the stage, and to make him work miracles for the sake of confirming our preconceived hypothesis. I hold in utter abomination, most learned academicians, those systems which are built with their foundations in the air, and cannot be propped up without a miracle. And I undertake, with the assistance of Morrow, to explain to you how these marine animals were transported into the mountains by natural causes. A brief abstract then follows of Morrow's theory, by which, says Generelli, we may explain all the phenomena, as Vallisneri so ardently desired, without violence, without fictions, without hypothesis, without miracles. The Carmelitan then proceeds to struggle against an obvious objection to Morrow's system, considered as a method of explaining the revolutions of the earth naturally. If earthquakes have been the agents of such mighty changes, how does it happen that their effects, since the times of history, have been so inconsiderable? This same difficulty had, as we have seen, presented itself to Hooke half a century before, and forced him to resort to a former crisis of nature. But Generelli defended his position by showing how numerous were the accounts of eruptions and earthquakes, of new islands, and of elevations and subsidences of land, and yet how much greater a number of like events must have been unattested and unrecorded during the last 6,000 years. He also appealed to Vallisneri as an authority to prove that the mineral masses containing shells bore, upon the whole, but a small proportion to those rocks which were destitute of organic remains, and the latter, says the learned monk, might have been created as they now exist, in the beginning. Generelli then describes the continual waste of mountains and continents by the action of rivers and torrents, and concludes with these eloquent and original observations. Is it possible that this waste should have continued for 6,000 and perhaps a greater number of years, and that the mountains should remain so great, unless their ruins have been repaired? Is it credible that the author of nature should have founded the world upon such laws as that the dry land should forever be growing smaller and at last become wholly submerged beneath the waters? Is it credible that amid so many created things the mountains alone should daily diminish in number and bulk, without there being any repair of their losses? This would be contrary to that order of Providence which is seen to reign in all other things in the universe. Wherefore, I deem it just to conclude that the same cause which, in the beginning of time, raised mountains from the abyss, has down to the present day continued to produce others, in order to restore from time to time the losses of all such as sink down in different places, or are rent asunder, or in other ways suffer disintegration. If this be admitted, we can easily understand why there should now be found upon many mountains so great a number of crustacea and other marine animals. In the above extract, I have not merely enumerated the opinions and facts which are confirmed by recent observation, suppressing all that has since proved to be erroneous, but have given a faithful abridgment of the entire treatise, with the omission only of Morrow's hypothesis, which Generelli adopted, with all its faults and excellences. The reader will therefore remark that although this admirable essay embraces so large a portion of the principal objects of geological research, it makes no allusion to the extinction of certain classes of animals, and it is evident that no opinions on this head had at that time gained a firm footing in Italy. That Lister and other English naturalists should long before have declared in favor of the loss of species, while Sylla and most of his countrymen hesitated, was perhaps natural, since the Italian museums were filled with fossil shells belonging to species of which a great portion did actually exist in the Mediterranean, whereas the English collectors could obtain no recent species from such of their own strata as were then explored. The weakest point in Morrow's system consisted in deriving all the stratified rocks from volcanic ejections, an absurdity which his opponents took care to expose, especially Vito Amici. Morrow seems to have been misled by his anxious desire to represent the formation of secondary rocks as having occupied an extremely short period, while at the same time he wished to employ known agents in nature. To imagine torrents, rivers, currents, partial floods, and all the operations of moving water to have gone on exerting an energy many thousand times greater than at present would have appeared preposterous and incredible, and would have required 100 violent hypotheses. But we are so unacquainted with the true sources of subterranean disturbances that their former violence may in theory be multiplied indefinitely, without its being possible to prove the same manifest contradiction or absurdity in the conjecture. For this reason, perhaps, Morrow preferred to derive the materials of the strata from volcanic ejections rather than from transportation by running water. Marsili, whose work is alluded to by Generelli, had been prompted to institute inquiries into the bed of the Adriatic by discovering in the territory of Parma what Spada had observed near Verona and Schiavo in Sicily, that fossil shells were not scattered through the rocks at random, but disposed in regular order according to certain genera and species. Vitaliano Donati, 1750. But with a view of throwing further light upon these questions, Donati in 1750 undertook a more extensive investigation of the Adriatic, and discovered by numerous soundings that deposits of sand, marl, and tufaceous incrustations most strictly analogous to those of the sub-Apennine hills, were in the act of accumulating there. He ascertained that there were no shells in some of the submarine tracts, while in other places they lived together in families, particularly the genera Arca, Pecten, Venus, Murex, and some others. He also states that in diverse localities he found a mass composed of corals, shells, and crustaceous bodies of different species, confusedly blended with earth, sand, and gravel. At the depth of a foot or more, the organic substances were entirely petrified and reduced to marble. At less than a foot from the surface, they approached nearer to their natural state, while at the surface they were alive, or if dead, in a good state of preservation. Baldassari. A contemporary naturalist, Baldassari, had shown that the organic remains in the tertiary marls of the Sienese territory were grouped in families, in a manner precisely similar to that above alluded to by Donati. Buffon, 1749. Buffon first made known his theoretical views concerning the former changes of the earth in his Natural History, published in 1749. He adopted the theory of an original volcanic nucleus, together with the universal ocean of Leibnitz. By this aqueous envelope, the highest mountains were once covered. Marine currents then acted violently and formed horizontal strata by washing away solid matter in some parts and depositing it in others. They also excavated deep submarine valleys. The length of the ocean was then depressed by the entrance of a part of its waters into subterranean caverns, and thus some land was left dry. Buffon seems not to have profited, like Leibnitz and Morrow, by the observations of Steno, or he could not have imagined that the strata were generally horizontal, and that those which contain organic remains had never been disturbed since the era of their formation. He was conscious of the great power annually exerted by rivers and marine currents in transporting earthy materials to lower levels, and he even contemplated the period when they would destroy all the present continents. Although in geology he was not an original observer, his genius enabled him to render his hypothesis attractive, and by the eloquence of his style and the boldness of his speculations, he awakened curiosity and provoked a spirit of inquiry amongst his countrymen. Soon after the publication of his Natural History, in which was included his theory of the earth, he received an official letter, dated January 1751, from the Sorbonne, or Faculty of Theology in Paris, informing him that 14 propositions in his works were reprehensible and contrary to the creed of the Church. The first of these obnoxious passages, and the only one related to geology, was as follows: "The waters of the sea have produced the mountains and valleys of the land. The waters of the heavens, reducing all to a level, will at last deliver the whole land over to the sea, and the sea, successively prevailing over the land, will leave dry new continents like those which we inhabit." Buffon was invited by the college in very courteous terms to send in an explanation, or rather a recantation of his unorthodox opinions. To this he submitted, and a general assembly of the faculty, having approved of his declaration, he was required to publish it in his next work. The document begins with these words: "I declare that I had no intention to contradict the text of Scripture, that I believe most firmly all therein related about the creation, both as to order of time and matter of fact, and I abandon everything in my book respecting the foundation of the earth, and generally all which may be contrary to the narration of Moses." The grand principle which Buffon was called upon to renounce was simply this: that the present mountains and valleys of the earth are due to secondary causes, and that the same causes will in time destroy all the continents, hills, and valleys, and reproduce others like them. Now, whatever may be the defects of many of his views, it is no longer controverted that the present continents are of secondary origin. The doctrine is as firmly established as the earth's rotation on its axis, and that the land now elevated above the level of the sea will not endure forever, is an opinion which gains ground daily in proportion as we enlarge our experience of the changes now in progress. Targioni, 1751. Targioni, in his voluminous Travels in Tuscany, 1751 and 1754, labored to fill up the sketch of the geology of that region left by Steno 60 years before. Notwithstanding a want of arrangement and condensation in his memoirs, they contain a rich store of faithful observations. He has not indulged in many general views, but in regard to the origin of valleys, he was opposed to the theory of Buffon, who attributed them principally to submarine currents. The Tuscan naturalist labored to show that both the larger and smaller valleys of the Apennines were excavated by rivers and floods, caused by the bursting of the barriers of lakes after the retreat of the ocean. He also maintained that the elephants and other quadrupeds so frequent in the lacustrine and alluvial deposits of Italy had inhabited that peninsula, and had not been transported thither, as some had conceived, by Hannibal or the Romans, nor by what they were pleased to term a catastrophe of nature. Lehmann, 1756. In the year 1756, the treatise of Lehmann, a German mineralogist and director of the Prussian mines, appeared, who also divided mountains into three classes. The first, those formed with the world, and prior to the creation of animals, and which contained no fragments of other rocks. The second class, those which resulted from the partial destruction of the primary rocks by a general revolution, and a third class resulting from local revolutions, and in part from the deluge of Noah. A French translation of this work appeared in 1759, in the preface of which the translator displays very enlightened views respecting the operations of earthquakes, as well as of the aqueous causes. End of chapter 3, part 4. Chapter 3, part 5 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by deongines, Salt Lake City, Utah. Principles of Geology by Charles Lyell. Chapter 3, Section 5. Gesner, 1758. In this year, Gesner, the botanist of Zurich, published an excellent treatise on petrifactions and the changes of the earth which they testify. After a detailed enumeration of the various classes of fossils of the animal and vegetable kingdoms, and remarks on the different states in which they are found petrified, he considers the geological phenomena connected with them, observing that some, like those of Ehningen, resembled the testacea, fish, and plants indigenous in the neighboring region, while some, such as ammonites, graphites, belemnites, and other shells, are either of unknown species or found only in the Indian and other distant seas. In order to elucidate the structure of the earth, he gives sections from Verenius, Buffon, and others, obtained in digging wells, distinguishes between horizontal and inclined strata, and in speculating on the causes of these appearances, mentions Donati's examination of the bed of the Adriatic, the filling up of lakes and seas by sediment, the embedding of shells now in progress, and many known effects of earthquakes, such as the sinking down of districts or the heaving up of the bed of the sea, so as to form new islands, and lay dry strata containing petrifactions. The ocean, he says, deserts its shores in many countries, as on the borders of the Baltic, but the rate of recession has been so slow in the last 2,000 years that to allow the Apennines, whose summits are filled with marine shells, to emerge to their present height would have required about 80,000 years, a lapse of time 10 times greater or more than the age of the universe. We must therefore refer the phenomenon to the command of the deity, related by Moses, that the waters should be gathered together in one place, and the dry land appear. Gessner adopted the views of Leibniz to account for the retreat of the primeval ocean. His essay displays much erudition, and the opinions of preceding writers of Italy, Germany, and England are commented upon with fairness and discrimination. Arduino, 1759. In the year following, Arduino, in his memoirs on the mountains of Padua, Vicenza, and Verona, deduced from original observations the distinction of rocks into primary, secondary, and tertiary, and showed that in those districts there had been a succession of submarine volcanic eruptions. Michel, 1760. In the following year, 1760, the Reverend John Michel, Woodwardian professor of mineralogy at Cambridge, published in the Philosophical Transactions an essay on the cause and phenomena of earthquakes. His attention had been drawn to this subject by the great earthquake of Lisbon in 1755. He advanced many original and philosophical views respecting the propagation of subterranean movements and the caverns and fissures wherein steam might be generated. In order to point out the application of his theory to the structure of the globe, he was led to describe the arrangement and disturbance of the strata, their usual horizontality in low countries, and their contortions and fractured state in the neighborhood of mountain chains. He also explained, with surprising accuracy, the relations of the central ridges of older rocks to the long, narrow slips of similar earth, stones, and minerals, which are parallel to these ridges. In his generalizations, derived in great part from his own observations on the geological structure of Yorkshire, he anticipated many of the views more fully developed by later naturalists. Catcott, 1761. Michel's papers were entirely free from all physico-theological disquisitions, but some of his contemporaries were still earnestly engaged in defending or impugning the Woodwardian hypothesis. We find many of these writings referred to by Catcott, a Hutchinsonian, who published a treatise on the deluge in 1761. He labored particularly to refute an explanation offered by his contemporary, Bishop Clayton, of the Mosaic writings. That prelate had declared that the deluge could not be literally true, save in respect to that part where Noah lived before the flood. Catcott insisted on the universality of the deluge, and referred to traditions of inundations mentioned by ancient writers or by travelers in the East Indies, China, South America, and other countries. This part of his book is valuable, although it is not easy to see what bearing the traditions have, if admitted to be authentic, on the bishop's argument, since no evidence is adduced to prove that the catastrophes were contemporaneous events, while some of them are expressly represented by ancient authors to have occurred in succession. Fortis, Odoardi, 1761. The doctrines of Arduino, above adverted to, were afterwards confirmed by Fortis and Desmartist in their travels in the same country, and they, as well as Baldassari, labored to complete the history of the sub-Apennine strata. In the work of Odoardi, there was also a clear argument in favor of the distinct ages of the older Apennine strata, and the sub-Apennine formations of more recent origin. He pointed out that the strata of these two groups were unconformable, and must have been the deposits of different seas at distant periods of time. Raspe, 1763. A history of the New Islands by Raspe, a Hanoverian, appeared in 1763 in Latin. In this work, all the authentic accounts of earthquakes which had produced permanent changes on the solid parts of the earth were collected together and examined with judicious criticism. The best systems which had been proposed concerning the ancient history of the globe, both by ancient and modern writers, are reviewed, and the merits and defects of the doctrines of Hooke, Ray, Morrow, Buffon, and others fairly estimated. Great admiration is expressed for the hypothesis of Hooke, and his explanation of the origin of the strata is shown to have been more correct than Morrow's, while their theory of the effects of earthquakes was the same. Raspe had not seen Michel's memoirs, and his views concerning the geological structure of the earth were perhaps less enlarged. Yet he was able to add many additional arguments in favor of Hooke's theory, and to render it, as he said, a nearer approach to what Hooke would have written had he lived in later times. As to the periods wherein all the earthquakes happened, to which we owe the elevation of various parts of our continents and islands, Raspe says he pretends not to assign their duration, still less to defend Hooke's suggestion that the convulsions almost all took place during the deluge of Noah. He adverts to the apparent indications of the former tropical heat of the climate of Europe, and the changes in the species of animals and plants, as among the most obscure and difficult problems in geology. In regard to the islands raised from the sea, within the times of history or tradition, he declares that some of them were composed of strata containing organic remains, and that they were not, as Buffon had asserted, made from mere volcanic matter. His work concludes with an eloquent exhortation to naturalists to examine the isles which rose in 1707 in the Grecian archipelago and in 1720 in the Azores, and not to neglect such splendid opportunities of studying nature in the act of parturition. That Hooke's writings should have been neglected for more than half a century was matter of astonishment to Raspe, but it is still more wonderful that his own luminous exposition of that theory should, for more than another half-century, have excited so little interest. Feuchsel, 1762 and 1773. Feuchsel, a German physician, published in 1762 a geological description of the country between the Thuringerwald and the Harz, and a memoir on the environs of Rudolstadt, and afterwards, in 1773, a theoretical work on the ancient history of the earth and of man. He had evidently advanced considerably beyond his predecessor Lehmann, and was aware of the distinctness, both as to position and fossil contents, of several groups of strata of different ages, corresponding to the secondary formations now recognized by geologists in various parts of Germany. He supposed the European continents to have remained covered by the sea until the formation of the marine strata, called in Germany Muschelkalk, at the same time that the terrestrial plants of many European deposits attested the existence of dry land which bordered the ancient sea, land which, therefore, must have occupied the place of the present ocean. The pre-existing continent had been gradually swallowed up by the sea, different parts having subsided in succession into subterranean caverns. All the sedimentary strata were originally horizontal, and their present state of derangement must be referred to subsequent oscillations of the ground. As there were plants and animals in the ancient periods, so also there must have been men, but they did not all descend from one pair, but were created at various points on the earth's surface, and the number of these distinct birthplaces was as great as are the original languages of nations. In the writings of Feuchsel we see a strong desire manifested to explain geological phenomena, as far as possible by reference to the agency of known causes, and although some of his speculations were fanciful, his views coincide much more nearly with those now generally adopted than the theories afterwards promulgated by Werner and his followers. Brander, 1766. Gustavus Brander published in 1766 his Fossilia Hantoniensia, containing excellent figures of fossil shells from the more modern, or Eocene, marine strata of Hampshire. Various opinions, he says in the preface, had been entertained concerning the time when and how these bodies became deposited. Some there are who conceive that it might have been effected in a wonderful length of time by a gradual changing and shifting of the sea, etc. But the most common cause assigned is that of the deluge. This conjecture, he says, even if the universality of the flood be not called in question, is purely hypothetical. In his opinion, fossil animals and testacea were for the most part of unknown species, and of such as were known, the living analogues now belonged to southern latitudes. Soldani, 1780. Soldani applied successfully his knowledge of zoology to illustrate the history of stratified masses. He explained that microscopic testacea and zoophytes inhabited the depths of the Mediterranean, and that the fossil species were, in like manner, found in those deposits wherein the fineness of their particles and the absence of pebbles implied that they were accumulated in a deep sea or far from shore. This author first remarked the alternation of marine and freshwater strata in the Paris basin. Fortis, Testa, 1793. A lively controversy arose between Fortis and another Italian naturalist, Testa, concerning the fish of Monte Bolca in 1793. Their letters, written with great spirit and elegance, show that they were aware that a large proportion of the sub-Apennine shells were identical with living species, and some of them with species now living in the torrid zone. Fortis proposed a somewhat fanciful conjecture that when the volcanoes of the Vicentin were burning, the waters of the Adriatic had a higher temperature, and in this manner, he said, the shells of warmer regions may once have peopled their own seas. But Testa was disposed to think that these species of testacea were still common to their own and to equinoctial seas. For many, he said, once supposed to be confined to hotter regions, had been afterwards discovered in the Mediterranean. Cortesi, Balanzani, Wallerius Whitehurst. While these Italian naturalists, together with Cortesi and Spallanzani, were busily engaged in pointing out the analogy between the deposits of modern and ancient seas and the habits and arrangement of their organic inhabitants, and while some progress was making in the same country in investigating the ancient and modern volcanic rocks, some of the most original observers among the English and German writers, Whitehurst and Wallerius, were wasting their strength in contending, according to the old Woodwardian hypothesis, that all the strata were formed by Noah's deluge. But Whitehurst's description of the rocks of Derbyshire were most faithful, and he atoned for false theoretical views by providing data for their refutation. Pallas, Saussure. Towards the close of the 18th century, the idea of distinguishing the mineral masses on our globe into separate groups and studying their relations began to be generally diffused. Pallas and Saussure were among the most celebrated whose labors contributed to this end. After an attentive examination of the two great mountain chains of Siberia, Pallas announced the result that the granitic rocks were in the middle, the schistose at their sides, and the limestones again on the outside of these, and this he conceived would prove a general law in the formation of all chains composed chiefly of primary rocks. In his Travels in Russia in 1793, and 1794, he made many geological observations on the recent strata near the Volga and the Caspian, and adduced proofs of the greater extent of the latter sea at no distant era in the earth's history. His memoir on the fossil bones of Siberia attracted attention to some of the most remarkable phenomena in geology. He stated that he had found a rhinoceros entire in the frozen soil, with its skin and flesh. An elephant, found afterwards in a mass of ice on the shore of the North Sea, removed all doubt as to the accuracy of so wonderful a discovery. The subjects relating to natural history which engaged the attention of Pallas were too multifarious to admit of his devoting a large share of his labors exclusively to geology. Saussure, on the other hand, employed the chief portion of his time in studying the structure of the Alps and Jura, and he provided valuable data for those who followed him. He did not pretend to deduce any general system from his numerous and interesting observations, and the few theoretical opinions which escaped from him seem, like those of Pallas, to have been chiefly derived from the cosmological speculations of preceding writers. End of chapter 3, part 5.
Chapter 4, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Painter. Principles of Geology by Charles Lyell. Chapter 4, Part 1. History of the Progress of Geology. Werner's application of geology to the art of mining, excursive character of his lectures, enthusiasm of his pupils, his authority, his theoretical errors, Demarest's map and description of Auvergne, controversy between the volcanists and Neptunists, intemperance of the rival sects, Hutton's theory of the earth, his discovery of granite veins, originality of his views, why opposed, Playfair's illustrations, influence of Voltaire's writings on geology, imputations cast on the Huttonians by Williams, Kirwan, and Deluc, Smith's map of England, Geological Society of London, progress of the science in France, growing importance of the study of organic remains. Werner. The art of mining has long been taught in France, Germany, and Hungary, in scientific institutions established for that purpose, where mineralogy has always been a principal branch of instruction. Werner was named, in 1775, professor of that science in the School of Mines at Freiburg in Saxony. He directed his attention not merely to the composition and external characters of minerals, but also to what he termed geognosy, or the natural position of minerals in particular rocks, together with the grouping of those rocks, their geographical distribution, and various relations. The phenomena observed in the structure of the globe had hitherto served for little else than to furnish interesting topics for philosophical discussion. But when Werner pointed out their application to the practical purposes of mining, they were instantly regarded by a large class of men as an essential part of their professional education, and from that time the science was cultivated in Europe most ardently and systematically. Werner's mind was at once imaginative and richly stored with miscellaneous knowledge. He associated everything with his favourite science, and in his excursive lectures he pointed out all the economical uses of minerals and their application to medicine, the influence of the mineral composition of rocks upon the soil, and of the soil upon the resources, wealth, and civilization of man. The vast sandy plains of Tartary and Africa, he would say, retained their inhabitants in the shape of wandering shepherds. The granitic mountains and the low calcareous and alluvial plains gave rise to different manners, degrees of wealth, and intelligence. The history even of languages and the migration of tribes had been determined by the direction of particular strata. The qualities of certain stones used in building would lead him to descant on the architecture of different ages and nations, and the physical geography of a country frequently invited him to treat of military tactics. The charm of his manners and his eloquence kindled enthusiasm in the minds of his pupils, and many, who had intended at first only to acquire a slight knowledge of mineralogy, when they had once heard him, devoted themselves to it as the business of their lives. In a few years, a small school of mines, before unheard of in Europe, was raised to the rank of a great university, and men already distinguished in science studied the German language and came from the most distant countries to hear the great oracle of geology. Ware had a great antipathy to the mechanical labour of writing, and, with the exception of a valuable treatise on metalliferous veins, he could never be persuaded to pen more than a few brief memoirs, and those containing no development of his general views. Although the natural modesty of his disposition was excessive, approaching even to timidity, he indulged in the most bold and sweeping generalizations, and he inspired all his scholars with a most implicit faith in his doctrines. Their admiration of his genius and the feelings of gratitude and friendship which they all felt for him were not undeserved. But the supreme authority usurped by him over the opinions of his contemporaries was eventually prejudicial to the progress of the science, so much so as greatly to counterbalance the advantages which it derived from his exertions. If it be true that delivery be the first, second, and third requisite in a popular orator, it is no less certain that to travel is of first, second, and third importance to those who desire to originate just and comprehensive views concerning the structure of our globe. Now Ware had not travelled to distant countries. He had merely explored a small portion of Germany, and conceived and persuaded others to believe that the whole surface of our planet and all the mountain chains in the world were made after the model of his own province. It became a ruling object of ambition in the minds of his pupils to confirm the generalizations of their great master, and to discover in the most distant parts of the globe his universal formations, which he supposed had been each in succession simultaneously precipitated over the whole earth from a common menstruum or chaotic fluid. It now appears that the Saxon professor had misinterpreted many of the most important appearances even in the immediate neighbourhood of Freiburg. Thus, for example, within a day's journey of his school, the porphyry, called by him primitive, has been found not only to send forth veins or dykes through strata of the coal formation, but to overlie them in mass. The granite of the Harz Mountains, on the other hand, which he supposed to be the nucleus of the chain, is now well known to traverse the other beds, as near Goslar, and still nearer Freiburg in the Erzgebirge. The mica slate does not mantle round the granite as was supposed, but abuts abruptly against it. Fragments also of the Greywacker slate, containing organic remains, have recently been found entangled in the granite of the Harz by M. de Seckendorf. The principal merit of Ware's system of instruction consisted in steadily directing the attention of his scholars to the constant relations of superposition of certain mineral groups. But he had been anticipated, as has been shown in the last chapter, in the discovery of this general law, by several geologists in Italy and elsewhere, and his leading divisions of the secondary strata were at the same time and independently made the basis of an arrangement of the British strata by our countryman William Smith, to whose work I shall refer in the sequel. Controversy between the volcanists and Neptunists. In regard to basalt and other igneous rocks, Werner's theory was original, but it was also extremely erroneous. The basalts of Saxony and Hesse, to which his observations were chiefly confined, consisted of tabular masses capping the hills, and not connected with the levels of existing valleys, like many in Auvergne and the Vivarais. These basalts and all other rocks of the same family in other countries were, according to him, chemical precipitates from water. He denied that they were the products of submarine volcanoes, and even taught that, in the primeval ages of the world, there were no volcanoes. His theory was opposed, in a twofold sense, to the doctrine of the permanent agency of the same causes in nature, for not only did he introduce, without scruple, many imaginary causes supposed to have once effected great revolutions in the earth, and then to have become extinct, but new ones also were feigned to have come into play in modern times, and above all, that most violent instrument of change, the agency of subterranean heat. So early as 1768, before Werner had commenced his mineralogical studies, Raspe had truly characterized the basalts of Hesse as of igneous origin. Arduino, we have seen, had pointed out numerous varieties of trap rock in the Vicentin as analogous to volcanic products and as distinctly referable to ancient submarine eruptions. Desmarest, as before stated, had, in company with Fortis, examined the Vicentin in 1766 and confirmed Arduino's views. In 1772, Banks, Solander, and Troil compared the columnar basalt of Hecla with that of the Hebrides. Collini, in 1774, recognized the true nature of the igneous rocks on the Rhine, between Andernach and Bonn. In 1775, Guittard visited the Vivarais and established the relation of basaltic currents to lavas. Lastly, in 1779, Feuillas published his description of the volcanoes of the Vivarais and Velay, and showed how the streams of basalt had poured out from craters which still remain in a perfect state. Desmarest. When sound opinions had thus for 20 years prevailed in Europe concerning the true nature of the ancient trap rocks, Werner, by his simple dictum, caused a retrograde movement, and not only overturned the true theory, but substituted for it one of the most unphilosophical that can well be imagined. The continued ascendancy of his dogmas on this subject was the more astonishing because a variety of new and striking facts were daily accumulated in favour of the correct opinions previously entertained. Desmarest, after a careful examination of Auvergne, pointed out, first, the most recent volcanoes, which had their craters still entire, and their streams of lava conforming to the level of the present river courses. He then showed that there were others of an intermediate epoch, whose craters were nearly effaced, and whose lavas were less intimately connected with the present valleys. And lastly, that there were volcanic rocks, still more ancient, without any discernible craters or scoriae, and bearing the closest analogy to rocks in other parts of Europe, the igneous origin of which was denied by the school of Freiberg. Desmarest's map of Auvergne was a work of uncommon merit. He first made a trigonometrical survey of the district, and delineated its physical geography with minute accuracy and admirable graphic power. He contrived, at the same time, to express without the aid of colours many geological details, including the different ages and sometimes even the structure of the volcanic rocks, and distinguishing them from the freshwater and the granitic. They alone who have carefully studied Auvergne and traced the different lava streams from their craters to their termination, the various isolated basaltic cappings, the relation of some lavas to the present valleys, the absence of such relations in others, can appreciate the extraordinary fidelity of this elaborate work. No other district of equal dimensions in Europe exhibits, perhaps, so beautiful and varied a series of phenomena, and fortunately Desmarest possessed at once the mathematical knowledge required for the construction of a map, skill in mineralogy, and a power of original generalization. Dolomeur Montlosier. Dolomeur, another of Werner's contemporaries, had found prismatic basalt among the ancient lavas of Etna, and, in 1784, had observed the alternations of submarine lavas and calcareous strata in the Val di Noto in Sicily. In 1790 also he described similar phenomena in the Vicentin and in the Tyrol. Montlosier published in 1788 an essay on the theories of volcanoes of Auvergne, combining accurate local observations with comprehensive views. Notwithstanding this mass of evidence, the scholars of Werner were prepared to support his opinions to their utmost extent, maintaining, in the fullness of their faith, that even obsidian was an aqueous precipitate. As they were blinded by their veneration for the great teacher, they were impatient of opposition, and soon imbibed the spirit of a faction, and their opponents, the volcanists, were not long in becoming contaminated with the same intemperate zeal. Ridicule and irony were weapons more frequently employed than argument by the rival sects, till at last the controversy was carried on with a degree of bitterness almost unprecedented in questions of physical science. Desmarest, who had long before provided ample materials for refuting such a theory, kept aloof from the strife, and whenever a zealous Neptunist wished to draw the old man into an argument, he was satisfied with replying, "Go and see." Hutton, 1788. It would be contrary to all analogy in matters of graver import that a war should rage with such fury on the continent, and that the inhabitants of our island should not mingle in the affray. Although in England the personal influence of Werner was wanting to stimulate men to the defence of the weaker side of the question, they contrived to find good reason for espousing the Wernerian errors with great enthusiasm. In order to explain the peculiar motives which led many to enter, even with party feeling, into this contest, it will be necessary to present the reader with a sketch of the views unfolded by Hutton, a contemporary of the Saxon geologist. The former naturalist had been educated as a physician, but declining the practice of medicine, he resolved, when young, to remain content with the small independence inherited from his father, and thenceforth to give his undivided attention to scientific pursuits. He resided at Edinburgh, where he enjoyed the society of many men of high attainments, who loved him for the simplicity of his manners and the sincerity of his character. His application was unwearied, and he made frequent tours through different parts of England and Scotland, acquiring considerable skill as a mineralogist, and consequently arriving at grand and comprehensive views in geology. He communicated the results of his observations unreservedly, and with the fearless spirit of one who was conscious that love of truth was the sole stimulus of his exertions. When at length he had matured his views, he published, in 1788, his Theory of the Earth, and the same, afterwards more fully developed in a separate work in 1795. This treatise was the first in which geology was declared to be in no way concerned about questions as to the origin of things, the first in which an attempt was made to dispense entirely with all hypothetical causes, and to explain the former changes of the earth's crust by reference exclusively to natural agents. Hutton laboured to give fixed principles to geology, as Newton had succeeded in doing to astronomy. But in the former science, too little progress had been made towards furnishing the necessary data to enable any philosopher, however great his genius, to realise so noble a project. Huttonian theory. The ruins of an older world, said Hutton, are visible in the present structure of our planet, and the strata which now compose our continents have been once beneath the sea, and were formed out of the waste of pre-existing continents. The same forces are still destroying, by chemical decomposition or mechanical violence, even the hardest rocks, and transporting the materials to the sea, where they are spread out and form strata analogous to those of more ancient date. Although loosely deposited along the bottom of the ocean, they become afterwards altered and consolidated by volcanic heat, and then heaved up, fractured, and contorted. Although Hutton had never explored any region of active volcanoes, he had convinced himself that basalt and many other trap rocks were of igneous origin, and that many of them had been injected in a melted state through fissures in the older strata. The compactness of these rocks, and their different aspect from that of ordinary lava, he attributed to their having cooled down under the pressure of the sea. And in order to remove the objections started against this theory, his friend, Sir James Hall, instituted a most curious and instructive series of chemical experiments, illustrating the crystalline arrangement and texture assumed by melted matter cooled under high pressure. The absence of stratification in granite, and its analogy in mineral character to rocks which he deemed of igneous origin, led Hutton to conclude that granite also must have been formed from matter in fusion, and this inference he felt could not be fully confirmed unless he discovered at the contact of granite and other strata a repetition of the phenomena exhibited so constantly by the trap rocks. Resolved to try his theory by this test, he went to the Grampians and surveyed the line of junction of the granite and superincumbent stratified masses until he found in Glen Tilt in 1785 the most clear and unequivocal proofs in support of his views. Veins of red granite are there seen branching out from the principal mass, and traversing the black micaceous schist and primary limestone. The intersected stratified rocks are so distinct in colour and appearance as to render the example in that locality most striking, and the alteration of the limestone in contact was very analogous to that produced by trap veins on calcareous strata. This verification of his system filled him with delight, and called forth such marks of joy and exultation that the guides who accompanied him, says his biographer, were convinced that he must have discovered a vein of silver or gold. He was aware that the same theory would not explain the origin of the primary schists, but these he called primary, rejecting the term primitive, and was disposed to consider them as sedimentary rocks altered by heat, and that they originated in some other form from the waste of previously existing rocks. By this important discovery of granite veins, to which he had been led by fair induction from an independent class of facts, Hutton prepared the way for the greatest innovation of the systems of his predecessors, Vallisnieri had pointed out the general fact that there were certain fundamental rocks which contained no organic remains, and which he supposed to have been formed before the creation of living beings. Moro, Generelli, and other Italian writers embraced the same doctrine, and Lehmann regarded the mountains, called by him primitive, as parts of the original nucleus of the globe. The same tenet was an article of faith in the school of Freiburg, and if any one ventured to doubt the possibility of our being enabled to carry back our researches to the creation of the present order of things, the granitic rocks were triumphantly appealed to. On them seemed written, in legible characters, the memorable inscription, Dinanzi a me non fur cose create se non eterne. And no small sensation was excited when Hutton seemed, with unhallowed hand, desirous to erase characters already regarded by many as sacred. In the economy of the world, said the Scotch geologist, I can find no traces of a beginning, no prospect of an end. A declaration the more startling when coupled with the doctrine that all past ages on the globe had been brought about by the slow agency of existing causes. The imagination was first fatigued and overpowered by endeavouring to conceive the immensity of time required for the annihilation of whole continents by so insensible a process. And when the thoughts had wandered through these interminable periods, no resting place was assigned in the remotest distance. The oldest rocks were represented to be of a derivative nature, the last of an antecedent series, and that, perhaps, one of many pre-existing worlds. Such views of the immensity of past time, like those unfolded by the Newtonian philosophy in regard to space, were too vast to awaken ideas of sublimity unmixed with a painful sense of our own incapacity to conceive a plan of such infinite extent. Worlds are seen beyond worlds, immeasurably distant from each other, and, beyond them all, innumerable other systems are faintly traced on the confines of the visible universe. The characteristic feature of the Huttonian theory was, as before hinted, the exclusion of all causes not supposed to belong to the present order of nature. But Hutton had made no step beyond Hooke, Moro, and Raske in pointing out in what manner the laws now governing subterranean movements might bring about geological changes, if sufficient time be allowed. On the contrary, he seems to have fallen far short of some of their views, especially when he refused to attribute any part of the external configuration of the earth's crust to subsidence. He imagined that the continents were first gradually destroyed by aqueous degradation, and when their ruins had furnished materials for new continents, they were upheaved by violent convulsions. He therefore required alternate periods of general disturbance and repose, and such he believed had been and would forever be the course of nature. Generelli, in his exposition of Moro's system, had made a far nearer approximation towards reconciling geological appearances with the state of nature as known to us, for while he agreed with Hutton that the decay and reproduction of rocks were always in progress, proceeding with the utmost uniformity, the learned Carmelite represented the repairs of mountains by elevation from below to be effected by an equally constant and synchronous operation. Neither of these theories, considered singly, satisfies all the conditions of the great problem which a geologist who rejects cosmological causes is called upon to solve, but they probably contain together the germs of a perfect system. There can be no doubt that periods of disturbance and repose have followed each other in succession in every region of the globe. But it may be equally true that the energy of the subterranean movements have been always uniform as regards the whole earth. The force of earthquakes may for a cycle of years have been invariably confined, as it is now, to large but determinate spaces, and may then have gradually shifted its position, so that another region, which had for ages been at rest, became in its turn the grand theatre of action. Playfair's illustrations of Hutton. The explanation proposed by Hutton and by Playfair, the illustrator of his theory, respecting the origin of valleys and of alluvial accumulations, was also very imperfect. They ascribed none of the inequalities of the earth's surface to movements which accompanied the upheaving of the land, imagining that valleys in general were formed in the course of ages by the rivers now flowing in them, while they seem not to have reflected on the excavating and transporting power which the waves of the ocean might exert on land during its emergence. Although Hutton's knowledge of mineralogy and chemistry was considerable, he possessed but little information concerning organic remains. They merely served him, as they did Werner, to characterize certain strata and to prove their marine origin. The theory of former revolutions in organic life was not yet fully recognized, and without this class of proofs in support of the antiquity of the globe, the indefinite periods demanded by the Huttonian hypothesis appeared visionary to many, and some, who deemed the doctrine inconsistent with revealed truths, indulged very uncharitable suspicions of the motives of its author. They accused him of a deliberate design of reviving the heathen dogma of an eternal succession, and of denying that this world ever had a beginning. Playfair, in the biography of his friend, has the following comment on this part of their theory. In the planetary motions, where geometry has carried the eye so far, both into the future and the past, we discover no mark either of the commencement or termination of the present order. It is unreasonable indeed to suppose that such marks should anywhere exist. The author of nature has not given laws to the universe, which, like the institutions of men, carry in themselves the elements of their own destruction. He has not permitted in his works any symptom of infancy or of old age, or any sign by which we may estimate either their future or their past duration. He may put an end, as he no doubt gave a beginning, to the present system at some determinate period of time, but we may rest assured that this great catastrophe will not be brought about by the laws now existing, and that it is not indicated by anything which we perceive. The party feeling excited against the Huttonian doctrines, and the open disregard of candour and temper in the controversy, will hardly be credited by the reader, unless he recalls to his recollection that the mind of the English public was at that time in a state of feverish excitement. A class of writers in France had been labouring industriously for many years to diminish the influence of the clergy by sapping the foundations of the Christian faith, and their success and the consequences of the Revolution had alarmed the most resolute minds, while the imagination of the more timid was continually haunted by dread of innovation, as by the phantom of some fearful dream. End of chapter 4, part 1. Chapter 4, part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Painter. Principles of Geology by Charles Lyell. Section 10. Chapter 4, Part 2. Voltaire. Voltaire had used the modern discoveries in physics as one of the numerous weapons of attack and ridicule directed by him against the Scriptures. He found that the most popular systems of geology were accommodated to the sacred writings, and that much ingenuity had been employed to make every fact coincide exactly with the Mosaic account of the creation and deluge. It was, therefore, with no friendly feelings that he contemplated the cultivators of geology in general, regarding the science as one which had been successfully enlisted by theologians as an ally in their cause. He knew that the majority of those who were aware of the abundance of fossil shells in the interior of continents were still persuaded that they were proofs of the universal deluge, and as the readiest way of shaking this article of faith, he endeavoured to inculcate scepticism as to the real nature of such shells, and to recall from contempt the exploded dogma of the 16th century that they were sports of nature. He also pretended that vegetable impressions were not those of real plants. Yet he was perfectly convinced that the shells had really belonged to living testacea, as may be seen in his essay On the Formation of Mountains. He would sometimes, in defiance of all consistency, shift his ground when addressing the vulgar, and, admitting the true nature of the shells collected in the Alps and other places, pretend that they were Eastern species which had fallen from the hats of pilgrims coming from Syria. The numerous essays written by him on geological subjects were all calculated to strengthen prejudices, partly because he was ignorant of the real state of the science, and partly from his bad faith. On the other hand, they who knew that his attacks were directed by a desire to invalidate Scripture, and who were unacquainted with the true merits of the question, might well deem the old Diluvian hypothesis incontrovertible, if Voltaire could adduce no better argument against it than to deny the true nature of organic remains. It is only by careful attention to impediments originating in extrinsic causes that we can explain the slow and reluctant adoption of the simplest truths in geology. First, we find many able naturalists adducing the fossil remains of marine animals as proof of an event related in Scripture. The evidence is deemed conclusive by the multitude for a century or more, for it favours opinions which they entertained before, and they are gratified by supposing them confirmed by fresh and unexpected proofs. Many who see through the fallacy have no wish to undeceive those who are influenced by it, approving the effect of the delusion and conniving at it as a pious fraud, until, finally, an opposite party, who are hostile to the sacred writings, labour to explode the erroneous opinion by substituting for it another dogma, which they know to be equally unsound. The heretical Vulcanists were soon after openly assailed in England by imputations of the most illiberal kind. We cannot estimate the malevolence of such a persecution by the pain which similar insinuations might now inflict. For although charges of infidelity and atheism must always be odious, they were injurious in the extreme at that moment of political excitement, and it was better, perhaps, for a man's good reception in society that his moral character should have been traduced, than that he should become a mark for these poisoned weapons. I shall pass over the works of numerous divines, who may be excused for sensitiveness on points which then excited so much uneasiness in the public mind, and shall say nothing of the amiable poet Cowper, who could hardly be expected to have inquired into the merit of doctrines in physics. But in the foremost ranks of the intolerant are found several laymen who had high claims to scientific reputation. Among these appears Williams, a mineral surveyor of Edinburgh, who published a Natural History of the Mineral Kingdom in 1789, a work of great merit for that day, and of practical utility, as containing the best account of the coal strata. In his preface he misrepresents Hutton's theory altogether, and charges him with considering all rocks to be lavas of different colours and structure, and also with warping everything to support the eternity of the world. He descants on the pernicious influence of such sceptical notions as leading to downright infidelity and atheism, and as being nothing less than to depose the Almighty Creator of the universe from his office. Kirwan de Luc. Kirwan, President of the Royal Academy of Dublin, a chemist and mineralogist of some merit, but who possessed much greater authority in the scientific world than he was entitled by his talents to enjoy, said, in the introduction to his Geological Essays, 1799, that sound geology graduated into religion, and was required to dispel certain systems of atheism or infidelity, of which they had had recent experience. He was an uncompromising defender of the aqueous theory of all rocks, and was scarcely surpassed by Burnet and Whiston in his desire to adduce the Mosaic writings in confirmation of his opinions. De Luc, in the preliminary discourse to his treatise on geology, says, "The weapons have been changed by which revealed religion is attacked. It is now assailed by geology, and the knowledge of this science has become essential to theologians." He imputes the failure of former geological systems to their having been anti-Mosaical and directed against a sublime tradition. These and similar imputations, reiterated in the works of De Luc, seem to have been taken for granted by some modern writers. It is therefore necessary to state, in justice to the numerous geologists of different nations whose works have been considered, that none of them were guilty of endeavouring, by arguments drawn from physics, to invalidate scriptural tenets. On the contrary, the majority of those who were fortunate enough to discover the true cause of things rarely deserved another part of the poet's panegyric, atque metus omnes subjectit pedibus. The caution and even timid reserve of many eminent Italian authors of the earlier period is very apparent, and there can hardly be a doubt that they subscribed to certain dogmas, and particularly to the first diluvian theory, out of deference to popular prejudices rather than from conviction. If they were guilty of dissimulation, we may feel regret, but must not blame their want of moral courage, reserving rather our condemnation for the intolerance of the times, and that inquisitorial power which forced Galileo to abjure and the two Jesuits to disclaim the theory of Newton. Hutton answered Kirwan's attacks with great warmth and with the indignation justly excited by unmerited reproach. He had always displayed, says Playfair, the utmost disposition to admire the beneficent design manifested in the structure of the world, and he contemplated with delight those parts of his theory which made the greatest additions to our knowledge of final causes. We may say with equal truth that in no scientific works in our language can more eloquent passages be found concerning the fitness, harmony, and grandeur of all parts of the creation than in those of Playfair. They are evidently the unaffected expressions of a mind which contemplated the study of nature as best calculated to elevate our conceptions of the attributes of the first cause. At any other time, the force and elegance of Playfair's style must have ensured popularity to the Huttonian doctrines. But, by a singular coincidence, Neptunianism and orthodoxy were now associated in the same creed, and the tide of prejudice ran so strong that the majority were carried far away into the chaotic fluid and other cosmological inventions of Ware. These fictions the Saxon professor had borrowed with little modification and without any improvement from his predecessors. They had not the smallest foundation either in scripture or in common sense, and were probably approved of by many as being so ideal and unsubstantial that they could never come into violent collision with any preconceived opinions. According to Deluc, the first essential distinction to be made between the various phenomena exhibited on the surface of the earth was, to determine which were the results of causes still in action, and which had been produced by causes that had ceased to act. The form and composition of the mass of our continents, he said, and their existence above the level of the sea, must be ascribed to causes no longer in action. These continents emerged, at no very remote period, on the sudden retreat of the ocean, the waters of which made their way into subterranean caverns. The formation of the rocks which enter into the crust of the earth began with the precipitation of granite from a primordial liquid, after which other strata containing the remains of organized bodies were deposited, till at last the present sea remained as the residuum of the primordial liquid, and no longer continued to produce mineral strata. William Smith, 1790. While the tenets of the rival schools of Freiburg and Edinburgh were warmly espoused by devoted partisans, the labours of an individual, unassisted by the advantages of wealth or station in society, were almost unheeded. Mr. William Smith, an English surveyor, published his Tabular View of the British Strata in 1790, wherein he proposed a classification of the secondary formations in the west of England. Although he had not communicated with Ware, it appeared by this work that he had arrived at the same views respecting the laws of superposition of stratified rocks, that he was aware that the order of succession of different groups was never inverted, and that they might be identified at very distant points by their peculiar organized fossils. From the time of the appearance of the Tabular View, the author laboured to construct a geological map of the whole of England, and with the greatest disinterestedness of mind communicated the results of his investigations to all who desired information, giving such publicity to his original views as to enable his contemporaries almost to compete with him in the race. The execution of his map was completed in 1815, and remains a lasting monument of original talent and extraordinary perseverance, for he had explored the whole country on foot, without the guidance of previous observers or the aid of fellow labourers, and had succeeded in throwing into natural divisions the whole complicated series of British rocks. D'Aubusson, a distinguished pupil of Ware, paid a just tribute of praise to this remarkable performance, observing that what many celebrated mineralogists had only accomplished for a small part of Germany in the course of half a century, had been effected by a single individual for the whole of England. Ware invented a new language to express his division of rocks, and some of his technical terms, such as gravaker, gneiss, and others, passed current in every country in Europe. Smith adopted for the most part English provincial terms, often of barbarous sound, such as gault, cornbrash, clunch clay, and affixed them to subdivisions of the British series. Many of these still retain their place in our scientific classifications and attest his priority of arrangement. Modern progress of geology. The contention of the rival factions of the volcanists and Neptunists had been carried to such a height that these names had become terms of reproach, and the two parties had been less occupied in searching for truth than for such arguments as might strengthen their own cause or serve to annoy their antagonists. A new school at last arose, who professed the strictest neutrality and the utmost indifference to the systems of Ware and Hutton, and who resolved diligently to devote their labours to observation. The reaction, provoked by the intemperance of the conflicting parties, now produced a tendency to extreme caution. Speculative views were discountenanced, and, through fear of exposing themselves to the suspicion of a bias towards the dogmas of a party, some geologists became anxious to entertain no opinion whatever on the causes of phenomena, and were inclined to scepticism even where the conclusions deducible from observed facts scarcely admitted of reasonable doubt. Geological Society of London. But although the reluctance to theorise was carried somewhat to excess, no measure could be more salutary at such a moment than a suspension of all attempts to form what were termed theories of the earth. A great body of new data were required, and the Geological Society of London, founded in 1807, conduced greatly to the attainment of this desirable end. To multiply and record observations, and patiently to await the result at some future period, was the object proposed by them, and it was their favourite maxim that the time was not yet come for a general system of geology, but that all must be content for many years to be exclusively engaged in furnishing materials for future generalizations. By acting up to these principles with consistency, they, in a few years, disarmed all prejudice, and rescued the science from the imputation of being a dangerous, or at best, but a visionary pursuit. A distinguished modern writer has with truth remarked that the advancement of three of the main divisions of geological inquiry have during the last half-century been promoted successively by three different nations of Europe: the Germans, the English, and the French. We have seen that the systematic study of what may be called mineralogical geology had its origin and chief point of activity in Germany, where Ware first described with precision the mineral characters of rocks. The classification of the secondary formations, each marked by their peculiar fossils, belongs, in a great measure, to England, where the labours before alluded to of Smith, and those of the most active members of the Geological Society of London, were steadily directed to these objects. The foundation of the third branch, that relating to the tertiary formations, was laid in France by the splendid work of Cuvier and Brongniart, published in 1808, on the mineral geography and organic remains of the neighbourhood of Paris. We may still trace, in the language of the science and our present methods of arrangement, the various countries where the growth of these several departments of geology was at different times promoted. Many names of simple minerals and rocks remain to this day German, while the European divisions of the secondary strata are in great part English, and are, indeed, often founded too exclusively on English types. Lastly, the subdivisions first established of the succession of strata in the Paris basin have served as normal groups to which other tertiary deposits throughout Europe have been compared, even in cases where this standard was wholly inapplicable. No period could have been more fortunate for the discovery, in the immediate neighbourhood of Paris, of a rich store of well-preserved fossils, than the commencement of the present century, for at no former era had natural history been cultivated with such enthusiasm in the French metropolis. The labours of Cuvier in comparative osteology and of Lamarck in recent and fossil shells had raised these departments of study to a rank of which they had never previously been deemed susceptible. Their investigations had eventually a powerful effect in dispelling the illusion which had long prevailed concerning the absence of analogy between the ancient and modern state of our planet. A close comparison of the recent and fossil species, and the inferences drawn in regard to their habits, accustomed the geologist to contemplate the earth as having been at successive periods the dwelling place of animals and plants of different races, some terrestrial and others aquatic, some fitted to live in seas, others in the waters of lakes and rivers. By the consideration of these topics, the mind was slowly and insensibly withdrawn from imaginary pictures of catastrophes and chaotic confusion, such as haunted the imagination of the early cosmogonists. Numerous proofs were discovered of the tranquil deposition of sedimentary matter and the slow development of organic life. If many writers, and Cuvier himself in the number, still continued to maintain that the thread of induction was broken, yet, in reasoning by the strict rules of induction from recent to fossil species, they, in a great measure, disclaimed the dogma which in theory they professed. The adoption of the same generic, and in some cases even of the same specific, names for the exuviae of fossil animals and their living analogues was an important step towards familiarizing the mind with the idea of the identity and unity of the system in distant eras. It was an acknowledgment, as it were, that part at least of the ancient memorials of nature were written in a living language. The growing importance, then, of the natural history of organic remains may be pointed out as the characteristic feature of the progress of the science during the present century. This branch of knowledge has already become an instrument of great utility in geological classification, and is continuing daily to unfold new data for grand and enlarged views respecting the former changes of the earth. When we compare the result of observations in the last 50 years with those of the 3 preceding centuries, we cannot but look forward with the most sanguine expectations to the degree of excellence to which geology may be carried, even by the labours of the present generation. Never, perhaps, did any science, with the exception of astronomy, unfold, in an equally brief period, so many novel and unexpected truths, and overturn so many preconceived opinions. The senses had for ages declared the earth to be at rest, until the astronomer taught that it was carried through space with inconceivable rapidity. In like manner was the surface of this planet regarded as having remained unaltered since its creation, until the geologist proved that it had been the theatre of reiterated change, and was still the subject of slow but never-ending fluctuations. The discovery of other systems in the boundless regions of space was the triumph of astronomy. To trace the same system through various transformations, to behold it at successive eras adorned with different hills and valleys, lakes and seas, and peopled with new inhabitants, was the delightful meed of geological research. By the geometer were measured the regions of space and the relative distances of the heavenly bodies. By the geologist, myriads of ages were reckoned not by arithmetical computation, but by a train of physical events, a succession of phenomena in the animate and inanimate worlds, signs which convey to our minds more definite ideas than figures can do of the immensity of time. whether our investigation of the Earth's history and structure will eventually be productive of as great practical benefits to mankind as a knowledge of the distant heavens, must remain for the decision of posterity. It was not till astronomy had been enriched by the observations of many centuries, and had made its way against popular prejudices to the establishment of a sound theory, that its application to the useful arts was most conspicuous. The cultivation of geology began at a later period, and in every step which it has hitherto made towards sound theoretical principles, it had to contend against more violent prepossessions. The practical advantages already derived from it have not been inconsiderable, but our generalizations are yet imperfect, and they who come after us may be expected to reap the most valuable fruits of our labour. Meanwhile, the charm of first discovery is our own, and as we explore this magnificent field of inquiry, the sentiment of a great historian of our times may continually be present to our minds, that he who calls what has vanished back again into being enjoys a bliss like that of creating. End of chapter 4, part 2.
Chapter 5, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick McHaffie, Chicago. Chapter 5. Prejudices which have retarded the progress of geology. Prepossessions in regard to the duration of past time. Prejudices arising from our peculiar position as inhabitants of the land. Of those occasioned by our not seeing subterranean changes now in progress. All these causes combine to make the former course of nature appear different from the present. Objections to the doctrine that causes similar in kind and energy to those now acting have produced the former changes of the earth's surface considered. If we reflect on the history of the progress of geology, as explained in the preceding chapters, we perceive that there have been great fluctuations of opinion respecting the nature of the causes to which all former changes of the earth's surface are referable. The first observers conceived the monuments which the geologist endeavors to decipher to relate to an original state of the earth, or to a period when there were causes in activity distinct in kind and degree from those now constituting the economy of nature. These views were gradually modified, and some of them entirely abandoned, in proportion as observations were multiplied and the signs of former mutations more skillfully interpreted. Many appearances which had for a long time been regarded as indicating mysterious and extraordinary agency, were finally recognized as the necessary result of the laws now governing the material world, and the discovery of this unlooked-for conformity has at length induced some philosophers to infer that during the ages contemplated in geology, there has never been any interruption to the agency of the same uniform laws of change. The same assemblage of general causes, they conceive, may have been sufficient to produce, by their various combinations, the endless diversity of effects of which the shell of the earth has preserved the memorials, and, consistently with these principles, the recurrence of analogous changes is expected by them in time to come. Whether we coincide or not in this doctrine, we must admit that the gradual progress of opinion concerning the succession of phenomena in very remote eras resembles, in a singular manner, that which has accompanied the growing intelligence of every people in regard to the economy of nature in their own times. In an early state of advancement, when a great number of natural appearances are unintelligible and eclipse an earthquake, a flood, or the approach of a comet, with many other occurrences afterwards found to belong to the regular course of events, are regarded as prodigies. The same delusion prevails as to moral phenomena, and many of these are ascribed to the intervention of demons, ghosts, witches, and other immaterial and supernatural agents. By degrees, many of the enigmas of the moral and physical world are explained, and, instead of being due to extrinsic and irregular causes, they are found to depend on fixed and invariable laws. The philosopher at last becomes convinced of the undeviating uniformity of secondary causes, and, guided by his faith in this principle, he determines the probability of accounts transmitted to him of former occurrences, and often rejects the fabulous tales of former times, on the ground of their being irreconcilable with the experience of more enlightened ages. Prepossessions in regard to the duration of past time. As a belief in the want of conformity in the causes by which the earth's crust has been modified in ancient and modern periods was, for a long time, universally prevalent, and that, too, amongst men who were convinced that the order of nature had been uniform for the last several thousand years, every circumstance which could have influenced their minds and given an undue bias to their opinions deserves particular attention. Now the reader may easily satisfy himself that, however undeviating the course of nature may have been from the earliest epochs, it was impossible for the first cultivators of geology to come to such a conclusion, so long as they were under a delusion as to the age of the world, and the date of the first creation of animate beings. However fantastical some theories of the 16th century may now appear to us, however unworthy of men of great talent and sound judgment, we may rest assured that, if the same misconception now prevailed in regard to the memorials of human transactions, it would give rise to a similar train of absurdities. Let us imagine, for example, that Champollion and the French and Tuscan literati, lately engaged in exploring the antiquities of Egypt, had visited that country with a firm belief that the banks of the Nile were never peopled by the human race before the beginning of the 19th century, and that their faith in this dogma was as difficult to shake as the opinion of our ancestors that the earth was never the abode of living beings until the creation of the present continents, and of the species now existing. It is easy to perceive what extravagant systems they would frame while under the influence of this delusion to account for the monuments discovered in Egypt. The sight of the pyramids, obelisks, colossal statues, and ruined temples would fill them with such astonishment that for a time they would be as men spellbound, wholly incapable of reasoning with sobriety. They might incline at first to refer to the construction of such stupendous works to some superhuman powers of a primeval world. A system might be invented resembling that so gravely advanced by Manetho, who relates that a dynasty of gods originally ruled in Egypt, of whom Vulcan, the first monarch, reigned 9,000 years, after whom came Hercules and other demigods, who were at last succeeded by human kings. When some fanciful speculations of this kind had amused their imaginations for a time, some vast repository of mummies would be discovered, and would immediately undeceive those antiquaries who enjoyed an opportunity of personally examining them, but the prejudices of others at a distance, who were not eyewitnesses of the whole phenomena, would not be so easily overcome. The concurrent report of many travellers would, indeed, render it necessary for them to accommodate ancient theories to some of the new facts, and much wit and ingenuity would be required to modify and defend their old positions. Each new invention would violate a greater number of known analogies. For if a theory be required to embrace some false principle, it becomes more visionary in proportion as facts are multiplied, as would be the case if geometers were now required to form an astronomical system on the assumption of the immobility of the earth. Amongst other fanciful conjectures concerning the history of Egypt, we may suppose some of the following to be started. Quote, as the banks of the Nile have been so recently colonized for the first time, the curious substances called mummies could never in reality have belonged to men. They may have been generated by some plastic virtue residing in the interior of the earth, or they may be abortions of nature, produced by her incipient efforts in the work of creation. For if deformed beings are sometimes born even now, when the scheme of the universe is fully developed, many more may have been sent before their time, scarce half made up, when the planet itself was in the embryo state. But if these notions appear to derogate from the perfection of the divine attributes, and if these mummies be in all their parts true representations of the human form, may we not refer them to the future rather than the past? May we not be looking into the womb of nature and not her grave? May not these images be like the shades of the unborn in Virgil's Elysium, the archetypes of men not yet called into existence? End quote. These speculations, if advocated by eloquent writers, would not fail to attract many zealous votaries, for they would relieve men from the painful necessity of renouncing preconceived opinions. Incredible as such skepticism may appear, it has been rivaled by many systems of the 16th and 17th centuries, and among others by that of the learned Falloppio, who regarded the tusks of fossil elephants as earthy concretions, and the pottery or fragments of vases in the Monte Testaceo near Rome as works of nature, and not of art. But when one generation had passed away, and another, not compromised to the support of antiquated dogmas, had succeeded, they would review the evidence afforded by mummies more impartially, and would no longer controvert the preliminary question that human beings had lived in Egypt before the 19th century, so that when 100 years perhaps had been lost, the industry and talents of the philosopher would be at last directed to the elucidation of points of real historical importance. But the above arguments are aimed against one only of many prejudices with which the earlier geologists had to contend. Even when they conceded that the earth had been peopled with animate beings at an earlier period than was at first supposed, they had no conception that the quantity of time bore so great a proportion to the historical era as is now generally conceded. How fatal every error as to the quantity of time must prove to the introduction of rational views concerning the state of things in former ages may be conceived by supposing the annals of the civil and military transactions of a great nation to be perused under the impression that they occurred in a period of 100 instead of 2,000 years. Such a portion of history would immediately assume the air of a romance. The events would seem devoid of credibility and inconsistent with the present course of human affairs. A crowd of incidents would follow each other in thick succession. Armies and fleets would appear to be assembled only to be destroyed, and cities built merely to fall in ruins. There would be the most violent transitions from foreign or intestine war to periods of profound peace, and the works effected during the years of disorder or tranquillity would appear alike superhuman in magnitude. He who should study the monuments of the natural world under the influence of a similar infatuation must draw a no less exaggerated picture of the energy and violence of causes, and must experience the same insurmountable difficulty in reconciling the former and present state of nature. If we could behold in one view all the volcanic cones thrown up in Iceland, Italy, Sicily, and other parts of Europe during the last 5,000 years, we could see the lavas which have flowed during the same period, the dislocations, subsidences, and elevations caused during earthquakes, the lands added to various deltas, or devoured by the sea, together with the effects of devastation by floods, and imagine that all these events had happened in 1 year, we must form most exalted ideas of the activity of the agents and the suddenness of the revolutions. Were an equal amount of change to pass before our eyes in the next year, could we avoid the conclusion that some great crisis of nature was at hand? If geologists, therefore, have misinterpreted the signs of a succession of events, so as to conclude that centuries were implied where the characters imported thousands of years, and thousands of years where the language of nature signified millions, they could not, if they reasoned logically from such false premises, come to any other conclusion than that the system of the natural world had undergone a complete revolution. We should be warranted in ascribing the erection of the Great Pyramid to superhuman power if we were convinced that it was raised in 1 day, and if we imagine in the same manner a continent or mountain chain to have been elevated during an equally small fraction of the time which was really occupied in upheaving it, we might then be justified in inferring that the subterranean movements were once far more energetic than in our own times. We know that during one earthquake the coast of Chile may be raised for 100 miles, to the average height of about 3 feet. A repetition of 2,000 shocks of equal violence might produce a mountain chain 100 miles long and 6,000 feet high. Now, should 1 or 2 only of these convulsions happen in a century, it would be consistent with the order of events experienced by the Chileans from the earliest times. But if the whole of them were to occur in the next 100 years, the entire district must be depopulated. Scarcely any animals or plants could survive, and the surface would be one confused heap of ruin and desolation. One consequence of undervaluing greatly the quantity of past time is the apparent coincidence which it occasions of events necessarily disconnected, or which are so unusual that it would be inconsistent with all calculation of chances to suppose them to happen at one and the same time. When the unlooked-for association of such rare phenomena is witnessed in the present course of nature, it scarcely ever fails to excite a suspicion of the preternatural in those minds which are not firmly convinced of the uniform agency of secondary causes. As if the death of some individual in whose fate they are interested happens to be accompanied by the appearance of a luminous meteor or a comet, or the shock of an earthquake. It would be only necessary to multiply such coincidences indefinitely, and the mind of every philosopher would be disturbed. Now it would be difficult to exaggerate the number of physical events, many of them most rare and unconnected in their nature, which were imagined by the Woodwardian hypothesis to have happened in the course of a few months. And numerous other examples might be found of popular geological theories, which require us to imagine that a long succession of events happened in a brief and almost momentary period. Another liability to error, very nearly allied to the former, arises from the frequent contact of geological monuments referring to very distant periods of time. We often behold, at one glance, the effects of causes which have acted at times incalculably remote, and yet there may be no striking circumstances to mark the occurrence of a great chasm in the chronological series of nature's archives. In the vast interval of time which may really have elapsed between the results of operations thus compared, the physical condition of the earth may, by slow and insensible modifications, have become entirely altered. One or more races of organic beings may have passed away, and yet have left behind, in the particular region under contemplation, no trace of their existence. To a mind unconscious of these intermediate events, the passage from one state of things to another must appear so violent that the idea of revolutions in the system inevitably suggests itself. The imagination is as much perplexed by the deception as it might be if two distant points in space were suddenly brought into immediate proximity. Let us suppose for a moment that a philosopher should lie down to sleep in some Arctic wilderness, and then be transferred by a power such as we read of in tales of enchantment to a valley in a tropical country, where, on awakening, he might find himself surrounded by birds of brilliant plumage, and all the luxuriance of animal and vegetable forms of which nature is so prodigal in those regions. The most reasonable supposition, perhaps, which he could make, if by the necromancer's art he were placed in such a situation, would be that he was dreaming, and if a geologist formed theories under a similar delusion, we cannot expect him to preserve more consistency in his speculations than in the train of ideas in an ordinary dream. It may afford, perhaps, a lively illustration of the principle here insisted upon, if I recall to the reader's recollection the legend of the 7 Sleepers. The scene of that popular fable was placed in the 2 centuries which elapsed between the reign of the Emperor Decius and the death of Theodosius the Younger. In that interval of time, between the years 249 and 450 of our era, the union of the Roman Empire had been dissolved, and some of its fairest provinces overrun by the barbarians of the north. The seat of government had passed from Rome to Constantinople, and the throne from a pagan persecutor to a succession of Christian and Orthodox princes. The genius of the empire had been humbled in the dust, and the altars of Diana and Hercules were on the point of being transferred to Catholic saints and martyrs. The legend relates, quote, that when Decius was still persecuting the Christians, 7 noble youths of Ephesus concealed themselves in a spacious cavern in the side of an adjacent mountain, where they were doomed to perish by the tyrant, who gave orders that the entrance should be firmly secured with a pile of huge stones. They immediately fell into a deep slumber, which was miraculously prolonged without injuring the powers of life during a period of 187 years. At the end of that time, the slaves of Adolius, to whom the inheritance of the mountain had descended, removed the stones to supply materials for some rustic edifice. The light of the sun darted into the cavern, and the 7 sleepers were permitted to awake. After a slumber, as they thought, of a few hours, they were pressed by the calls of hunger, and resolved that Jamblichus, one of their number, should secretly return to the city to purchase bread for the use of his companions. The youth could no longer recognize the once familiar aspect of his native country, and his surprise was increased by the appearance of a large cross triumphantly erected over the principal gate of Ephesus. His singular dress and obsolete language confounded the baker, to whom he offered an ancient medal of Decius as the current coin of the empire, and Jamblichus, on the suspicion of a secret treasure, was dragged before the judge. Their mutual inquiries produced the amazing discovery that 2 centuries were almost elapsed since Jamblichus and his friends had escaped from the rage of a pagan tyrant." End quote. This legend was received as authentic throughout the Christian world before the end of the 6th century, and was afterwards introduced by Mohammed as a divine revelation into the Koran, and from hence was adopted and adorned by all the nations from Bengal to Africa who professed the Mohammedan faith. Some vestiges even of a similar tradition have been discovered in Scandinavia. Quote, "This easy and universal belief," observes the philosophical historian of the Decline and Fall, "so expressive of the sense of mankind, may be ascribed to the genuine merit of the fable itself. We imperceptibly advance from youth to age without observing the gradual but incessant change of human affairs, and even in our larger experience of history, the imagination is accustomed by a perpetual series of causes and effects to unite the most distant revolutions. But if the interval between 2 memorable eras could be instantly annihilated, if it were possible, after a momentary slumber of 200 years, to display the new world to the eyes of a spectator who still retained a lively and recent impression of the old, his surprise and his reflections would furnish the pleasing subject of a philosophical romance." End quote. End of Chapter 5, Part 1. Recording by Patrick McHaffie, Chicago. Chapter 5, Part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick McHaffie, Chicago. Principles of Geology by Charles Lyell. Chapter 5, Part 2. Prejudices arising from our peculiar position as inhabitants of the land. The sources of prejudice hitherto considered may be deemed peculiar for the most part to the infancy of the science, but others are common to the first cultivators of geology, and to ourselves, and are all singularly calculated to produce the same deception, and to strengthen our belief that the course of nature in the earlier ages differed widely from that now established. Although these circumstances cannot be fully explained without assuming some things as proved, which it will be the object of another part of this work to demonstrate, it may be well to allude to them briefly in this place. The first and greatest difficulty, then, consists in an habitual unconsciousness that our position as observers is essentially unfavorable when we endeavor to estimate the nature and magnitude of the changes now in progress. In consequence of our inattention to this subject, we are liable to serious mistakes in contrasting the present with former states of the globe. As dwellers on the land, we inhabit about 1/4 part of the surface, and that portion is almost exclusively a theater of decay, and not of reproduction. We know, indeed, that new deposits are annually formed in seas and lakes, and that every year some new igneous rocks are produced in the bowels of the earth. But we cannot watch the progress of their formation, and as they are only present to our minds by the aid of reflection, it requires an effort both of the reason and the imagination to appreciate duly their importance. It is, therefore, not surprising that we estimate very imperfectly the result of operations thus invisible to us, and that, when analogous results of former epochs are presented to our inspection, we cannot immediately recognize the analogy. He who has observed the quarrying of stone from a rock, and has seen it shipped for some distant port, and then endeavors to conceive what kind of edifice will be raised by the materials, is in the same predicament as a geologist, who, while he is confined to the land, sees the decomposition of rocks and the transportation of matter by rivers to the sea, and then endeavors to picture to himself the new strata which nature is building beneath the waters. Prejudices arising from our not seeing subterranean changes. Nor is his position less unfavorable when, beholding a volcanic eruption, he tries to conceive what changes the column of lava has produced in its passage upwards on the intersected strata, or what from the melted matter may assume at great depths on cooling, or what may be the extent of the subterranean rivers and reservoirs of liquid matter far beneath the surface. It should, therefore, be remembered that the task imposed on those who study the earth's history requires no ordinary share of discretion, for we are precluded from collating the corresponding parts of the system of things as it exists now, and as it existed at former periods. If we were inhabitants of another element, if the great ocean were our domain, instead of the narrow limits of the land, our difficulties would be considerably lessened. While, on the other hand, there can be little doubt, although the reader may, perhaps, smile at the bare suggestion of such an idea, that an amphibious being who should possess our faculties would still more easily arrive at sound theoretical opinions in geology, since he might behold, on the one hand, the decomposition of rocks in the atmosphere, or the transportation of matter by running water, and, on the other, examine the deposition of sediment in the sea and the embedding of animal and vegetable remains in new strata. He might ascertain by direct observation the action of a mountain torrent as well as of a marine current, might compare the products of volcanoes poured out upon the land with those ejected beneath the waters, and might mark, on the one hand, the growth of the forest, and, on the other, that of the coral reef. Yet, even with these advantages, he would be liable to fall into the greatest errors when endeavoring to reason on rocks of subterranean origin. He would seek in vain, within the sphere of his observation, for any direct analogy to the process of their formation, and would therefore be in danger of attributing them, wherever they are upraised to view, to some primeval state of nature. But if we may be allowed so far to indulge the imagination as to suppose a being entirely confined to the nether world, some dusky melancholy sprite like Umbriel, who could flit on sooty pinions to the central earth, but who was never permitted to sully the fair face of light, and emerge into the regions of water and of air, and if this being should busy himself in investigating the structure of the globe, he might frame theories the exact converse of those usually adopted by human philosophers. He might infer that the stratified rocks containing shells and other organic remains were the oldest of created things, belonging to some original and nascent state of the planet. Of these masses, he might say, whether they consist of loose, incoherent sand, soft clay, or solid stone, none have been formed in modern times. Every year some part of them are broken and shattered by earthquakes, or melted by volcanic fire. And when they cool down slowly from a state of fusion, they assume a new and more crystalline form, no longer exhibiting that stratified disposition and those curious impressions and fantastic markings by which they were previously characterized. This process cannot have been carried on for an indefinite time, for in that case all the stratified rocks would long ere this have been fused and crystallized. It is therefore probable that the whole planet once consisted of these mysterious and curiously bedded formations at a time when the volcanic fire had not yet been brought into activity. Since that period there seems to have been a gradual development of heat, and this augmentation we may expect to continue till the whole globe shall be in a state of fluidity and incandescence. Such might be the system of the gnome at the very time that the followers of Leibniz, reasoning on what they saw in the outer surface, might be teaching the opposite doctrine of gradual refrigeration, and averring that the earth had begun its career as a fiery comet, and might be destined hereafter to become a frozen mass. The tenets of the school of the nether and of the upper world would be directly opposed to each other, for both would partake of the prejudices inevitably resulting from the continual contemplation of one class of phenomena to the exclusion of another. Man observes the annual decomposition of crystalline and igneous rocks, and may sometimes see their conversion into stratified deposits, but he cannot witness the reconversion of the sedimentary into the crystalline by subterranean fire. He is in the habit of regarding all the sedimentary rocks as more recent than the unstratified, for the same reason that we may suppose him to fall into the opposite error if he saw the origin of the igneous class only. It was not an impossible contingency that astronomers might have been placed at some period in a situation much resembling that in which the geologist seems to stand at present. If the Italians, for example, in the early part of the 12th century, had discovered at Amalfi, instead of the Pandects of Justinian, some ancient manuscripts filled with astronomical observations relating to a period of 3,000 years, and made by some ancient geometers who possessed optical instruments as perfect as any in modern Europe, they would probably, on consulting these memorials, have come to a conclusion that there had been a great revolution in the solar and sidereal systems. Many primary and secondary planets, they might say, are enumerated in these tables, which exist no longer. Their positions are assigned with such precision that we may assure ourselves that there is nothing in their place at present but the blue ether. Where one star is visible to us, these documents represent several thousands. Some of those which are now single consisted then of two separate bodies, often distinguished by different colors, and revolving periodically around a common center of gravity. There is nothing analogous to them in the universe at present, for they were neither fixed stars nor planets, but seem to have stood in the mutual relation of sun and planet to each other. We must conclude, therefore, that there has occurred at no distant period a tremendous catastrophe, whereby thousands of worlds have been annihilated at once, and some heavenly bodies absorbed into the substance of others. When such doctrines had prevailed for ages, the discovery of some of the worlds supposed to have been lost, the satellites of Jupiter, for example, by aid of the first rude telescope invented after the revival of science, would not dissipate the delusion, for the whole burden of proof would now be thrown on those who insisted on the stability of the system from a remote period, and these philosophers would be required to demonstrate the existence of all the worlds said to have been annihilated. Such popular prejudices would be most unfavorable to the advancement of astronomy. For instead of persevering in the attempt to improve their instruments and laboriously to make and record observations, the greater number would despair of verifying the continued existence of the heavenly bodies not visible to the naked eye. Instead of confessing the extent of their ignorance and striving to remove it by bringing to light new facts, they would indulge in the more easy and indolent employment of framing imaginary theories concerning catastrophes and mighty revolutions in the system of the universe. For more than 2 centuries, the shelly strata of the sub-Apennine hills afforded matter of speculation to the early geologists of Italy, and few of them had any suspicion that similar deposits were then forming in the neighboring sea. They were as unconscious of the continued action of causes still producing similar effects as the astronomers, in the case above supposed, of the existence of certain heavenly bodies still giving and reflecting light, and performing their movements as of old. Some imagined that the strata, so rich in organic remains, instead of being due to secondary agents, had been so created in the beginning of things by the fiat of the Almighty. Others, as we have seen, ascribed the embedded fossil bodies to some plastic power which resided in the earth in the early ages of the world. In what manner were these dogmas at length exploded? The fossil relics were carefully compared with their living analogues, and all doubts as to their organic origin were eventually dispelled. So, also, in regard to the nature of the containing beds of mud, sand, and limestone. Those parts of the bottom of the sea were examined where shells are now becoming annually entombed in new deposits. Donati explored the bed of the Adriatic, and found the closest resemblance between the strata there forming and those which constituted hills above 1,000 feet high in various parts of the Italian peninsula. He ascertained by dredging that living testacea were there grouped together in precisely the same manner as were their fossil analogues in the inland strata. And while some of the recent shells of the Adriatic were becoming encrusted with calcareous rock, he observed that others had been newly buried in sand and clay, precisely as fossil shells occur in the sub-Apennine hills. This discovery of the identity of modern and ancient submarine operations was not made without the aid of artificial instruments, which, like the telescope, brought phenomena into view not otherwise within the sphere of human observation. In like manner, the volcanic rocks of the Vicentin had been studied in the beginning of the last century, but no geologist suspected before the time of Arduino that these were composed of ancient submarine lavas. During many years of controversy, the popular opinion inclined to a belief that basalt and rocks of the same class had been precipitated from a chaotic fluid or an ocean which rose at successive periods over the continents, charged with the component elements of the rocks in question. Few will now dispute that it would have been difficult to invent a theory more distant from the truth, yet we must cease to wonder that it gained so many proselytes, when we remember that its claims to probability arose partly from the very circumstance of its confirming the assumed want of analogy between geological causes and those now in action. By what train of investigations were geologists induced at length to reject these views, and to assent to the igneous origin of the trappean formations by an examination of volcanoes now active, and by comparing their structure and the composition of their lavas with the ancient trap rocks. The establishment from time to time of numerous points of identification drew at length from geologists a reluctant admission that there was more correspondence between the conditions of the globe at remote eras and now, and more uniformity in the laws which have regulated the changes of its surface than they at first imagined. If, in this state of the science, they still despaired of reconciling every class of geological phenomena to the operations of ordinary causes, even by straining analogy to the utmost limits of credibility, we might have expected, at least, that the balance of probability would now have been presumed to incline towards the close analogy of the ancient and modern causes. But after repeated experience of the failure of attempts to speculate on geological monuments as belonging to a distant order of things, new sects continued to persevere in the principles adopted by their predecessors. They still began, as each new problem presented itself, whether relating to the animate or inanimate world, to assume an original and dissimilar order of nature, and when at length they approximated or entirely came round to an opposite opinion, it was always with the feeling that they were conceding what they had been justified a priori in deeming improbable. In a word, the same men who, as natural philosophers, would have been most incredulous respecting any extraordinary deviations from the known course of nature, if reported to have happened in their own time, were equally disposed, as geologists, to expect the proofs of such deviations at every period of the past. I shall proceed in the following chapters to enumerate some of the principal difficulties still opposed to the theory of the uniform nature and energy of the causes which have worked successive changes in the crust of the earth and in the condition of its living inhabitants. The discussion of so important a question on the present occasion may appear premature, but it is one which naturally arises out of a review of the former history of the science. It is, of course, impossible to enter into such speculative topics without occasionally carrying the novice beyond his depth and appealing to facts and conclusions with which he will be unacquainted until he has studied some elementary work on geology. But it may be useful to excite his curiosity and lead him to study such works by calling his attention at once to some of the principal points of controversy. End of Chapter 5, Part 2. Recording by Patrick McHaffie, Chicago.
Chapter 6, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in June 2019. Principles of Geology by Charles Lyell. Chapter 6, Part 1. Doctrine of the discordance of the ancient and modern causes of change controverted. Climate of the northern hemisphere formerly different. Direct proofs from the organic remains of the Italian strata. Proofs from analogy derived from extinct quadrupeds. Embedding of animals in icebergs. Siberian mammoths. Evidence in regard to temperature from the fossils of tertiary and secondary rocks. From the plants of the coal formation. Northern limit of these fossils. whether such plants could endure the long continuance of an Arctic night. Climate of the Northern Hemisphere formerly different. Proofs of former revolutions in climate, as deduced from fossil remains, have afforded one of the most popular objections to the theory which endeavors to explain all geological changes by reference to those now in progress on the earth. The probable causes, therefore, of fluctuations in climate may first be treated of. That the climate of the Northern Hemisphere has undergone an important change, and that its mean annual temperature must once have more nearly resembled that now experienced within the tropics, was the opinion of some of the first naturalists who investigated the contents of the ancient strata. Their conjecture became more probable when the shells and corals of the older Tertiary and many secondary rocks were carefully examined, for the organic remains of these formations were found to be intimately connected by generic affinity with species now living in warmer latitudes. At a later period, many reptiles, such as turtles, tortoises, and large saurian animals, were discovered in European formations in great abundance, and they supplied new and powerful arguments, from analogy, in support of the doctrine that the heat of the climate had been great when our secondary strata were deposited. Lastly, when the botanist turned his attention to the specific determination of fossil plants, the evidence acquired still further confirmation, for the flora of a country is peculiarly influenced by temperature, and the ancient vegetation of the earth might have been expected more readily than the forms of animals to have afforded conflicting proofs, had the popular theory been without foundation. When the examination of fossil remains was extended to rocks in the most northern parts of Europe and North America, and even to the Arctic regions, indications of the same revolution in climate were discovered. It cannot be said that in this, as in many other departments of geology, we have investigated the phenomena of former eras and neglected those of the present state of things. On the contrary, since the first agitation of this interesting question, the accessions to our knowledge of living animals and plants have been immense, and have far surpassed all the data previously obtained for generalizing on the relation of certain types of organization to particular climates. The tropical and temperate zones of South America and of Australia have been explored, and, on close comparison, it has been found that scarcely any of the species of the animate creation in these extensive continents are identical with those inhabiting the Old World. Yet the zoologist and botanist, well acquainted with the geographical distribution of organic beings in other parts of the globe, would have been able, if distinct groups of species had been presented to them from these regions, to recognize those which had been collected from latitudes within, and those which were brought from without the tropics. Before I attempt to explain the probable causes of great vicissitudes of temperature on the earth's surface, I shall take a rapid view of some of the principal data which appear to support the popular opinions now entertained on the subject. To insist on the soundness of these inferences is the more necessary because some zoologists have undertaken to vindicate the uniformity of the laws of nature, not by accounting for former fluctuations in climate, but by denying the value of the evidence in their favor. Proofs from fossil shells in Tertiary strata. In Sicily, Calabria, and the neighborhood of Naples, the fossil Testacea of the most modern Tertiary formations belong almost entirely to species now inhabiting the Mediterranean, but as we proceed northwards in the Italian peninsula, we find in the strata called sub-Apennine an assemblage of fossil shells departing somewhat more widely from the type of the neighboring seas. The proportion of species identifiable with those now living in the Mediterranean is still considerable, but it no longer predominates, as in the south of Italy and part of Sicily, over the unknown species. Although occurring in localities which are removed several degrees farther from the equator, as in Siena, Parma, Asti, etc., the shells yield clear indications of a warmer climate. This evidence is of great weight, and is not neutralized by any facts of a conflicting character, such, for instance, as the association, in the same group, of individuals referable to species now confined to Arctic regions. Whenever any of the fossil shells are identified with living species foreign to the Mediterranean, it is not in the northern ocean, but nearer the tropics, that they must be sought. On the other hand, the associated unknown species belong, for the most part, to genera which are now most largely developed in equinoctial regions, as, for example, the genera Cancellaria, Cassidaria, Plurotoma, Conus, and Cyprea. On comparing the fossils of the tertiary deposits of Paris and London with those of Bordeaux, and these again with the more modern strata of Sicily, we should at first expect that they would each indicate a higher temperature in proportion as they are situated farther to the south. But the contrary is true. Of the shells belonging to these several groups, whether freshwater or marine, some are of extinct, others of living species. Those found in the older, or Eocene, deposits of Paris and London, although 6 or 7 degrees to the north of the Miocene strata at Bordeaux, afford evidence of a warmer climate, while those of Bordeaux imply that the sea in which they lived was of a higher temperature than that of Sicily, where the shelly strata was formed 6 or 7 degrees nearer to the equator. In these cases the greater antiquity of the several formation, the Parisian being the oldest and the Sicilian the newest, has more than counterbalanced the influence which latitude would otherwise exert, and this phenomenon clearly points to a gradual and successive refrigeration of climate. Siberian mammoths. It will naturally be asked whether some recent geological discoveries bringing evidence to light of a colder, or as it has been termed, glacial epoch, towards the close of the tertiary periods throughout the northern hemisphere, does not conflict with the theory above alluded to, of a warmer temperature having prevailed in the eras of the Eocene, Miocene, and Pliocene formations. In answer to this inquiry, it may certainly be affirmed that an oscillation of climate has occurred in times immediately antecedent to the peopling of the earth by men, but proof to the intercalation of a less genial climate at an era where nearly all the marine and terrestrial testacea had already become specifically the same as those now living, by no means rebuts the conclusion previously drawn in favor of a warmer condition of the globe during the ages which elapsed while the tertiary strata were deposited. In some of the most superficial patches of sand, gravel, and loam, scattered very generally over Europe, and containing recent shells, the remains of extinct species of land quadrupeds have been found, especially in places where the alluvial matter appears to have been washed into small lakes, or into depressions in the plains bordering ancient rivers. Similar deposits have also been lodged in rents and caverns of rocks, where they may have been swept in by land floods or introduced by engulfed rivers during changes in the physical geography of these countries. The various circumstances under which the bones of animals have been thus preserved will be more fully considered hereafter. I shall only state here that among the extinct mammalia thus entombed we find species of the elephant, rhinoceros, hippopotamus, bear, hyena, lion, tiger, monkey, macacus, and many others, consisting partly of genera now confined to warmer regions. It is certainly probable that when some of these quadrupeds abounded in Europe, the climate was milder than that now experienced. The hippopotamus, for example, is now only met with where the temperature of the water is warm and nearly uniform throughout the year, and where the rivers are never frozen over. Yet, when the great fossil species, Hippopotamus major, CUV, inhabited England, the Testacea of our country were nearly the same as those now existing, and the climate cannot be supposed to have been very hot. The bones of this animal have lately been found by Mr. Strickland, together with those of a bear and other mammalia at Cropthorne, near Evesham, in Worcestershire, in alluvial sand, together with 23 species of terrestrial and freshwater shells, all, with 2 exceptions, of British species. The bed of sand, containing the shells and bones, reposes on lias, and is covered with alternating strata of gravel, sand, and loam. The mammoth also appears to have existed in England when the temperature of our latitudes could not have been very different from that which now prevails, for remains of this animal have been found at Northcliffe, in the county of York, in a lacustrine formation, in which all the land and freshwater shells, 13 in number, can be identified with species and varieties now existing in that county. Bones of the bison also, an animal now inhabiting a cold or temperate climate, have been found in the same place. That these quadrupeds, and the indigenous species of Testacea associated with them, were all contemporary inhabitants of Yorkshire, has been established by unequivocal proof. The Rev. W. V. Vernon Harcourt caused a pit to be sunk to the depth of 22 feet through undisturbed strata, in which the remains of the mammoth were found embedded, together with the shells, in a deposit which had evidently resulted from tranquil waters. In the valley of the Thames, as at Ilford and Grays in Essex, bones of the elephant and rhinoceros occur in strata abounding in freshwater shells of the genera Unio, Cyclus, Paludina, Valvata, Ancylus, and others. These fossil shells belong for the most part to species now living in the same district, yet some few of them are extinct, as, for example, a species of Sirena, a genus no longer inhabiting Europe and now entirely restricted to warmer latitudes. When reasoning on such phenomena, the reader must always bear in mind that the fossil individuals belonged to species of elephant, rhinoceros, hippopotamus, bear, tiger, and hyena, distinct from those which now dwell within or near the tropics. Dr. Fleming, in a discussion on this subject, has well remarked that a near resemblance in form and osteological structure is not always followed, in the existing creation, by a similarity of geographical distribution, and we must therefore be on our guard against deciding too confidently, from mere analogy of anatomical structure, respecting the habits and physiological peculiarities of species now no more. The zebra delights to roam over the tropical plains, while the horse can maintain its existence throughout an Iceland winter. The buffalo, like the zebra, prefers a high temperature, and cannot thrive even where the common ox prospers. The musk ox, on the other hand, though nearly resembling the buffalo, prefers the stinted herbage of the Arctic regions, and is able, by its periodical migrations, to outlive a northern winter. The jackal, Canis aureus, inhabits Africa, the warmer parts of Asia, and Greece, while the Isatis, Canis lagopus, resides in the Arctic regions. The African hare and the polar hare have their geographical distribution expressed in their trivial names, and different species of bears thrive in tropical, temperate, and Arctic latitudes. Recent investigations have placed beyond all doubt the important fact that a species of tiger, identical with that of Bengal, is common in the neighborhood of Lake Aral, near Sussex, in the 45th degree of north latitude, and from time to time this animal is now seen in Siberia, in a latitude as far north as the parallel of Berlin and Hamburg. Humboldt remarks that the part of southern Asia now inhabited by this Indian species of tiger is separated from the Himalaya by 2 great chains of mountains, each covered with perpetual snow, the chain of Kuen Lun, latitude 35 degrees north, and that of Muztagh, latitude 42 degrees, so that it is impossible that these animals should merely have made excursions from India so as to have penetrated in summer to the 48th and 53rd degrees of north latitude. They must remain all the winter north of the Muztagh, or Celestial Mountains. The last tiger killed in 1828 on the Lena in latitude 52 1/4 degree was in a climate colder than that of Petersburg and Stockholm. We learn from Mr. Hodgen's account of the mammalia of Nepal that the tiger is sometimes found at the very edge of perpetual snow in the Himalaya, and Pennant mentions that it is found among the snows of Mount Ararat in Armenia. The jaguar also has been seen in America, wandering from Mexico as far north as Kentucky, latitude 37 degrees north, and even as far as 42 degrees south in South America, a latitude which corresponds to that of the Pyrenees in the northern hemisphere. The range of the puma is still wider, for it roams from the equator to the Straits of Magellan, being often seen at Port Famine in latitude 53 degrees 38 minutes south. A new species of panther, Felis irbis, covered with long hair, has been discovered in Siberia, evidently inhabiting, like the tiger, a region north of the Celestial Mountains, which are in latitude 42 degrees. The two-horned African rhinoceros occurs without the tropics at the Cape of Good Hope, in latitude 34 degrees 29 minutes south, where it is accompanied by the elephant, hippopotamus, and hyena. Here the migration of all these species towards the south is arrested by the ocean, but if the continent had been prolonged still farther, and the land had been of moderate elevation, it is very probable that they might have extended their range to a greater distance from the tropics. Now, if the Indian tiger can range in our own times to the southern borders of Siberia or skirt the snows of the Himalaya, and if the puma can reach the 53rd degree of latitude in South America, we may easily understand how large species of the same genera may once have inhabited our temperate climates. The mammoth, E. primigenius, already alluded to, as occurring fossil in England, was decidedly different from the two existing species of elephants, one of which is limited to Asia, south of the 31st degree of northern latitude, the other to Africa, where it extends, as before stated, as far south as the Cape of Good Hope. The bones of the great fossil species are very widely spread over Europe and North America, but are nowhere in such profusion as in Siberia, particularly near the shores of the frozen ocean. Are we, then, to conclude that this animal preferred a polar climate? If so, it may well be asked, by what food was it sustained, and why does it not still survive near the Arctic Circle? Footnote. The speculations which follow on the ancient physical geography of Siberia and its former fitness as a residence for the mammoth were first given in their present form in my 4th edition, June, 1835. Recently, Dr. Sir Murchison and his companions in their great work on the Geology of Russia, 1845, Volume 1, page 497, have, in citing this chapter, declared that their investigations have led them to similar conclusions. Professor Owen, in his excellent History of British Fossil Mammalia, 1844, page 261 et sequitur, observes that the teeth of the mammoth differ from those of the living Asiatic or African elephant in having a larger proportion of dense enamel, which may have enabled it to subsist on the coarser ligneous tissues of trees and shrubs. In short, he is of opinion that the structure of its teeth, as well as the nature of its epidermis and coverings, may have made it a meet companion for the reindeer. End footnote. Pallas and other writers describe the bones of the mammoth as abounding throughout all the lowlands of Siberia, stretching in a direction west and east, from the borders of Europe to the extreme point nearest America, and south and north from the base of the mountains of Central Asia to the shores of the Arctic Sea. See map Figure 1. Within this space, scarcely inferior in area to the whole of Europe, fossil ivory has been collected almost everywhere, on the banks of the Irtish, Obi, Yenisei, Lena, and other rivers. The elephantine remains do not occur in the marshes and low plains, but where the banks of the rivers present lofty precipices of sand and clay, from which circumstance Pallas very justly inferred that, if sections could be obtained, similar bones might be found in all the elevated lands intervening between the great rivers. Strahlenberg indeed had stated, before the time of Pallas, that wherever any of the great rivers overflowed and cut out fresh channels during floods, more fossil remains of the same kind were invariably disclosed. As to the position of the bones, Pallas found them in some places embedded together with marine remains, in others simply with fossil wood or lignite, such as, he says, might have been derived from carbonized peat. On the banks of the Yenisei, below the city of Krasnoyarsk, in latitude 56 degrees, he observed grinders and bones of elephants, in strata of yellow and red loam, alternating with coarse sand and gravel, in which was also much petrified wood of the willow and other trees. Neither here nor in the neighboring country were there any marine shells, but merely layers of black coal. But grinders of the mammoth were collected much farther down the same river, near the sea, in latitude 70 degrees, mixed with marine petrifactions. Many other places in Siberia are cited by Pallas, where seashells and fishes' teeth accompany the bones of the mammoth, rhinoceros, and Siberian buffalo or bison, Bos priscus. But it is not on the Obi nor the Yenisei, but on the Lena, farther to the east, where, in the same parallels of latitude, the cold is far more intense, that fossil remains have been found in the most wonderful state of preservation. In 1772, Pallas obtained from Vilyuiskoy, in latitude 64 degrees, from the banks of the Vilyui, a tributary of the Lena, the carcass of a rhinoceros, R. ticcorhinus, taken from the sand in which it must have remained congealed for ages, the soil of that region being always frozen to within a slight depth of the surface. This carcass was compared to a natural mummy, and emitted an odor like putrid flesh, part of the skin being still covered with black and gray hairs. So great indeed was the quantity of hair on the foot and head conveyed to St. Petersburg, that Pallas asked whether the rhinoceros of the Lena might not have been an inhabitant of the temperate regions of Middle Asia, its clothing being so much warmer than that of the African rhinoceros. Professor Brandt of St. Petersburg, in a letter to Baron Alexander von Humboldt, dated 1846, adds the following particulars respecting this wonderful fossil relic. I have been so fortunate as to extract from cavities in the molar teeth of the Vilyui rhinoceros a small quantity of its half-chewed food, among which fragments of pine leaves, 1/2 of the seed of a polygonoecious plant, and very minute portions of wood with porous cells, or small fragments of coniferous wood, were still recognizable. It was also remarkable, on a close investigation of the head, that the blood vessels discovered in the interior of the mass appeared filled, even to the capillary vessels, with a brown mass, coagulated blood, which in many places still showed the red color of blood. After more than 30 years, the entire carcass of a mammoth, or extinct species of elephant, was obtained in 1803 by Mr. Adams, much farther to the north. It fell from a mass of ice, in which it had been encased, on the banks of the Lena, in latitude 70 degrees, and so perfectly had the soft parts of the carcass been preserved, that the flesh, as it lay, was devoured by wolves and bears. This skeleton is still in the Museum of St. Petersburg, the head retaining its integument and many of the ligaments entire. The skin of the animal was covered, first with black bristles, thicker than horsehair, from 12 to 16 inches in length, secondly, with hair of a reddish-brown color, about 4 inches long, and thirdly, with wool of the same color as the hair, about an inch in length. Of the fur, upwards of 30 pounds weight were gathered from the wet sandbank. The individual was 9 feet high and 16 feet long, without reckoning the large curved tusks, a size rarely surpassed by the largest living male elephants. It is evident, then, that the mammoth, instead of being naked like the living Indian and African elephants, was enveloped in a thick, shaggy covering of fur, probably as impenetrable to rain and cold as that of the musk ox. Footnote. Fleming, editor, New Philosophical Journal, No. 12, page 285. Bishop Heber informs us, Narrative of a Journey through the Upper Provinces of India, Volume 2, page 166 to 219, that in the lower range of the Himalaya Mountains, in the northeastern borders of the Delhi territory, between latitude 29 degrees and 30 degrees, he saw an Indian elephant of a small size, covered with shaggy hair. But this variety must be exceedingly rare, for Mr. Royal, late superintendent of the East India Company's Botanic Garden at Sarahunpur, has assured me that being in India when Heber's journal appeared, and having never seen or heard of such elephants, he made the strictest inquiries respecting the fact, and was never able to obtain any evidence in corroboration. Mr. Royal resided at Saharunpur, latitude 30 degrees north, upon the extreme northern limits of the range of the elephant. Mr. Everest also declares that he has been equally unsuccessful in finding any one aware of the existence of such a variety or breed of the animal, though one solitary individual was mentioned to him as having been seen at Delhi, with a good deal of long hair upon it. The greatest elevation, says Mr. Everest, at which the wild elephant is found in the mountains to the north of Bengal, is at a place called Nahoon, about 4,000 feet above the level of the sea, and in the 31st degree of northern latitude, where the mean yearly temperature may be about 64 degrees Fahrenheit, and the difference between winter and summer very great, equal to about 36 degrees Fahrenheit, the month of January averaging 45 degrees, and June, the hottest month, 81 degrees Fahrenheit. Everest on Climates of Fossil Elephants, Journal of Asiatic Society, No. 25, page 21. End footnote. The species may have been fitted by nature to withstand the vicissitudes of a northern climate, and it is certain that, from the moment when the carcasses, both of the rhinoceros and elephant above described, were buried in Siberia, in latitudes 64 degrees and 70 degrees north, the soil must have remained frozen, and the atmosphere nearly as cold as at this day. The most recent discoveries made in 1843 by Mr. Middendorf, a distinguished Russian naturalist, and which he communicated to me in September 1846, afford more precise information as to the climate of the Siberian lowlands, at the period when the extinct quadrupeds were entombed. One elephant was found on the Tass, between the Obi and Yenisei, near the Arctic Circle, about latitude 66 degrees 30 minutes north, with some parts of the flesh in so perfect a state that the bulb of the eye is now preserved in the museum at Moscow. Another carcass, together with a young individual of the same species, was met with in the same year, 1843, in latitude 75 degrees 15 minutes north, near the river Taimyr, with the flesh decayed. It was embedded in strata of clay and sand, with erratic blocks, at about 15 feet above the level of the sea. In the same deposit, Mr. Middendorf observed the trunk of a large tree, Pinus larix, the same wood as that now carried down in abundance by the Taimyr to the Arctic Sea. There were also associated fossil shells of living northern species, and which are moreover characteristic of the drift or glacial deposits of Europe. Among these, Nucula pygmaea, Tellina calcera, Maya truncata, and Saxicava rugosa were conspicuous. So fresh is the ivory throughout northern Russia that, according to Tilesius, thousands of fossil tusks have been collected and used in turning, yet others are still procured and sold in great plenty. He declares his belief that the bones still left in northern Russia must greatly exceed in number all the elephants now living on the globe. We are as yet ignorant of the entire geographical range of the mammoth, but its remains have been recently collected from the cliffs of frozen mud and ice on the east side of Bering's Straits, in Eschscholz Bay, in Russian America, latitude 66 degrees north. As the cliffs waste away by the thawing of the ice, tusks and bones fall out, and a strong odor of animal matter is exhaled from the mud. On considering all the facts above enumerated, it seems reasonable to imagine that a large region in Central Asia, including perhaps the southern half of Siberia, enjoyed, at no very remote period in the earth's history, a temperate climate, sufficiently mild to afford food for numerous herds of elephants and rhinoceroses, of species distinct from those now living. It has usually been taken for granted that herbivorous animals of large size require a very luxuriant vegetation for their support, but this opinion is, according to Mr. Darwin, completely erroneous. It has been derived, he says, from our acquaintance with India and the Indian islands, where the mind has been accustomed to associate troops of elephants with noble forests and impenetrable jungles. But the southern parts of Africa, from the Tropic of Capricorn to the Cape of Good Hope, although sterile and desert, are remarkable for the number and great bulk of the indigenous quadrupeds. We there meet with an elephant, 5 species of rhinoceros, a hippopotamus, a giraffe, the bos kaffir, the eland, 2 zebras, the quagga, 2 gnus, and several antelopes. Nor must we suppose that while the species are numerous, the individuals of each kind are few. Dr. Andrew Smith saw in one day's march, in latitude 24 degrees south, without wandering to any great distance on either side, about 150 rhinoceroses, with several herds of giraffes, and his party had killed, on the previous night, 8 hippopotamuses. Yet the country which they inhabited was thinly covered with grass and bushes about 4 feet high, and still more thinly with mimosa trees, so that the wagons of the travelers were not prevented from proceeding in a nearly direct line. End of Chapter 6, Part 1. Chapter 6, Part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in July 2019. Principles of Geology by Charles LYELL. Chapter 6, Part 2. In order to explain how so many animals can find support in this region, it is suggested that the underwood, of which their food chiefly consists, may contain much nutriment in a small bulk, and also that the vegetation has a rapid growth, for no sooner is a part consumed than its place, says Dr. Smith, is supplied by a fresh stock. Nevertheless, after making every allowance for this successive production and consumption, it is clear, from the facts above cited, that the quantity of food required by the larger herbivora is much less than we have usually imagined. Mr. Darwin conceives that the amount of vegetation supported at any one time by Great Britain may exceed in a 10-fold ratio the quantity existing on an equal area in the interior parts of southern Africa. It is remarked, moreover, in illustration of the small connection discoverable between abundance of food and the magnitude of indigenous mammalia, that while in the desert part of southern Africa there are so many huge animals, in Brazil, where the splendor and exuberance of the vegetation are unrivaled, there is not a single wild quadruped of large size. It would doubtless be impossible for herds of mammoths and rhinoceroses to subsist, at present, throughout the year, even in the southern part of Siberia, covered as it is with snow during winter. But there is no difficulty in supposing a vegetation capable of nourishing these great quadrupeds to have once flourished between the latitudes 40° and 60° north. Dr. Fleming has hinted that the kind of food which the existing species of elephant prefers will not enable us to determine, or even to offer a probable conjecture, concerning that of the extinct species. No one acquainted with the gramineous character of the food of our fallow deer, stag, or roe would have assigned a lichen to the reindeer. Travelers mention that even now, when the climate of Eastern Asia is so much colder than the same parallels of latitude farther west, there are woods not only of fir, but of birch, on the banks of the Lena, as far north as latitude 60°. It has, moreover, been suggested that as, in our own times, the northern animal migrate, so the Siberian elephant and rhinoceros may have wandered towards the north in summer. The musk oxen annually desert their winter quarters in the south and cross the sea upon the ice to graze for 4 months, from May to September, on the rich pasturage of Melvin Island in latitude 75°. The mammoths, without passing so far beyond the Arctic Circle, may nevertheless have made excursions, during the heat of a brief northern summer, from the central or temperate parts of Asia to the 60th parallel of latitude. Now, in this case, the preservation of their bones, or even occasionally of their entire carcasses, in ice or frozen soil, may be accounted for, without resorting to speculations concerning sudden revolutions in the former state and climate of the earth's surface. We are entitled to assume that, in the time of the extinct elephant and rhinoceros, the lowland of Siberia was less extensive towards the north than now, for we have seen that the strata of this lowland, in which the fossil bones lie buried, were originally deposited beneath the sea, and we know, from the facts brought to light in Wrangell's voyage, in the year 1821, 1822, and 1823, that a slow upheaval of the land along the borders of the icy sea is now constantly taking place, similar to that experienced in part of Sweden. In the same manner, then, as the shores of the Gulf of Bothnia are extended not only by the influx of sediment brought down by rivers, but also by the elevation and consequent drying up of the bed of the sea, so a like combination of causes may, in modern times, have been extending the low tract of land where marine shells and fossil bones occur in Siberia. Such a change in the physical geography of that region, implying a constant augmentation in the quantity of Arctic land, would, according to principles to be explained in the next chapter, tend to increase the severity of the winters. We may conclude, therefore, that before the land reached so far to the north, the temperature of the Siberian winter and summer was more nearly equalized, and a greater degree of winter's cold may, even more than a general diminution of the mean annual temperature, have finally contributed to the extermination of the mammoth and its contemporaries. On referring to the map, the reader will see how all the great rivers of Siberia flow at present from south to north, from temperate to Arctic regions, and they are all liable, like the Mackenzie in North America, to remarkable floods, in consequence of flowing in this direction. For they are filled with running water in their upper or southern course when completely frozen over for several hundred miles near their mouths, where they remain blocked up by ice for 6 months in every year. The descending waters, therefore, finding no open channel, rush over the ice, often changing their direction and sweeping along forests and prodigious quantities of soil and gravel mixed with ice. Now the rivers of Siberia are among the largest in the world, and Yenisei having a course of 2,500, the Lena of 2,000 miles, so that we may easily conceive that the bodies of animals which fall into their waters may be transported to vast distances towards the Arctic Sea, and, before arriving there, may be stranded upon, and often frozen into, thick ice. Afterwards, when the ice breaks up, they may be floated still farther towards the ocean, until at length they become buried in fluviatile and submarine deposits near the mouths of rivers. Humboldt remarks that near the mouths of the Lena a considerable thickness of frozen soil may be found at all seasons at the depth of a few feet, so that if a carcass be once embedded in mud and ice in such a region and in such a climate, its putrefaction may be arrested for indefinite ages. According to Professor von Beer of St. Petersburg, the ground is now frozen permanently to the depth of 400 feet, at the town of Yakutsk, on the western bank of the Lena, in latitude 62 degrees north, 600 miles distant from the Polar Sea. Mr. Hedenstrom tells us that throughout a wide area in Siberia, the boundary cliffs of the lakes and rivers consist of alternate layers of earthy materials and ice in horizontal stratification, and Mr. Mittendorf informed us in 1846 that in his tour there 3 years before, he had bored in Siberia to the depth of 70 feet, and, after passing through much frozen soil mixed with ice, had come down upon a solid mass of pure transparent ice, the thickness of which, after penetrating 2 or 3 yards, they did not ascertain. We may conceive, therefore, that even at the period of the Mammoth, when the lowland of Siberia was less extensive towards the north, and consequently the climate more temperate than now, the cold may still have been sufficiently intense to cause the rivers flowing in their present direction to sweep down from south to north the bodies of drowned animals, and there bury them in drift ice and frozen mud. If it be true that the carcass of the mammoth was embedded in pure ice, there are 2 ways in which it may have been frozen in. We may suppose the animal to have been overwhelmed by drift snow. I have been informed by Dr. Richardson that, in the northern parts of America, comprising regions now inhabited by many herbivorous quadrupeds, the drift snow is often converted into permanent glaciers. It is commonly blown over the edges of steep cliffs, so as to form an inclined talus hundreds of feet high, and when a thaw commences, torrents rush from the land, and throw down from the top of the cliff alluvial soil and gravel. This new soil soon becomes covered with vegetation, and protects the foundation of snow from the rays of the sun. Water occasionally penetrates into the crevices and pores of the snow, but as it soon freezes again, it serves the more rapidly to consolidate the mass into a compact iceberg. It may sometimes happen that cattle grazing in a valley at the base of such cliffs, on the borders of a sea or river, may be overwhelmed, and at length enclosed in solid ice, and then transported towards the polar regions. Or a herd of mammoths returning from their summer pastures in the north may have been surprised, while crossing a stream, by the sudden congelation of the waters. The missionary Huck relates, in his travels in Tibet in 1846, that, after many of his party had been frozen to death, they pitched their tents on the banks of the Mourois-Ousson, which lower down becomes the famous Blue River, and saw from their encampment some black, shapeless objects ranged in file across the stream. As they advanced nearer, no change either in form or distinctness was apparent, nor was it till they were quite close that they recognized in them a troop of the wild oxen, called yak by the Tibetans. There were more than 50 of them encrusted in the ice. No doubt they had tried to swim across at the moment of congelation and had been unable to disengage themselves. Their beautiful heads, surmounted by huge horns, were still above the surface, but their bodies were held fast in the ice, which was so transparent that the position of the imprudent beasts was easily distinguishable. They looked as if still swimming, but the eagles and ravens had pecked out their eyes. The foregoing investigations, therefore, lead us to infer that the mammoth and some other extinct quadrupeds fitted to live in high latitudes were inhabitants of northern Asia at a time when the geographical conditions and climate of that continent were different from the present. But the age of this fauna was comparatively modern in the earth's history. It appears that when the oldest or Eocene tertiary deposits were formed, a warm temperature pervaded the European seas and lands. Shells of the genus Nautilus and other forms characteristic of tropical latitudes, fossil reptiles such as the crocodile, turtle, and tortoise, plants such as palms, some of them allied to the cocoa nut, the screw pine, the custard apple, and the acacia, all lead to this conclusion. This flora and fauna were followed by those of the Miocene formation, in which indications of a southern but less tropical climate are detected. Finally, the Pliocene deposits, which come next in succession, exhibit in their organic remains a much nearer approach to the state of things now prevailing in corresponding latitudes. It was towards the close of this period that the seas of the northern hemisphere became more and more filled with floating icebergs, often charged with erratic blocks, so that the waters and the atmosphere were chilled by the melting ice, and an Arctic fauna enabled, for a time, to invade the temperate latitudes both of North America and Europe. The extinction of a considerable number of land quadrupeds and aquatic mollusca was gradually brought about by the increasing severity of the cold, but many species survived this revolution in climate, either by their capacity of living under a variety of conditions, or by migrating for a time to more southern lands and seas. At length, by modifications in the physical geography of the northern regions, and the cessation of floating ice on the eastern side of the Atlantic, the cold was moderated, and a milder climate ensued, such as we now enjoy in Europe. Proofs from fossils in secondary and still older strata. A great interval of time appears to have elapsed between the formation of the secondary strata, which constitute the principal portion of the elevated land in Europe, and the origin of the Eocene deposits. If we examine the rocks from the chalk to the new red sandstone inclusive, we find many distinct assemblages of fossils entombed in them, all of unknown species, and many of them referable to genera and families now most abundant between the tropics. Among the most remarkable are reptiles of gigantic size, some of them herbivorous, others carnivorous, and far exceeding in size any now known even in the torrid zone. The genera are for the most part extinct, but some of them, as the crocodile and monitor, have still representatives in the warmer parts of the earth. Coral reefs also were evidently numerous in the seas of the same periods, composed of species often belonging to genera now characteristics of a tropical climate. The number of large chambered shells also, including the Nautilus, leads us to infer an elevated temperature, and the associated fossil plants, although imperfectly known, tend to the same conclusion, the Cycadiae constituting the most numerous family. But it is from the more ancient coal deposits that the most extraordinary evidence has been supplied in proof of the former existence of a very different climate, a climate which seems to have been moist, warm, and extremely uniform, in those very latitudes which are now the colder, and, in regard to temperature, the most variable regions of the globe. We learn from the researches of Adolphe Brongniart, Goeppert, and other botanists that in the flora of the Carboniferous era there was a great predominance of ferns, some of which were arborescent, as, for example, Colopteris, Protopteris, and Saronius, nor can this be accounted for, as some have supposed, by the greater power which ferns possess of resisting maceration in water. This prevalence of ferns indicates a moist, equable, and temperate climate, and the absence of any severe cold, for such are the conditions which, at the present day, are found to be most favorable to that tribe of plants. It is only in the islands of the tropical oceans, and of the southern temperate zone, such as Norfolk Island, Otaheite, the Sandwich Islands, Tristan da Cunha, and New Zealand, that we find any near approach to that remarkable preponderance of ferns which is characteristic of the Carboniferous flora. It has been observed that tree ferns and other forms of vegetation which flourished most luxuriantly within the tropics extend to a much greater distance from the equator in the southern hemisphere than in the northern, being found even as far as 46 degrees south latitude in New Zealand. There is little doubt that this is owing to the more uniform and moist climate occasioned by the greater proportional area of sea. Next to ferns and pines, the most abundant vegetable forms in the coal formation are the calamites, Lepidodendra, Sigillariae, and Stigmariae. These were formerly considered to be so closely allied to tropical genera and to be so much greater in size than the corresponding tribes now inhabiting equatorial latitudes that they were thought to imply an extremely hot as well as humid and equable climate. But recent discoveries respecting the structure and relations of these fossil plants have shown that they deviated so widely from all existing types in the vegetable world that we have more reason to infer from this evidence a widely different climate in the Carboniferous era as compared to that now prevailing than a temperature extremely elevated. Palms, if not entirely wanting when the strata of the Carboniferous group were deposited, appear to have been exceedingly rare. The Coniferae, on the other hand, so abundantly met within the coal, resemble Araucariae in structure, a family of the fir tribe, characteristic at present of the milder regions of the southern hemisphere, such as Chile, Brazil, New Holland, and Norfolk Island. In regard to the geographical extent of the ancient vegetation, it was not confined, says M. Brongniart, to a small space, as to Europe, for example, for the same forms are met with again at great distances. Thus, the coal plants of North America are, for the most part, identical with those of Europe, and all belong to the same genera. Some specimens also from Greenland are referable to ferns, analogous to those of our European coal mines. The fossil plants brought from Melville Island, although in a very imperfect state, have been supposed to warrant similar conclusions, and assuming that they agree with those of Baffin's Bay, mentioned by M. Brongniart, how shall we explain the manner in which such a vegetation lived through an Arctic night of several months' duration? It may seem premature to discuss this question until the true nature of the fossil flora of the Arctic regions has been more accurately determined. Yet, as the question has attracted some attention, let us assume for a moment that the coal plants of Melville Island are strictly analogous to those of the strata of Northumberland. Would such a fact present an inexplicable enigma to the vegetable physiologist? Plants, it is affirmed, cannot remain in darkness, even for a week, without serious injury, unless in a torpid state, and if exposed to heat and moisture they cannot remain torpid, but will grow, and must therefore perish. If then, in the latitude of Melville Island, 75 degrees north, a high temperature and consequent humidity prevailed at that period when we know the Arctic seas were filled with corals and large multilocular shells, how could plants of tropical forms have flourished? Is not the bright light of equatorial regions as indispensable a condition of their well-being as the sultry heat of the same countries? And how could they annually endure a night prolonged for 3 months? Now, in reply to this objection, we must bear in mind, in the first place, that, so far as experiments have been made, there is every reason to conclude that the range of intensity of light to which living plants can accommodate themselves is far wider than that of heat. No palms or tree ferns can live in our temperate latitudes without protection from the cold, but when placed in hothouses they grow luxuriantly, even under a cloudy sky, and where much light is intercepted by the glass and framework. At St. Petersburg, in latitude 60 degrees north, these plants have been successfully cultivated in hothouses, although there they must exchange the perpetual equinox of their native regions for days and nights which are alternately protracted to 19 hours and shortened to 5. How much farther towards the pole they might continue to live, provided a due quantity of heat and moisture were supplied, has not yet been determined, but St. Petersburg is probably not the utmost limit, and we should expect that in latitude 65 degrees at least, where they would never remain 24 hours without enjoying the sun's light, they might still exist. It should also be borne in mind, in regard to tree ferns, that they grow in the gloomiest and darkest parts of the forest of warm and temperate regions, even extending to nearly the 46th degree of south latitude in New Zealand. In equatorial countries, says Humboldt, they abound chiefly in the temperate, humid, and shady parts of mountains. As we know, therefore, that elevation often compensates for the effect of latitude in the geographical distribution of plants, we may easily understand that a class of vegetables, which grows at a certain height in the torrid zone, would flourish on the plains at greater distances from the equator, if the temperature, moisture, and other necessary conditions were equally uniform throughout the year. Nor must we forget that in all the examples above alluded to, we have been speaking of living species, but the coal plants were of perfectly distinct species, nay, few of them except the ferns and pines can be referred to genera or even families of the existing vegetable kingdom. Having a structure, therefore, and often a form which appears to the botanist so anomalous, they may also have been endowed with a different constitution, enabling them to bear a greater variation of circumstances in regard to light. We find that particular species of plants and tree ferns require at present different degrees of heat, and that some species can thrive only in the immediate neighborhood of the equator, others only a distance from it. In the same manner, the minimum of light, sufficient for the now existing species, cannot be taken as the standard for all analogous tribes that may ever have flourished on the globe. But granting that the extreme northern point to which a flora like that of the Carboniferous era could ever reach may be somewhere between the latitudes of 65 degrees and 70 degrees, we should still have to inquire whether the vegetable remains might not have been drifted from thence, by rivers and currents, to the parallel of Melville Island, or still farther. In the northern hemisphere at present, we see that the materials for future beds of lignite and coal are becoming amassed in high latitudes, far from the districts where the forests grew, and on shores where scarcely a stunted shrub can now exist. The Mackenzie and other rivers of North America carry pines with their roots attached for many hundred miles towards the north, into the Arctic Sea, where they are embedded in deltas, and some of them drifted still farther by currents towards the pole. Before we can decide on this question of transportation, we must know whether the fossil coal plants occurring in high latitudes bear the marks of friction and of having decayed previously to fossilization. Many appearances in our English coal fields certainly prove that the plants were not floated from great distances, for the outline of the stems of succulent species preserve their sharp angles, and others have their surfaces marked with the most delicate lines and streaks. Long leaves also are attached in many instances to the trunks or branches, and leaves, we know, in general, are soon destroyed when steeped in water, although ferns will retain their forms after an immersion of many months. It seems fair to presume that most of the coal plants grew upon the same land which supplied materials for the sandstones and conglomerates of the strata in which they are embedded. The coarseness of the particles of many of these rocks attest that they were not born from very remote localities, and there was land therefore in the vicinity wasting away by the action of moving waters. The progress also of modern discovery has led to the very general admission of the doctrine that beds of coal have, for the most part, been formed of the remains of trees and plants that grew on the spot where the coal now exists, the land having been successively submerged, so that a covering of mud and sand was deposited upon accumulations of vegetable matter. That such has been the origin of some coal seams is proved by the upright position of fossil trees, both in Europe and America, in which the roots terminate downwards in beds of coal. To return, therefore, from this digression, the flora of the coal appears to indicate a uniform and mild temperature in the air, while the fossils of the contemporaneous mountain limestone, comprising abundance of lamelliferous corals, large chambered cephalopods, and crinoidea, naturally lead us to infer a considerable warmth in the waters of the Northern Sea of the Carboniferous period. So also in regard to strata older than the coal, they contain in high northern latitudes mountain masses of corals, which must have lived and grown on the spot, and large chambered univalves, such as Orthocerata and Nautilus, all seeming to indicate, even in regions bordering on the Arctic Circle, the former prevalence of a temperature more elevated than that now prevailing. The warmth and humidity of the air, and the uniformity of climate, both in the different seasons of the year and in different latitudes, appears to have been most remarkable when some of the oldest of the fossiliferous strata were formed. The approximation to a climate similar to that now enjoyed in these latitudes does not commence till the era of the formations termed Tertiary, and while the different Tertiary rocks were deposited in succession, from the Eocene to the Pliocene, the temperature seems to have been lowered, and to have continued to diminish even after the appearance upon the earth of a considerable number of the existing species, the cold reaching its maximum of intensity in European latitudes during the glacial epoch, or the epoch immediately antecedent to that in which all the species now contemporary with man were in being. End of Chapter 6, Part 2. Chapter 7, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2019. Principles of Geology by Charles Lyell. Chapter 7, Part 1. Further examination of the question as to the assumed discordance of the ancient and modern causes of change. On the causes of vicissitudes in climate. Remarks on the present diffusion of heat over the globe. On the dependence of the mean temperature on the relative position of land and sea. Isothermal lines. Currents from equatorial regions. Drifting of icebergs. Different temperature of northern and southern hemispheres. Combination of causes which might produce the extreme cold of which the Earth's surface is susceptible. Conditions necessary for the production of the extreme of heat and its probable effects on organic life. Causes of vicissitudes in climate. As the proofs enumerated in the last chapter indicate that the Earth's surface has experienced great changes of climate since the deposition of the older sedimentary strata, we have next to inquire how such vicissitudes can be reconciled with the existing order of nature. The cosmogonist has availed himself of this, as of every obscure problem in geology, to confirm his views concerning a period when the planet was in a nascent or half-formed state, or when the laws of the animate and inanimate world differed essentially from those now established, and he has in this, as in many other cases, succeeded so far as to divert attention from that class of facts which, if fully understood, might probably lead to an explanation of the phenomena. At first it was imagined that the Earth's axis had been for ages perpendicular to the plane of the ecliptic, so that there was a perpetual equinox and uniformity of seasons throughout the year. That the planet enjoyed this paradisiacal state until the era of the Great Flood, but in that catastrophe, whether by the shock of a comet or some other convulsion, it lost its equal poise, and hence the obliquity of its axis, and with that the varied seasons of the temperate zone, and the long nights and days of the polar circles. When the progress of astronomical science had exploded this theory, it was assumed that the Earth at its creation was in a state of fluidity and red hot, and that ever since that era it had been cooling down, contracting its dimensions, and acquiring a solid crust, a hypothesis hardly less arbitrary, yet more calculated for lasting popularity, because, by referring the mind directly to the beginning of things, it requires no support from observation, nor from any ulterior hypothesis. But if, instead of forming vague conjectures as to what might have been the state of the planet at the era of its creation, we fix our thoughts on the connection at present existing between climate and the distribution of land and sea, and then consider what influence former fluctuations in the physical geography of the Earth must have had on superficial temperature, we may perhaps approximate to a true theory. If doubts and obscurities still remain, they should be ascribed to our limited acquaintance with the laws of nature, not to revolutions in her economy. They should stimulate us to farther research, not tempt us to indulge our fancies respecting the imaginary changes of internal temperature in an embryo world. Diffusion of heat over the globe. In considering the laws which regulate the diffusion of heat over the globe, we must be careful, as Humboldt well remarks, not to regard the climate of Europe as the type of the temperature which all countries placed under the same latitude enjoy. The physical sciences, observes this philosopher, always bear the impress of the places where they began to be cultivated, and as, in geology, an attempt was at first made to refer all the volcanic phenomena to those of the volcanoes in Italy, so in meteorology, a small part of the Old World, the center of the primitive civilization of Europe, was for a long time considered a type to which the climate of all corresponding latitudes might be referred. But this region, constituting only 1/7 of the whole globe, proved eventually to be the exception to the general rule. For the same reason, we may warn the geologist to be on his guard, and not hastily to assume that the temperature of the Earth in the present era is a type of that which most usually obtains, since he contemplates far mightier alterations in the positions of land and sea, at different epochs, than those which now cause the climate of Europe to differ from that of other countries in the same parallels. It is now well ascertained that zones of equal warmth, both in the atmosphere and in the waters of the ocean, are neither parallel to the equator nor to each other. It is also known that the mean annual temperature may be the same in two places which enjoy very different climates, for the seasons may be nearly uniform or violently contrasted, so that the lines of equal winter temperature do not coincide with those of equal annual heat or isothermal lines. The deviations of all these lines from the same parallel of latitude are determined by a multitude of circumstances, among the principal of which are the position, direction, and elevation of the continents and islands, the position and depths of the sea, and the direction of currents and of winds. On comparing the two continents of Europe and America, it is found that places in the same latitudes have sometimes a mean difference of temperature amounting to 11 degrees, or even in a few cases to 17 degrees Fahrenheit, and some places on the two continents, which have the same mean temperature, differ from 7 degrees to 17 degrees in latitude. Thus, Cumberland House in North America, having the same latitude, 54 degrees north, as the city of York in England, stands on the isothermal line of 32 degrees, which in Europe rises to the North Cape in latitude 71 degrees, but its summer heat exceeds that of Brussels or Paris. The principal cause of greater intensity of cold in corresponding latitudes of North America, as contrasted with Europe, is the connection of America with the polar circle by a large tract of land, some of which is from 3,000 to 5,000 feet in height, and, on the other hand, the separation of Europe from the Arctic Circle by an ocean. The ocean has a tendency to preserve everywhere a mean temperature, which it communicates to the contiguous land, so that it tempers the climate, moderating alike an excess of heat or cold. The elevated land, on the other hand, rising to the colder regions of the atmosphere, becomes a great reservoir of ice and snow, arrests, condenses, and congeals vapor, and communicates its cold to the adjoining country. For this reason, Greenland, forming part of a continent which stretches northward to the 82nd degree of latitude, experiences under the 60th parallel a more rigorous climate than Lapland under the 72nd parallel. But if land be situated between the 40th parallel and the equator, it produces, unless it be of extreme height, exactly the opposite effect, for it then warms the tracts of land or sea that intervene between it and the polar circle. For the surface being in this case exposed to the vertical, or nearly vertical rays of the sun, absorbs a large quantity of heat, which it diffuses by radiation into the atmosphere. For this reason, the western parts of the old continent derive warmth from Africa, which, like an immense furnace, distributes its heat to Arabia, to Turkey in Asia, and to Europe. On the contrary, the northeastern extremity of Asia experiences in the same latitude extreme cold, for it has land on the north between the 60th and 70th parallel, while to the south it is separated from the equator by the Pacific Ocean. In consequence of the more equal temperature of the waters of the ocean, the climate of islands and of coasts differs essentially from that of the interior of continents, the more maritime climate being characterized by mild winters and more temperate summers, for the sea breezes moderate the cold of winter as well as the heat of summer. When, therefore, we trace round the globe those belts in which the mean annual temperature is the same, we often find great differences in climate, for there are insular climates in which the seasons are nearly equalized, and excessive climates, as they have been termed, where the temperature of winter and summer is strongly contrasted. The whole of Europe, compared with the eastern parts of America and Asia, has an insular climate. The northern part of China and the Atlantic region of the United States exhibit excessive climates. We find at New York, says Humboldt, the summer of Rome and the winter of Copenhagen, at Quebec the summer of Paris and the winter of Petersburg. At Pekin, in China, where the mean temperature of the year is that of the coasts of Brittany, the scorching heats of summer are greater than at Cairo, and the winters as rigorous as at Uppsala. If lines be drawn round the globe through all those places which have the same winter temperature, they are found to deviate from the terrestrial parallels much farther than the lines of equal mean annual heat. The lines of equal winter in Europe, for example, are often curved so as to reach parallels of latitude 9 or 10 degrees distant from each other, whereas the isothermal lines, or those passing through places having the same mean annual temperature, differ only from 4 to 5 degrees in Europe. Influence of currents and drift ice on temperature. Among other influential causes, both of remarkable diversity in the mean annual heat and of unequal division of heat in the different seasons, are the direction of currents and the accumulation and drifting of ice in high latitudes. The temperature of the Lagulas current is 10 degrees or 12 degrees Fahrenheit above that of the sea at the Cape of Good Hope, for it derives the greater part of its waters from the Mozambique Channel and southeast coast of Africa, and from regions in the Indian Ocean much nearer the line and much hotter than the Cape. An opposite effect is produced by the equatorial current, which crosses the Atlantic from Africa to Brazil, having a breadth varying from 160 to 450 nautical miles. Its waters are cooler by 3 degrees to 4 degrees Fahrenheit than those of the ocean under the line, so that it moderates the heat of the tropics. But the effects of the Gulf Stream on the climate of the North Atlantic Ocean are far more remarkable. This most powerful of known currents has its source in the Gulf or Sea of Mexico, which, like the Mediterranean and other close seas in temperate or low latitudes, is warmer than the open ocean in the same parallels. The temperature of the Mexican Sea in summer is, according to Rennell, 86 degrees Fahrenheit, or at least 7 degrees above that of the Atlantic in the same latitude. From this great reservoir or cauldron of warm water, a constant current pours forth through the Straits of Bahama at the rate of 3 or 4 miles an hour. It crosses the ocean in a northeasterly direction, skirting the Great Bank of Newfoundland, where it still retains a temperature of 8 degrees above that of the surrounding sea. It reaches the Azores in about 78 days, after flowing nearly 3,000 geographical miles, and from thence it sometimes extends its course 1,000 miles farther so as to reach the Bay of Biscay, still retaining an excess of 5 degrees above the mean temperature of that sea. As it has been known to arrive there in the months of November and January, it may tend greatly to moderate the cold of winter in countries on the west of Europe. There is a large tract in the center of the North Atlantic, between the parallels of 33 degrees and 45 degrees northern latitude, which Rennell calls the recipient of the Gulf water. A great part of it is covered by the weed called sargasso, Sargassum bacchiferum, which the current floats in abundance from the Gulf of Mexico. This mass of water is nearly stagnant, is warmer by 7 or 10 degrees than the waters of the Atlantic, and may be compared to the fresh water of a river overflowing the heavier salt water of the sea. Rennell estimates the area of the recipient, together with that covered by the main current, as being 2,000 miles in length from east to west, and 350 in breadth from north to south, which, he remarks, is a larger area than that of the Mediterranean. The heat of this great body of water is kept up by the incessant and quick arrivals of fresh supplies of warm water from the south, and there can be no doubt that the general climate of parts of Europe and America is materially affected by this cause. It is considered probable by Scoresby that the influence of the Gulf Stream extends even to the sea near Spitzbergen, where its waters may pass under those of melted ice, for it has been found that in the neighborhood of Spitzbergen the water is warmer by 6 or 7 degrees at the depth of 100 and 200 fathoms than at the surface. This might arise from the known law that fresh water passes the point of greatest density when cooled down below 40 degrees, and between that and the freezing point expands again. The water of melted ice might be lighter, both as being fresh, having lost its salt in the decomposing process of freezing, and because its temperature is nearer the freezing point than the interior water of the Gulf Stream. The great glaciers generated in the valleys of Spitzbergen, in the 79th degree of north latitude, are almost all cut off at the beach, being melted by the feeble remnant of heat still retained by the Gulf Stream. In Baffin's Bay, on the contrary, on the west coast of Old Greenland, where the temperature of the sea is not mitigated by the same cause, and where there is no warmer undercurrent, the glaciers stretch out from the shore, and furnish repeated crops of mountainous masses of ice which float off into the ocean. The number and dimensions of these bergs is prodigious. Captain Sir John Ross saw several of them together in Baffin's Bay, aground, in water 1,500 feet deep. Many of them are driven down to Hudson's Bay, and, accumulating there, diffuse excessive cold over the neighboring continent, so that Captain Franklin reports that at the mouth of Hayes River, which lies in the same latitude as the north of Prussia or the south of Scotland, ice is found everywhere in digging wells in summer at the depth of 4 feet. Other bergs have been occasionally met with, at midsummer, in a state of rapid thaw, as far south as latitude 40 degrees and longitude about 60 degrees west, where they cool the water sensibly to the distance of 40 or 50 miles around, the thermometer sinking sometimes 17 degrees or even 18 degrees Fahrenheit in their neighborhood. It is a well-known fact that every 4 or 5 years a large number of icebergs floating from Greenland double Cape Langaness and are stranded on the west coast of Iceland. The inhabitants are then aware that their crops of hay will fail, in consequence of fogs which are generated almost incessantly, and the dearth of food is not confined to the land, for the temperature of the water is so changed that the fish entirely desert the coast. Difference of climate of the northern and southern hemispheres. When we compare the climate of the northern and southern hemispheres, we obtain still more instruction in regard to the influence of the distribution of land and sea on climate. The dry land in the southern hemisphere is to that of the northern in the ratio only of 1 to 3, excluding from our consideration that part which lies between the pole and the 78th degree of south latitude, which has hitherto proved inaccessible. And whereas in the northern hemisphere, between the pole and the 30th parallel of north latitude, the land and sea occupy nearly equal areas, the ocean in the southern hemisphere covers no less than 15 parts in 16 of the entire space included between the Antarctic Circle and the 30th parallel of south latitude. This great extent of sea gives a particular character to climates south of the equator, the winters being mild and the summers cool. Thus, in Van Diemen's Land, corresponding nearly in latitude to Rome, the winters are more mild than at Naples, and the summers not warmer than those at Paris, which is 7 degrees farther from the equator. The effects on animal and vegetable life are remarkable. Captain King observed large shrubs of fuchsia and veronica, which in England are treated as tender plants, thriving and in full flower in Tierra del Fuego, with the temperature at 36 degrees. He states also that hummingbirds were seen sipping the sweets of the flowers, after 2 or 3 days of constant rain, snow, and sleet, during which time the thermometer had been at the freezing point. Mr. Darwin also saw parrots feeding on the seeds of a tree called the winter spark, south of latitude 55 degrees, near Cape Horn. So, the orchideous plants which are parasitical on trees and are generally characteristic of the tropics advance to the 38th and 42nd degree of southern latitude, and even beyond the 45th degree in New Zealand, where they were found by Forster. In South America also arborescent grasses abound in the dense forests of Chiloé in latitude 42 degrees south, where They entwine the trees into one entangled mass to the height of 30 or 40 feet above the ground. Palm trees in the same quarter of the globe grow in latitude 37 degrees, an arborescent grass very like a bamboo in 40 degrees, and another closely allied kind of great length, but not erect, even as far south as 45 degrees. It has long been supposed that the general temperature of the southern hemisphere was considerably lower than that of the northern, and that the difference amounted to at least 10 degrees Fahrenheit. Baron Humboldt, after collecting and comparing a great number of observations, came to the conclusion that even a much larger difference existed, but that none was to be observed within the tropics, and only a small difference as far as the 35th and 40th parallel. Captain Cook was of opinion that the ice of the Antarctic predominated greatly over that of the Arctic region, that encircling the southern pole coming nearer to the equator by 10 degrees than the ice around the North Pole. All the recent voyages of discovery have tended to confirm this opinion, although Captain Weddell penetrated, in 1823, 3 degrees farther south than Captain Cook, reaching latitude 74 degrees 15 minutes south, longitude 34 degrees 17 minutes west, and Sir James Ross, in 1842, arrived at latitude 78 degrees 10 minutes south, as high a latitude, within 3 degrees, as the farthest point attained by Captain Peary in the Arctic Circle, or latitude 81 degrees 12 minutes north. The description given by ancient as well as modern navigators of the sea and land in high southern latitudes clearly attests the greater severity of the climate as compared to Arctic regions. In Sandwich Land, in latitude 59 degrees south, or in nearly the same parallel as the north of Scotland, Captain Cook found the whole country, from the summits of the mountains down to the very brink of the sea cliffs, covered many fathoms thick with everlasting snow, and this on the 1st of February, the hottest time of the year. And, what is still more astonishing, in the island of South Georgia, which is in the 54th degree south latitude, or the same parallel as Yorkshire, the line of perpetual snow descends to the level of the ocean. When we consider this fact, and then recollect that the highest mountains in Scotland, which ascend to an elevation of nearly 5,000 feet, and are 4 degrees farther to the north, do not attain the limit of perpetual snow on our side of the equator, we learn that latitude is one only of many powerful causes which determine the climate of particular regions of the globe. Captain Sir James Ross, in his exploring expedition in 1841-3, found that the temperature south of the 60th degree of latitude seldom rose above 32 degrees Fahrenheit. During the 2 summer months of the year 1841, January and February, the range of the thermometer was between 11 degrees and 32 degrees Fahrenheit, and scarcely once rose above the freezing point. The permanence of snow in the southern hemisphere is in this instance partly due to the floating ice, which chills the atmosphere and condenses the vapor, so that in summer the sun cannot pierce through the foggy air. But besides the abundance of ice which covers the sea to the south of Georgia and Sandwich Land, we may also, as Humboldt suggests, ascribe the cold of those countries in part to the absence of land between them and the tropics. If Africa and New Holland extended farther to the south, a diminution of ice would take place in consequence of the radiation of heat from these continents during summer, which would warm the contiguous sea and rarefy the air. The heated aerial currents would then ascend and flow more rapidly towards the South Pole and moderate the winter. In confirmation of these views, it is stated that the ice, which extends as far as the 68th degree and 71st degree of south latitude, advances more towards the equator whenever it meets an open sea, that is, where the extremities of the present continents are not opposite to it, and this circumstance seems explicable only on the principle above alluded to, of the radiation of heat from the lands so situated. The cold of the Antarctic regions was conjectured by Cook to be due to the existence of a large tract of land between the 70th degree of south latitude and the pole. The justness of these and other speculations of that great navigator have since been singularly confirmed by the investigation made by Sir James Ross in 1841. He found Victoria Land, extending from 71 degrees to 79 degrees south latitude, skirted by a great barrier of ice, the height of the land ranging from 4,000 to 14,000 feet, the whole entirely covered with snow, except a narrow ring of black earth surrounding the huge crater of the active volcano of Mount Erebus, rising 12,400 feet above the level of the sea. The position of a mountainous territory of such altitude, so near the pole, and so obvious a source of intense cold, fully explains why Graham's and Enderby's Land, discovered by Captain Biscoe in 1831-2, between latitude 64 degrees and 68 degrees south, presented a most wintry aspect, covered even in summer with ice and snow, and nearly destitute of animal life. In corresponding latitudes of the northern hemisphere, we not only meet with herds of wild herbivorous animals, but with land which man himself inhabits, and where he has even built ports and inland villages. The distance to which icebergs float from the polar regions on the opposite side of the line is, as might have been anticipated, very different. Their extreme limit in the northern hemisphere is latitude 40 degrees, as before mentioned, and they are occasionally seen in latitude 42 degrees north, near the termination of the Great Bank of Newfoundland, and at the Azores, latitude 42 degrees north, to which they are sometimes drifted from Baffin's Bay. But in the other hemisphere they have been seen, within the last few years, at different points off the Cape of Good Hope, between latitude 36 degrees and 39 degrees. One of these was 2 miles in circumference and 150 feet high, appearing like chalk when the sun was obscured, and having the luster of refined sugar when the sun was shining on it. Others rose from 250 to 300 feet above the level of the sea, and were therefore of great volume below, since it is ascertained by experiments on the buoyancy of ice floating in sea water that for every cubic foot seen above, there must at least be 8 cubic feet below water. If ice islands from the North Polar regions floated as far, they might reach Cape St. Vincent, and there, being drawn by the current that always sets in from the Atlantic through the Straits of Gibraltar, be drifted into the Mediterranean, so that the serene sky of that delightful region might soon be deformed by clouds and mist. Before the amount of difference between the temperature of the two hemispheres was ascertained, it was referred by many astronomers to the precession of the equinoxes, or the acceleration of the Earth's motion in its perihelium, in consequence of which the spring and summer of the southern hemisphere are now shorter, by nearly 8 days, than those seasons north of the equator. But Sir J. Herschel reminds us that the excess of 8 days in the duration of the sun's presence in the northern hemisphere is not productive of an excess of annual light and heat, since, according to the laws of elliptic motion, it is demonstrable that whatever be the ellipticity of the Earth's orbit, the two hemispheres must receive equal absolute quantities of light and heat per annum, the proximity of the sun in perigee exactly compensating the effect of its swifter motion. Humboldt, however, observes that there must be a greater loss of heat by radiation in the southern hemisphere during a winter longer by 8 days than that on the other side of the equator. Perhaps no very sensible effect may be produced by this source of disturbance, yet the geologist should bear in mind that to a certain extent it operates alternately on each of the two hemispheres for a period of upwards of 10,000 years, dividing unequally the times during which the annual supply of solar light and heat is received. This cause may sometimes tend to counterbalance inequalities of temperature resulting from other, far more influential circumstances, but, on the other hand, it must sometimes tend to increase the extreme of deviation arising from particular combinations of causes. But whatever may be at present the inferiority of heat in the temperate and frigid zones south of the line, it is quite evident that the cold would be far more intense if there happened, instead of open sea, to be tracts of elevated land between the 55th and 70th parallel, and, on the other hand, the cold would be moderated if there were more land between the line and the 45th degree of south latitude. End of Chapter 7, Part 1. Chapter 7, Part 2 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2019. Principles of Geology by Charles LYELL. Chapter 7, Part 2. Changes in the position of land and sea may give rise to vicissitudes in climate. Having offered these brief remarks on the diffusion of heat over the globe in the present state of the surface, I shall now proceed to speculate on the vicissitudes of climate, which must attend those endless variations in the geographical features of our planet which are contemplated in geology. That our speculations may be confined within the strict limits of analogy, I shall assume, first, that the proportion of dry land to sea continues always the same. Secondly, that the volume of the land rising above the level of the sea is a constant quantity, and not only that its mean, but that its extreme height is liable only to trifling variations. Thirdly, that both the mean and extreme depth of the sea are invariable, and fourthly, it may be consistent with due caution to assume that the grouping together of the land in continents is a necessary part of the economy of nature, for it is possible that the laws which govern the subterranean forces, and which act simultaneously along certain lines, cannot but produce, at every epoch, continuous mountain chains, so that the subdivision of the whole land into innumerable islands may be precluded. If it be objected that the maximum of elevation of land and depth of sea are probably not constant, nor the gathering together of all the land in certain parts, nor even perhaps the relative extent of land and water, I reply that the arguments about to be adduced will be strengthened if, in these peculiarities of the surface, there be considerable deviations from the present type. If, for example, all other circumstances being the same, the land is at one time more divided into islands than at another, a greater uniformity of climate might be produced, the mean temperature remaining unaltered, or if, at another era, there were mountains higher than the Himalaya, these, when placed in high latitudes, would cause a greater excess of cold. Or if we suppose that at certain periods no chain of hills in the world rose beyond the height of 10,000 feet, a greater heat might then have prevailed than is compatible with the existence of mountains thrice that elevation. However constant may be the relative proportion of sea and land, we know that there is annually some small variation in their respective geographical positions, and that in every century the land is in some parts raised and in others depressed in level, and so likewise is the bed of the sea. By these and other ceaseless changes, the configuration of the earth's surface has been remodeled again and again since it was the habitation of organic beings, and the bed of the ocean has been lifted up to the height of some of the loftiest mountains. The imagination is apt to take alarm when called upon to admit the formation of such irregularities in the crust of the earth after it had once become the habitation of living creatures. But, if time be allowed, the operation need not subvert the ordinary repose of nature, and the result is in a general view insignificant, if we consider how slightly the highest mountain chains cause our globe to differ from a perfect sphere. Chimborazo, though it rises to more than 21,000 feet above the sea, would be represented, on a globe of about 6 feet in diameter, by a grain of sand less than 1/20th of an inch in thickness. The superficial inequalities of the earth, then, may be deemed minute in quantity, and their distribution at any particular epoch must be regarded in geology as temporary peculiarities, like the height and outline of the cone of Vesuvius in the interval between two eruptions. But although, in reference to the magnitude of the globe, the unevenness of the surface is so unimportant, it is on the position and direction of these small inequalities that the state of the atmosphere, and both the local and general climate, are mainly dependent. Before considering the effect which a material change in the distribution of land and sea must occasion, it may be well to remark how greatly organic life may be affected by those minor variations, which need not in the least degree alter the general temperature. Thus, for example, if we suppose, by a series of convulsions, a certain part of Greenland to become sea, and, in compensation, a tract of land to rise and connect Spitzbergen with Lapland, an accession not greater in amount than one which the geologist can prove to have occurred in certain districts bordering the Mediterranean within a comparatively modern period, this altered form of the land might cause an interchange between the climate of certain parts of North America and of Europe, which lie in corresponding latitudes. Many European species of plants and animals would probably perish in consequence, because the mean temperature would be greatly lowered, and others would fail in America because it would there be raised. On the other hand, in places where the mean annual heat remained unaltered, some species which flourish in Europe, where the seasons are more uniform, would be unable to resist the greater heat of the North American summer, or the intenser cold of the winter, while others, now fitted by their habitats for the great contrast of the American seasons, would not be fitted for the insular climate of Europe. The vine, for example, according to Humboldt, can be cultivated with advantage 10 degrees farther north in Europe than in North America. Many plants endure severe frost, but cannot ripen their seeds without a certain intensity of summer heat and a certain quantity of light. Others cannot endure a similar intensity either of heat or cold. It is now established that many of the existing species of animals have survived great changes in the physical geography of the globe. If such species be termed modern, in comparison to races which preceded them, their remains, nevertheless, enter into submarine deposits many hundred miles in length, and which have since been raised from the deep to no inconsiderable altitude. When, therefore, it is shown that changes in the temperature of the atmosphere may be the consequence of such physical revolutions of the surface, we ought no longer to wonder that we find the distribution of existing species to be local in regard to longitude as well as latitude. If all species were now, by an exertion of creative power, to be diffused uniformly throughout those zones where there is an equal degree of heat, and in all respects a similarity of climate, they would begin from this moment to depart more and more from their original distribution. Aquatic and terrestrial species would be displaced, as Hooke long ago observed, so often as land and water exchanged places, and there would also, by the formation of new mountains and other changes, be transpositions of climate, contributing, in the manner before alluded to the local extermination of species. If we now proceed to consider the circumstances required for a general change of temperature, it will appear, from the facts and principles already laid down, that whenever a greater extent of high land is collected in the polar regions, the cold will augment, and the same result will be produced when there is more sea between or near the tropics, while, on the contrary, so often as the above conditions are reversed, the heat will be greater. If this be admitted, it will follow that unless the superficial inequalities of the earth be fixed and permanent, there must be never-ending fluctuations in the mean temperature of every zone, and that the climate of one era can no more be a type of every other than is one of our 4 seasons of all the rest. It has been well said that the earth is covered by an ocean, in the midst of which are 2 great islands, and many smaller ones, for the whole of the continents and islands occupy an area scarcely exceeding 1/4 of the whole superficies of the spheroid. Now, according to this analogy, we may fairly speculate on the probability that there would not be usually, at any given epoch of the past, more than about 1/4 dry land in a particular region, as, for example, near the poles, or between them and the 75th parallels of north and south latitude. If therefore at present there should happen to be, in both these quarters of the globe, much more than this average proportion of land, some of it in the Arctic region, being above 5,000 feet in height, and if in Antarctic latitudes a mountainous country has been found varying from 4,000 to 14,000 feet in height, this alone affords ground for concluding that, in the present state of things, the mean heat of the climate is below that which the earth's surface, in its more ordinary state, would enjoy. This presumption is heightened when we reflect on the results of the recent soundings made by Sir James Ross in the Southern Ocean, and continued for 4 successive years, ending 1844, which seem to prove that the mean depth of the Atlantic and Pacific is as great as Laplace and other eminent astronomers had imagined, for then we might look not only for more than 2/3 sea in the frigid zones, but for water of great depth, which could not readily be reduced to the freezing point. The same opinion is confirmed when we compare the quantity of land lying between the poles and the 30th parallels of north and south latitude, with the quantity placed between those parallels and the equator, for it is clear that we have at present not only more than the usual degree of cold in the polar regions, but also less than the average quantity of heat within the tropics. Position of land and sea which might produce the extreme of cold of which the earth's surface is susceptible. To simplify our view of the various changes in climate, which different combinations of geographical circumstances may produce, we shall first consider the conditions necessary for bringing about the extreme of cold, or what would have been termed in the language of the old writers, the winter of the great year, or geological cycle, and afterwards the conditions requisite to produce the maximum of heat, or the summer of the same year. To begin with the northern hemisphere. Let us suppose those hills of the Italian peninsula and of Sicily, which are of comparatively modern origin, and contain many fossil shells identical with living species, to subside again into the sea, from which they have been raised, and that an extent of land of equal area and height, varying from 1 to 3,000 feet, should rise up in the Arctic Ocean between Siberia and the North Pole. In speaking of such changes, I shall not allude to the manner in which I conceive it possible that they may be brought about, nor of the time required for their accomplishment, reserving for a future occasion not only the proofs that revolutions of equal magnitude have taken place, but that analogous operations are still in gradual progress. The alteration now supposed in the physical geography of the northern regions would cause additional snow and ice to accumulate where now there is usually an open sea, and the temperature of the greater part of Europe would be somewhat lowered, so as to resemble more nearly that of corresponding latitudes of North America, or, in other words, it might be necessary to travel about 10 degrees farther south in order to meet with the same climate which we now enjoy. No compensation would be derived from the disappearance of land in the Mediterranean countries, but the contrary, since the mean heat of the soil in those latitudes probably exceeds that which would belong to the sea by which we imagine it to be replaced. But let the configuration of the surface be still farther varied, and let some large district within or near the tropics, such as Brazil, with its plains and hills of moderate height, be converted into sea, while lands of equal elevation and extent rise up in the Arctic Circle. From these change there would, in the first place, result a sensible diminution of temperature near the tropic, for the Brazilian soil would no longer be heated by the sun, so that the atmosphere would be less warm, as also the neighboring Atlantic. On the other hand, the whole of Europe, Northern Asia, and North America would be chilled by the enormous quantity of ice and snow thus generated on the new Arctic continent. If, as we have already seen, there are now some points in the southern hemisphere where snow is perpetual down to the level of the sea, in latitudes as low as central England, such might assuredly be the case throughout a great part of Europe, under the change of circumstances above supposed, and if at present the extreme range of drifted icebergs is the Azores, they might easily reach the equator after the assumed alteration. But to pursue the subject still farther, let the Himalaya mountains, with the whole of Hindustan, sink down, and their place be occupied by the Indian Ocean, while an equal extent of territory and mountains, of the same vast height, rise up between North Greenland and the Orkney Islands. It seems difficult to exaggerate the amount to which the climate of the northern hemisphere would then be cooled. But the refrigeration brought about at the same time in the southern hemisphere would be nearly equal, and the difference of temperature between the Arctic and equatorial latitudes would not be much greater than at present, for no important disturbance can occur in the climate of a particular region without its immediately affecting all other latitudes, however remote. The heat and cold which surround the globe are in a state of constant and universal flux and reflux. The heated and rarefied air is always rising and flowing from the equator towards the poles in the higher regions of the atmosphere, while in the lower, the colder air is flowing back to restore the equilibrium. That this circulation is constantly going on in the aerial currents is not disputed. It is often proved by the opposite course of the clouds at different heights, and the fact has been farther illustrated in a striking manner by two recent events. The trade wind continually blows with great force from the island of Barbados to that of St. Vincent, notwithstanding which, during the eruption of the volcano in the island of St. Vincent in 1812, ashes fell in profusion from a great height in the atmosphere upon Barbados. In like manner, during the great eruption of Sumbawa in 1815, ashes were carried to the islands of Amboyna and Banda, which last is about 800 miles east from the site of the volcano. Yet the southeast monsoon was then at its height. This apparent transposition of matter against the wind confirmed the opinion of the existence of a counter-current in the higher regions, which had previously rested on theoretical conclusions only. That a corresponding interchange takes place in the seas is demonstrated, according to Humboldt, by the cold which is found to exist at great depths within the tropics, and, among other proofs, may be mentioned the mass of warmer water which the Gulf Stream is constantly bearing northwards, while a cooler current flows from the north along the coast of Greenland and Labrador, and helps to restore the equilibrium. Currents of colder, and therefore specifically heavier water, pass from the poles towards the equator, which cool the inferior parts of the ocean, so that the heat of the torrid zone and the cold of the polar circle balance each other. The refrigeration, therefore, of the polar regions resulting from the supposed alteration in the distribution of land and sea, would be immediately communicated to the tropics, and from them its influence would extend to the Antarctic Circle, where the atmosphere and the ocean would be cooled, so that ice and snow would augment. Although the mean temperature of higher latitudes in the southern hemisphere is, as before stated, for the most part, lower than that of the same parallels in the northern, yet, for a considerable space on each side of the line, the mean annual heat of the waters is found to be the same in corresponding parallels. If, therefore, by the new position of the land, the formation of icebergs had become of common occurrence in the northern temperate zone, and if these were frequently drifted as far as the equator, the same degree of cold which they generated would immediately be communicated as far as the Tropic of Capricorn, and from thence to the lands or ocean to the south. The freedom, then, of the circulation of heat and cold from pole to pole being duly considered, it will be evident that the mean temperature which may prevail at the same point at two distinct periods may differ far more widely than that of any 2 points in the same parallels of latitude, at one and the same period. For the range of temperature, or, in other words, the curvature of the isothermal lines in a given zone and at a given period, must always be circumscribed within narrow limits, the climate of each place in that zone being controlled by the combined influence of the geographical peculiarities of all other parts of the earth. Whereas, if we compare the state of things at two distinct and somewhat distant epochs, a particular zone may at one time be under the influence of one class of disturbing causes, and at another time may be affected by an opposite combination. The lands, for example, to the north of Greenland cause the present climate of North America to be colder than that of Europe in the same latitudes, but the excess of cold is not so great as it would have been if the western hemisphere had been entirely isolated or separated from the eastern like a distinct planet. For not only does the refrigeration produced by Greenland chill to a certain extent the atmosphere of northern and western Europe, but the mild climate of Europe reacts also upon North America and moderates the chilling influence of the adjoining polar lands. To return to the state of the earth after the changes above supposed, we must not omit to dwell on the important effects to which a wide expanse of perpetual snow would give rise. It is probable that nearly the whole sea, from the poles to the parallels of 45 degrees, would be frozen over, for it is well known that the immediate proximity of land is not essential to the formation and increase of field ice, provided there be in some part of the same zone a sufficient quantity of glaciers generated on or near the land to cool down the sea. Captain Scoresby, in his account of the Arctic regions, observes that when the sun's rays fall upon the snow-clad surface of the ice or land, they are in a great measure reflected, without producing any material elevation of temperature, but when they impinge on the black exterior of a ship, the pitch on one side occasionally becomes fluid, while ice is rapidly generated at the other. Now, field ice is almost always covered with snow, and thus not only land as extensive as our existing continents, but immense tracts of sea in the frigid and temperate zones might present a solid surface covered with snow, and reflecting the sun's rays for the greater part of the year. Within the tropics, moreover, where the ocean now predominates, the sky would no longer be serene and clear, as in the present era, but masses of floating ice would cause quick condensations of vapor, so that fogs and clouds would deprive the vertical rays of the sun of half their power. The whole planet, therefore, would receive annually a smaller portion of the solar influence, and the external crust would part, by radiation, with some of the heat which had been accumulated in it during a different state of the surface. This heat would be dissipated in the spaces surrounding our atmosphere, which, according to the calculations of M. Fourier, have a temperature much inferior to that of freezing water. After the geographical revolution above assumed, the climate of equinoctial lands might be brought at last to resemble that of the present temperate zone, or, perhaps, be far more wintry. They who should then inhabit such small isles and coral reefs as are now seen in the Indian Ocean and South Pacific would wonder that zoophytes of large dimensions had once been so prolific in their seas, or if, perchance, they found the wood and fruit of the cocoa-nut tree or the palm silicified by the waters of some ancient mineral spring, or encrusted with calcareous matter, they would muse on the revolutions which had annihilated such genera, and replaced them by the oak, the chestnut, and the pine. With equal admiration would they compare the skeletons of their small lizards with the bones of fossil alligators and crocodiles more than 20 feet in length, which, at a former epoch, had multiplied between the tropics, and when they saw a pine included in an iceberg drifted from latitudes which we now call temperate, they would be astonished at the proof thus afforded that forests had once grown where nothing could be seen in their own times but a wilderness of snow. If the reader hesitate to suppose so extensive an alteration of temperature as the probable consequence of geographical changes confined to one hemisphere, he should remember how great are the local anomalies in climate now resulting from the peculiar distribution of land and sea in certain regions. Thus, in the island of South Georgia, before mentioned, Captain Cook found the everlasting snows descending to the level of the seas between latitude 54 and 55 degrees south. No trees or shrubs were to be seen, and in summer a few rocks only, after a partial melting of the ice and snow, were scantily covered with moss and tufts of grass. If such a climate can now exist at the level of the sea in a latitude corresponding to that of Yorkshire, in spite of all those equalizing causes before enumerated, by which the mixture of the temperatures of distant regions is facilitated throughout the globe, what rigors might we not anticipate in a winter generated by the transfer of the mountains of India to our Arctic Circle? But we have still to contemplate the additional refrigeration which might be effected by changes in the relative position of land and sea in the southern hemisphere. If the remaining continents were transferred from the equatorial and contiguous latitudes to the south polar regions, the intensity of cold produced might, perhaps, render the globe uninhabitable. We are too ignorant of the laws governing the direction of subterranean forces to determine whether such a crisis be within the limits of possibility. At the same time, it may be observed that no distribution of land can well be imagined more irregular, or, as it were, capricious, than that which now prevails, for at present the globe may be divided into two equal parts, in such a manner that one hemisphere shall be almost entirely covered with water, while the other shall contain less water than land, and, what is still more extraordinary, on comparing the extratropical lands in the northern and southern hemispheres, the lands in the northern are found to be to those in the southern in the proportion of 13:1. To imagine all the lands, therefore, in high, and all the sea in low latitudes, as delineated in Figure 6, would scarcely be a more anomalous state of the surface. Position of land and sea which might give rise to the extreme of heat. Let us now turn from the contemplation of the winter of the great year, and consider the opposite train of circumstances which would bring on the spring and summer. To imagine all the lands to be collected together in equatorial latitudes, and a few promontories only to project beyond the 30th parallel, as represented in the annexed maps, would be undoubtedly to suppose an extreme result of geological change. But if we consider a mere approximation to such a state of things, it would be sufficient to cause a general elevation of temperature. Nor can it be regarded as a visionary idea that amidst the revolutions of the earth's surface, the quantity of land should, at certain periods, have been simultaneously lessened in the vicinity of both the poles and increased within the tropics. We must recollect that even now it is necessary to ascend to the height of 15,000 feet in the Andes under the line, and in the Himalaya mountains, which are without the tropic, to 17,000 feet, before we reach the limit of perpetual snow. On the northern slope, indeed, of the Himalaya range, where the heat radiated from a great continent moderates the cold, there are meadows and cultivated land at an elevation equal to the height of Mont Blanc. If, then, there were no Arctic lands to chill the atmosphere and freeze the sea, and if the loftiest chains were near the line, it seems reasonable to imagine that the highest mountains might be clothed with a rich vegetation to their summits, and that nearly all signs of frost would disappear from the earth. When the absorption of the solar rays was in no region impeded, even in winter, by a coat of snow, the mean heat of the earth's crust would augment to considerable depths, and springs, which we know to be in general an index of the mean temperature of the climate, would be warmer in all latitudes. The waters of lakes, therefore, and rivers would be much hotter in winter, and would be never chilled in summer by melted snow and ice. A remarkable uniformity of climate would prevail amid the archipelagos of the temperate and polar oceans, where the tepid waters of equatorial currents would freely circulate. The general humidity of the atmosphere would far exceed that of the present period, for increased heat would promote evaporation in all parts of the globe. The winds would be first heated in their passage over the tropical plains, and would then gather moisture from the surface of the deep, till, charged with vapor, they arrived at extreme northern and southern regions, and there, encountering a cooler atmosphere, discharged their burden in warm rain. If, during the long night of a polar winter, the snows should whiten the summits of some Arctic islands, they would be dissolved as rapidly by the returning sun as are the snows of Etna by the blasts of the Scirocco. We learn from those who have studied the geographical distribution of plants that in very low latitudes, at present, the vegetation of small islands remote from continents has a peculiar character, the ferns and allied families, in particular, bearing a great proportion to the total number of other plants. Other circumstances being the same, the more remote the isles are from the continents, the greater does this proportion become. Thus, in the continent of India and the tropical parts of New Holland, the proportion of ferns to the phaenogamous plants is only as 1 to 26, whereas in the South Sea Islands it is as 1 to 4, or even as 1 to 3. We might expect, therefore, in the summer of the great year, or cycle of climate, that there would be a predominance of tree ferns and plants, allied to genera now called tropical, in the islands of the wide ocean, while many forms now confined to Arctic and temperate regions, or only found near the equator on the summit of the loftiest mountains, would almost disappear from the earth. Then might those genera of animals return, of which the memorials are preserved in the ancient rocks of our continents. The pterodactyl might flit again through the air, the huge iguanodon reappear in the woods, and the ichthyosaurs swarm once more in the sea. Coral reefs might be prolonged again beyond the Arctic Circle, where the whale and the narwhal now abound, and droves of turtles might begin again to wander through regions now tenanted by the walrus and the sea. But not to indulge too far in these speculations, I may observe, in conclusion, that however great, during the lapse of ages, may be the vicissitudes of temperature in every zone, it accords with this theory that the general climate should not experience any sensible change in the course of a few thousand years, because that period is insufficient to affect the leading features of the physical geography of the globe. Notwithstanding the apparent uncertainty of the seasons, it is found that the mean temperature of particular localities is very constant, when observations made for a sufficient series of years are compared. Yet there must be exceptions to this rule, and even the labors of men have, by the drainage of lakes and marshes, and the felling of extensive forests, caused such changes in the atmosphere as greatly to raise our conception of the more important influence of those forces to which, in certain latitudes, even the existence of land or water, hill or valley, lake or sea, must be ascribed. If we possessed accurate information of the amount of local fluctuation in climate in the course of 20 centuries, it would often, undoubtedly, be considerable. Certain tracts, for example, on the coast of Holland and of England, consisted of cultivated land in the time of the Romans, which the sea, by gradual encroachments, has at length occupied. Here, at least, a slight alteration has been effected, for neither the distribution of heat in the different seasons nor the mean annual temperature of the atmosphere investing the sea is precisely the same as that which rests upon the land. In those countries also where earthquakes and volcanoes are in full activity, a much shorter period may produce a sensible variation. The climate of the great tableland of Malpais in Mexico must differ materially from that which prevailed before the middle of the last century, for since that time 6 mountains, the highest of them rising 1,600 feet above the plateau, have been thrown up by volcanic eruptions. It is by the repetition of an indefinite number of such local revolutions, and by slow movements extending simultaneously over wider areas, as will be afterwards shown, that a general change of climate may finally be brought about. End of Chapter 7, Part 2. Chapter 8, Part 1 of Principles of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2019. Principles of Geology by Charles Lyell. Chapter 8, Part 1. On former changes in physical geography and climate. Geographical features of the Northern Hemisphere at the period of the oldest fossiliferous strata. State of the surface when the mountain limestone and coal were deposited. Changes in physical geography between the Carboniferous period and the chalk. Abrupt transition from the secondary to the tertiary fossils. Accession of land and elevation of mountain chains after the consolidation of the secondary rocks. Explanation of map showing the area covered by sea since the commencement of the tertiary period. Astronomical theories of the causes of variations in climate. Theory of the diminution of the supposed primitive heat of the globe. In the 6th chapter, I stated the arguments derived from organic remains for concluding that in the period when the Carboniferous strata were deposited, the temperature of the ocean and the air was more uniform in the different seasons of the year and in different latitudes than at present, and that there was a remarkable absence of cold as well as great moisture in the atmosphere. It was also shown that the climate had been modified more than once since that epoch, and that it had been reduced, by successive changes, more and more nearly to that now prevailing in the same latitudes. Farther, I endeavored, in the last chapter, to prove that vicissitudes in climate of no less importance may be expected to recur in future, if it be admitted that causes now active in nature have power, in the lapse of ages, to produce considerable variations in the relative position of land and sea. It remains to inquire whether the alterations, which the geologist can prove to have actually taken place at former periods in the geographical features of the Northern Hemisphere, coincide in their nature and in the time of their occurrence with such revolutions in climate as might naturally have resulted, according to the meteorological principles already explained. Period of the primary fossiliferous rocks. The oldest system of strata which afford by their organic remains any evidence as to climate, or the former position of land and sea, are those formerly known as the transition rocks, or what have since been termed Lower Silurian or primary fossiliferous formations. These have been found in England, France, Germany, Sweden, Russia, and other parts of Central and Northern Europe, as also in the Great Lake District of Canada and the United States. The multilocular or chambered univalves, including the nautilus and the corals, obtained from the limestones of these ancient groups, have been compared to forms now most largely developed in tropical seas. The corals, however, have been shown by Mr. Milne Edwards to differ generally from all living zoophytes, so that conclusions as to a warmer climate drawn from such remote analogies must be received with caution. Hitherto, few, if any, contemporaneous vegetable remains have been noticed, but such as are mentioned agree more nearly with the plants of the Carboniferous era than any other, and would, therefore, imply a warm and humid atmosphere entirely free from intense cold throughout the year. This absence or great scarcity of plants as well as of freshwater shells and other indications of neighboring land, coupled with the wide extent of marine strata of this age in Europe and North America, are facts which imply such a state of physical geography, so far at least as regards the northern hemisphere, as would, according to the principles before explained, give rise to such a moist and equable climate. Carboniferous group. This group comes next in the order of succession, and one of its principal members, the mountain limestone, was evidently a marine formation, as is shown by the shells and corals which it contains. That the ocean of that period was of considerable extent in our latitudes, we may infer from the continuity of these calcareous strata over large areas in Europe, Canada, and the United States. The same group has also been traced in North America towards the borders of the Arctic Sea. There are also several regions in Scotland and in the central and northern parts of England, as well as in the United States, where marine carboniferous limestones alternate with strata containing coal, in such a manner as to imply the drifting down of plants by rivers into the sea, and the alternate occupation of the same space by fresh and salt water. Since the time of the earlier writers, no strata have been more extensively investigated, both in Europe and North America, than those of the ancient Carboniferous group, and the progress of science has led to a general belief that a large portion of the purest coal has been formed, not, as was once imagined, by vegetable matter floated from a distance, but by plants which grew on the spot, and somewhat in the manner of peat on the spaces now covered by the beds of coal. The former existence of land in some of these spaces has been proved, as already stated, by the occurrence of numerous upright fossil trees, with their roots terminating downwards in seams of coal, and still more generally by the roots of trees, Stigmariae, remaining in their natural position in the clays which underlie almost every layer of coal. As some nearly continuous beds of such coal have of late years been traced in North America, over areas 100 or 200 miles and upwards in diameter, it may be asked whether the large tracts of ancient land implied by this fact are not inconsistent with the hypothesis of the general prevalence of islands at the period under consideration. In reply, I may observe that the coal fields must originally have been low alluvial grounds, resembling in situation the cypress swamps of the Mississippi or the Sundarbans of the Ganges, being liable, like them, to be inundated at certain periods by a river or by the sea, if the land should be depressed a few feet. All the phenomena, organic and inorganic, imply conditions nowhere to be met with, except in the deltas of large rivers. We have to account for an abundant supply of fluviatile sediment, carried for ages towards one and the same region, and capable of forming strata of mud and sand thousands of feet, or even fathoms, in thickness, many of them consisting of laminated shale, enclosing the leaves of ferns and other terrestrial plants. We have also to explain the frequent intercalations of root beds and the interposition here and there of brackish and marine deposits, demonstrating the occasional presence of the neighboring sea. But these forest-covered deltas could only have been formed at the termination of large hydrographical basins, each drained by a great river and its tributaries, and the accumulation of sediment bears testimony to contemporaneous denudation on a large scale, and, therefore, to a wide area of land, probably containing within it one or more mountain chains. In the case of the great Ohio or Appalachian coal field, the largest in the world, it seems clear that the uplands drained by one or more great rivers were chiefly to the eastward, or they occupied a space now filled by part of the Atlantic Ocean, for the mechanical deposits of mud and sand increase greatly in thickness and coarseness of material as we approach the eastern borders of the coal field, or the southeast flanks of the Alleghany Mountains near Philadelphia. In that region, numerous beds of pebbles, often of the size of a hen's egg, are seen to alternate with beds of pure coal. But the American coal fields are all comprised within the 30th and 50th degrees of north latitude, and there is no reason to presume that the lands at the borders of which they originated ever penetrated so far or in such masses into the colder and Arctic regions so as to generate a cold climate. In the southern hemisphere, where the predominance of sea over land is now the distinguishing geographical feature, we nevertheless find a large part of the continent of Australia, as well as New Zealand, placed between the 30th and 50th degrees of southern latitude. The two islands of New Zealand taken together are between 800 and 900 miles in length, with a breadth in some parts of 90 miles, and they stretch as far south as the 46th degree of latitude. They afford, therefore, a wide area for the growth of a terrestrial vegetation, and the botany of this region is characterized by abundance of ferns, 140 species of which are already known, some of them attaining the size of trees. In this respect, the southern shores of New Zealand in the 46th degree of latitude almost vie with tropical islands. Another point of resemblance between the flora of New Zealand and that of the ancient Carboniferous period is the prevalence of the fir tribe or of coniferous wood. An argument of some weight in corroboration of the theory above explained respecting the geographical condition of the temperate and Arctic latitudes of the northern hemisphere in the Carboniferous period may also be derived from an examination of those groups of strata which immediately preceded the coal. The fossils of the Devonian and Silurian strata in Europe and North America have led to the conclusion that they were formed for the most part in deep seas, far from land. In those older strata, land plants are almost as rare as they are abundant or universal in the coal measures. Those ancient deposits, therefore, may be supposed to have belonged to an epoch when dry land had only just begun to be upraised from the deep, a theory which would imply the existence during the Carboniferous epoch of islands, instead of an extensive continent, in the area where the coal was formed. Such a state of things prevailing in the north, from the pole to the 30th parallel of latitude, if not neutralized by circumstances of a contrary tendency in corresponding regions south of the line, would give rise to a general warmth and uniformity of climate throughout the globe. Changes in physical geography between the formation of the Carboniferous strata and the chalk. We have evidence in England that the strata of the ancient Carboniferous group, already adverted to, were, in many instances, fractured and contorted, and often thrown into a vertical position, before the deposition of some even of the oldest known secondary rocks, such as the New Red Sandstone. Fragments of the older formations are sometimes included in the conglomerates of the more modern, and some of these fragments still retain their fossil shells and corals, so as to enable us to determine the parent rocks from whence they were derived. There are other proofs of the disturbance at successive epochs of different secondary rocks before the deposition of others, and satisfactory evidence that, during these reiterated convulsions, the geographical features of the northern hemisphere were frequently modified, and that from time to time new lands emerged from the deep. The vegetation, during some parts of the period in question, from the lias to the chalk inclusive, when genera allied to cycas and zamia were abundant, appears to have approached to that of the larger islands of the equatorial zone, such, for example, as we now find in the West Indian archipelago. These islands appear to have been drained by rivers of considerable size, which were inhabited by crocodiles and gigantic oviparous reptiles, both herbivorous and carnivorous, belonging for the most part to extinct genera. Of the contemporary inhabitants of the land, we have as yet acquired but scanty information, but we know that there were flying reptiles, insects, and small mammifers, allied to the marsupial tribes. A freshwater deposit, called the Wealden, occurs in the upper part of the secondary series of the south of England, which, by its extent and fossils, attests the existence in that region of a large river draining a continent or island of considerable dimensions. We know that this land was clothed with wood, and inhabited by huge terrestrial reptiles and birds. Its position so far to the north as the counties of Surrey and Sussex, at a time when the mean temperature of the climate is supposed to have been much hotter than at present, may at first sight appear inconsistent with the theory before explained, that the heat was caused by the gathering together of all the great masses of land in low latitudes, while the northern regions were almost entirely sea. But it must not be taken for granted that the geographical conditions already described as capable of producing the extreme of heat were ever combined at any geological period of which we have yet obtained information. It is more probable, from what has been stated in the preceding chapters, that a slight approximation to such an extreme state of things would be sufficient. In other words, if most of the dry land were tropical, and scarcely any of it Arctic or Antarctic, a prodigious elevation of temperature must ensue, even though a part of some continents should penetrate far into the temperate zones. Changes during the Tertiary periods. The secondary and tertiary formations of Europe, when considered separately, may be contrasted as having very different characters, the secondary appearing to have been deposited in open seas, the tertiary in regions where dry land, lakes, bays, and perhaps inland seas abounded. The secondary series is almost exclusively marine. The tertiary, even the oldest part, contains lacustrine strata, and not unfrequently freshwater and marine beds alternating. In fact, there is evidence of important geographical changes having occurred between the deposition of the Cretaceous system, or uppermost of the secondary series, and that of the oldest tertiary group, and still more between the era of the latter and that of the newer tertiary formations. This change in the physical geography of Europe and North America was accompanied by an alteration no less remarkable in organic life, scarcely any species being common both to the secondary and tertiary rocks, and the fossils of the latter affording evidence of a different climate. On the other hand, when we compare the tertiary formations of successive ages, we trace a gradual approximation in the embedded fossils, from an assemblage in which extinct species predominate, to one where the species agree for the most part with those now existing. In other words, we find a gradual increase of animals and plants fitted for our present climates, in proportion as the strata which we examine are more modern. Now, during all these successive tertiary periods, there are signs of a great increase of land in European and North American latitudes. By reference to the map and its description, page 121, the reader will see that about 2/3 of the present European lands have emerged since the earliest Tertiary group originated. Nor is this the only revolution which the same region has undergone within the period alluded to. Some tracts which were previously land have gained in altitude, others, on the contrary, having sunk below their former level. That the existing lands were not all upheaved at once into their present position is proved by the most striking evidence. Several Italian geologists, even before the time of Brocchi, had justly inferred that the Apennines were elevated several thousand feet above the level of the Mediterranean before the deposition of the modern sub-Apennine beds which flank them on either side. What now constitutes the central calcareous chain of the Apennines must for a long time have been a narrow, ridgy peninsula, branching off, at its northern extremity, from the Alps near Savona. This peninsula has since been raised from 1 to 2,000 feet, by which movement the ancient shores, and, for a certain extent, the bed of the contiguous sea, have been laid dry, both on the side of the Mediterranean and the Adriatic. The nature of these vicissitudes will be explained by the accompanying diagram, which represents a transverse section across the Italian peninsula. The inclined strata A are the disturbed formations of the Apennines, into which the ancient igneous rocks A are supposed to have intruded themselves. At a lower level on each flank of the chain are the more recent shelly beds B, which often contain rounded pebbles derived from the waste of contiguous parts of the older Apennine limestone. These, it will be seen, are horizontal, and lie in what is termed uncomfortable stratification on the more ancient series. They now constitute a line of hills of moderate elevation between the sea and the Apennines, but never penetrate to the higher and more ancient valleys of that chain. The same phenomena are exhibited in the Alps on a much grander scale, those mountains being composed in some even of their higher regions of the newer secondary and oldest tertiary formations, while they are encircled by a great zone of more modern tertiary rocks, both on their southern flanks towards the plains of the Po and on the side of Switzerland and Austria, and at their eastern termination towards Styria and Hungary. This newer tertiary zone marks the position of former seas or gulfs, like the Adriatic, wherein masses of strata accumulated, some single groups of which are not inferior in thickness to the most voluminous of our secondary formations in England. Some even of these newer groups have been raised to the height of 3,000 or 4,000 feet, and in proportion to their antiquity they generally rise to greater heights, the older of them forming interior zones nearest to the central ridges of the Alps. We have already ascertained that the Alps gained accessions to their height and width at several successive periods, and that the last series of improvements occurred when the seas were inhabited by many existing species of animals. We may imagine some future series of convulsions once more to heave up this stupendous chain, together with the adjoining bed of the sea, so that the mountains of Europe may rival the Andes in elevation, in which case the deltas of the Po, Adige, and the Brenta, now encroaching upon the Adriatic, might be uplifted, so as to form another exterior belt of considerable height around the southeastern flank of the Alps. The Pyrenees also have acquired their present altitude, which in Mont Perdu exceeds 11,000 feet, since the deposition of the Namaltic or Eocene division of the Tertiary series. Some of the tertiary strata at the base of the chain are raised to the height of only a few hundred feet above the sea, and retain a horizontal position, without partaking in general in the disturbance to which the older series has been subjected, so that the great barrier between France and Spain was almost entirely upheaved in the interval between the deposition of certain groups of tertiary strata. The remarkable break between the most modern of the known secondary rocks and the oldest tertiary may be apparent only and ascribable to the present deficiency of our information. Already the marls and green sand of Heers near Tongres in Belgium, observed by M. Dumont, and the Pisolithic limestone of the neighborhood of Paris, both intermediate in age between the Maastricht chalk and the lower Eocene strata, begin to afford us signs of a passage from one state of things to another. Nevertheless, it is far from impossible that the interval between the chalk and tertiary formations constituted an era in the Earth's history, when the transition from one class of organic beings to another was, comparatively speaking, rapid. For if the doctrines above explained in regard to vicissitudes of temperature are sound, it will follow that changes of equal magnitude in the geographical features of the globe may at different periods produce very unequal effects on climate, and, so far as the existence of certain animals and plants depends on climate, the duration of species would be shortened or protracted according to the rate at which the change of temperature proceeded. For even if we assume that the intensity of the subterranean disturbing forces is uniform and capable of producing nearly equal amounts of alteration on the surface of the planet during equal periods of time, still the rate of alteration in climate would be by no means uniform. Let us imagine the quantity of land between the equator and the tropic in one hemisphere to be to that in the other as 13:1, which, as before stated, represents the unequal proportion of the extratropical lands in the two hemispheres at present. Then, let the first geographical change consist in the shifting of this preponderance of land from one side of the line to the other, from the southern hemisphere, for example, to the northern. Now, this need not affect the general temperature of the earth. But if, at another epoch, we suppose a continuance of the same agency to transfer an equal volume of land from the torrid zone to the temperate and Arctic regions of the northern and southern hemispheres, or into one of them, there might be so great a refrigeration of the mean temperature in all latitudes that scarcely any of the pre-existing races of animals would survive, and, unless it pleased the author of nature that the planet should be uninhabited, new species, and probably of widely different forms, would then be substituted in the room of the extinct. We ought not, therefore, to infer that equal periods of time are always attended by an equal amount of change in organic life, since a great fluctuation in the mean temperature of the earth, the most influential cause which can be conceived in exterminating whole races of animals and plants, must, in different epochs, require unequal proportions of time for its completion. This map will enable the reader to perceive at a glance the great extent of change in the physical geography of Europe, which can be proved to have taken place since some of the older tertiary strata began to be deposited. The proofs of submergence, during some part or other of this period, in all the districts distinguished by ruled lines, are of a most unequivocal character, for the area thus described is now covered by deposits containing the fossil remains of animals which could only have lived in salt water. The most ancient part of the period referred to cannot be deemed very remote, considered geologically, because the deposits of the Paris and London basins, and many other districts belonging to the older tertiary epoch, are newer than the greater part of the sedimentary rocks, those commonly called secondary and primary fossiliferous or Paleozoic, of which the crust of the globe is composed. The species, moreover, of marine testacea, of which the remains are found in these older tertiary formations, are not entirely distinct from such as now live. Yet, notwithstanding the comparatively recent epoch to which this retrospect is carried, the variations in the distribution of land and sea depicted on the map form only a part of those which must have taken place during the period under consideration. Some approximation has merely been made to an estimate of the amount of sea converted into land in parts of Europe best known to geologists, but we cannot determine how much land has become sea during the same period, and there may have been repeated interchanges of land and water in the same places, changes of which no account is taken in the map, and respecting the amount of which little accurate information can ever be obtained. I have extended the sea in some instances beyond the limits of the land now covered by tertiary formations and marine drift, because other geological data have been obtained for inferring the submergence of these tracts after the deposition of the Eocene strata had begun. Thus, for example, there are good reasons for concluding that part of the chalk of England, the North and South Downs, for example, together with the intervening secondary tracts, continued beneath the sea until the oldest tertiary beds had begun to accumulate. End of Chapter 8, Part 1.